Yeah.
Yeah, next time when you in that area, come over.
Yeah, I'm gonna be there September 28th for another talk.
Okay.
Yeah, so
You want to stop by? We have actually several research centers there, including
okay.
like NYU Artists. We have NYC Media Lab, and we have Hinds, which is system sponsored by UCLA,
Okay.
focused on IT,
Okay.
including media. ID. Yeah. So yeah, just maybe
I'll
drop me
send
an
you. I
email,
will.
and I think yeah, several faculty definitely very interested in AR VR. Actually, we are putting a center on AR VR. It's a Immersive sponsor center. That's actually encourage not just research, also startups, how to kind of transfer technology.
So do you, for VR, you consider that to be the headset that is completely isolating, right?
Don't have to. Don't have to.
Okay.
Yeah. So I mean, you can nowadays, I mean, for example, 360 video streaming stuff.
Hmm.
You can do that on your computer. Use your mouse to move things around,
Okay.
but it's
Okay.
not that
Okay.
great.
Okay.
But I think I think we're working on 360 video streaming.
Hmm.
It can be applied to
Yeah.
desktop
Yeah.
display. It can be
Yeah.
applied to computer.
Yeah.
I think we have several papers.
Yeah. 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 The second half of the session. Yeah.
Okay, let's get started.
Okay.
Zhang? Okay. First, want to welcome everybody come to this AR VR network workshop. So this is the second, actually, AR VR network workshop. We had the first one last year, was very successful, and this year, and we want to do it again. And of course, I think everybody agrees that AR VR is going to be our next big thing, right? So whenever you talk to people working on future networking technology, what will be the killer apps? And they're actually looking for killer apps as well. They said, "Oh, I have all the bandwidth here, and how are we going to use up all those bandwidth?" So I always tell them, do AR VR. So, but it's not as easy as I just said, because lots of challenges remaining there, and everybody agree there's going to be a bandwidth challenge. There's going to be a delay challenge. It's actually more than that, and we also have lots of other issues like security issues, like how you going to deal with mobility, how you going to deal with reliability, and how you going to deliver at the end very good user experience. Okay, so we have this is why we have this workshop here. We have a half-day program, very compact, but we have very good papers and also very good keynote talk. So, since this is a workshop, I actually encourage we have more kind of interaction. Since we have very selected audience here, so we actually would encourage to have questions and discussions. That will be during the keynote, I assume,
Yeah.
right?
Yeah.
Also,
That's be fine.
okay. So, roughly we're going to have three kind of segments for this morning, and we're going to start with keynote, and then we have one, let's say, small segment on like AR, augmented reality. Have two papers there. Then we are going to have a break. After a break, we come back. We have another segment focused on 360 video streaming. That's mostly for VR, but also can be used for AR. Okay, so that's roughly how we're going to go about it. Before I guess get into this keynote, let me introduce myself. Sorry, I didn't do that. My name is Yong I'm from NYU, and also I want to introduce our co-chair Richard Lee from Huawei. And so we have been doing this together for 2 years, and definitely it's a good experience for us. Okay. So of course we will also want to thank all the kind of TPC members, and I'm not showing their names here, but you can find their names in the kind of proceeding of the workshop. Okay. So now without further delay, let me introduce our keynote speaker today. It's our honor to have Dr. Arianne Hinds from CableLabs to give the keynote today. So She is currently a principal architect at CableLabs, and she's kind of video and immersive experience. That's VR, AR, MR, subject matter expert. And so she's going to tell us about a little bit about the CableLabs, what's their mission, and so we'll hear from her about that. So, so essentially, this is her main responsibility is to help CableLabs members develop their roadmaps for deploying new services for immersive media and technologies. She's currently the U.S. Impact Chair, as I understand. And she got her master and PhD degrees in computer science at the University of Colorado Boulder in 2000 and 2007, respectively. Okay, let's hear from Dr. Hinds.
Okay. So I use, this one. Does it work? Okay, it works. So good morning, and thank you for the nice introduction. I was telling Jiang that this is my first time to Budapest, and it's so beautiful, and I'm sorry, I've only been here I have to leave to go back tomorrow morning, so I have to come back sometime. But so getting back to the introduction, Jung said that I work at CableLabs, and my role is primarily to do research about things that might be emerging in the technology space that are potentially our cable members could be delivering as new services. So what I'm going to be talking about this morning is maybe not so much the deep dive focus on AR and VR. What I want to share with you is more about what's coming next after AR, VR. And believe it or not, it's actually not that far away, and hence the title of my talk, The Near Future of Immersive Experiences. And so as Zhang mentioned, I really welcome you to raise your hand and ask questions if you have any in the while I'm up here. And all right, so let's get going. All right, so one way I would like for us to consider AR and VR is that it is actually a small step in a larger picture. So we need to step back a little bit and think about how did we get to AR and VR? And if you think about all of the visual technologies that have been that preceded AR and VR, you start to see that, like, even 125 years ago, there was the camera, right? And then that was followed by movies, and then that was followed by TV, and then of course, digital cinema, digital television, HD, UHD, and now we've come to AR and VR. And so you can see there's this really rich evolution of the visual technologies over the last century or more. And so now we are here with AR and VR, and again, I ask you, do you think that this is the end of, considering all the evolution of the visual technologies, do you think AR and VR is the end? Okay, so I happen to know that it is not the end. There is a next step, and actually the next step seems pretty impossible, but I've seen it, it's real, and that's part of the reason why at CableLabs we call this the near future. So let me tell you a little bit more about this journey. I want to talk about, like, summarizing it, and you can see that there's this pressure or desire in the human society to get to even more immersive technologies. And you'll understand, as I did, that what we're going to take as far as our next steps is really what I consider to be inevitable. So let's move on. So I'm going to just tell you a short story that helps me to understand what it is that's coming after AR and VR and why it is so inevitable. And also, I think that what's coming after AR and VR is really far more natural as far as how human beings consume visual information. So let's get to that. Okay, so this short story begins with a conference that I was at 16 months ago in April 2017. And I was really excited to be there. In fact, this is taken from me sitting in the front row because I was just so excited because the gentleman who's at the podium at this conference is John Carafin. And he was there to make the very first announcement that he had just launched a new startup company in the Silicon Valley called Lightfield Lab. Okay. So I just used this really interesting term, light field. Does anybody know what a light field is? Okay, so-so. Okay, well, so I'll give a little bit of background on that. All right, so getting back to the conference, once John had finished talking, I knew exactly what I had to do because I work for CableLabs, and as I said, I'm trying to keep an eye out for things that are new and exciting that might impact our members. And so when John was finished talking, I made my way through the crowd towards John, and I literally walked up to him and I uttered the words that I think pretty much everybody says when they're greeting somebody they hardly know for the first time. And so here's what I said. Oh, see, I didn't even advance it. I'm sorry, I'm so not used to this. Okay, here's what I said to John. So that's me on the left and that's John on the right. And I said, I want to support the delivery of light fields over cable networks. So that's what I said to him. And he, being the one who's now starting this company to develop light field displays, he said, okay, yeah, sounds like a good idea. So, and so that's how my adventure began with light fields and how now CableLabs is aiming to deliver light fields over cable networks. Okay, so getting back to what John was talking about, the mission of Lightfield Lab is to create a display that will deliver real-life holograms. Okay, like real holograms that would be indistinguishable from real life without the need for any headgear and without the threat of motion sickness and without the threat of nausea. And so real life holograms that also could be viewed by more than one person. So we're getting back to the importance of a social experience. And so that, you can imagine, would mean that you and your friends could see the real life holograms together at the same time. So I think that's really cool. And and now I need to do the caveat, because I told you I work for CableLabs and we are a not-for-profit company. So that means that I cannot be endorsing any one product, but what I am allowed to do is share with you new information that has the potential to disrupt an entire industry. And so that's really what I'm doing here, is I want you to think about it as I'm telling you about this new technology that I think is going to be important and will be disruptive. And so, and it's just as another existence proof. There is another company called Fovi 3D, and it's being led by Thomas Burnett, and both his company and Lightfield Lab are working on light field displays. And they actually have prototypes, and each are focusing on optimizing for slightly different visual experiences. But nevertheless, we have to consider that these do serve as existence proofs, and that there's a lot of work towards getting this type of experience delivered. So, all right, so I told you I work for CableLabs, and here's a short video. The sound is not working. Okay. Okay, so how do I get the video to work? I mean, not the video, the audio. It was working? Oh, sorry. Yeah, yeah. Okay.
Our role is to provide the innovation and technologies that allow our members to be the provider of choice in the markets they serve. And the way we do this is we focus on research and development, which is in the 0 to 3 year time frame, and innovation, which is 3 to 8 years out. This allows us to create a very robust funnel that allows our members to deliver those next great breakthrough products and services that their customers are expecting. We are served by 200 employees, both here in Colorado, but also in our Silicon Valley office, and staff around the world. And with that capability, we're able to serve a very robust set of products and technologies, both from wireless to video to security to ultimately broadband services.
Okay, so that was just a little bit about CableLabs. So I'm, as Zhang mentioned, I'm one of their subject matter experts for immersive technologies. And as CEO, by the way, the CEO that was in our video clip there, he explained that we're a not-for-profit research lab. We're headquartered just outside of Boulder, Colorado. And actually, we have now 60 member companies that fund our work worldwide. We have members on every continent except for Antarctica and Africa. Okay, so I just wanted to share a little bit about who CableLabs is. All right, so now getting back to this evolution of visual media, and where I think AR and VR form a small but integral part in this evolution. I want to do a short recap on what has happened with visual media over the last, let's say, 125 years or so. And as I go through that review, I would challenge you to keep in mind this one fun fact, which is that 90% of the information that the human brain receives comes from the human visual system. So not only is the visual communication essential for the continuing development of the human race, but it requires the largest amount of data. And we've all heard that the visual data is taking up the bulk of the available bandwidth for the internet. And now you know why. So I just want to compare that a little bit. You know, sharks, they use their sense of smell to, as their primary sense, and bats use hearing, and humans use their eyes. So it makes sense that the internet would be consumed with a lot of visual content. And so looking at the evolution of all that visual content, here are some of the formats, and you'll notice that every single one of these formats listed here has a standard, a standard that allows us to understand what's in the format and how it's been constructed so that it can be widely used. Okay, AR, VR, still no standards, right? Still very fragmented. And, okay, so let's go back at the very beginning. There was a photograph, which was soon followed by movies, first silent and then talking. And then television eclipsed the radio as a form of communication in the 1950s. And we started with black and white. And then we went to color. And then we went from analog to digital. We went from standard def to high def. We went from interlace to progressive scan, HD to ultra HD. Ultra HD, as some of you know, is also called 4K. And from there, we went from standard dynamic range to high dynamic range, which allowed us to improve the contrast between the darkest darks and the brightest whites. And we dramatically increased the number of colors that could be delivered with wide color gamut over the older legacy standard color gamut. High frame rate eliminated motion blur, and but to be honest, it remains to be seen how high of a frame rate really is consistent with how the human visual system wants to see the information. It's been shown in a couple of cases that high frame rate actually makes us uncomfortable. And yeah, I think that's true. And we've also suffered with the transition from rectilinear 2D video to stereoscopic 3D video. And then thankfully, we abandoned that idea and went back to regular 2D video. So that, like, just a quick summary, over 125 years, this is where we're at now in terms of media formats. And then the question is, how do you distribute that media format? Okay, so this is also a problem for AR and VR. But going back to how we started delivering visual multimedia, we started with terrestrial broadcasts, and then, okay, so everybody knows terrestrial broadcast is just beaming the signal from a tower, right? And buildings get in the way, hills get in the way, valleys create problems, and so that's why we had the cable network. And from the cable network, we started, there became another form of distribution with the satellite dish. Satellite television. And of course, JPEG and MPEG were important distribution formats for that. And the HTTP protocol, which was emerging on the internet, gave us the ability to distribute all of that data over the mobile and ubiquitous internet. And of course, now there's Wi-Fi and broadband, so you can imagine we've got all these distribution formats, and it's very important for, you know, to deliver the visual content and have lots of ways to do so. Not so much yet with AR and VR. Okay, so I want to also talk about, so I talked about the media formats and the distribution, but now I want to drill down a little bit into the content and the displays. And you can see that, you know, things are evolving, right? Starting with the photograph and the JPEG a long time ago, things are becoming more rich in terms of how much information are presented, and they're also becoming more immersive. And so I think that it's important to think about this. I mean, what are we trying to achieve as a human race, right? I think the answer is that we want to see the visual content in a way that is immersive and natural, right? That's what we've been after. That's this carrot we've been chasing for a long time. And then part of that is what motivating this evolution of content in the displays. I mean, it was obvious that the transition from color to black and white was really compelling because color is how we see the real world, right? And analog to digital gave us the ability to deliver higher quality signals. The transition from HD to SD increased the sharpness of the picture. The introduction of the widescreen versus full screen gave us more resolution. And progressive gave us progressive over interlace gave us smoother motion. But that's all relatively low-hanging fruit, right? Those were all pretty easy transitions. Now we're coming to the AR and the VR and AI, and the next steps are a lot more challenging. So not so low-hanging fruit. It's getting harder now, right, to make the displays and the content be even more immersive, right? I mean, AR and VR are at the point where it's a challenge to get the content to be more like how the human visual system wants to receive the content. And so some of the not so low-hanging fruit was, you know, high dynamic range, high frame rate, wide color gamut, ultra high definition, increased pixel depth, artificial intelligence. By the way, I was at one of the big box stores a couple of weeks ago, and you won't believe it, but there was a big widescreen display for sale that was labeled with having AI. I'm not sure why the widescreen TVs need AI right now. I mean, obviously that's going to be an important feature in next generation displays, maybe in AR and VR, but now flat screen displays, I'm not so sure. So all these things, you know, have really complicated where we are right now with displays. And I mean, high dynamic range, there must be half a dozen standards for high dynamic range. And high frame rate, I'm not really sure if the human visual system is really going to notice 120 versus 240 frames per second. So, so all of this is getting to be very difficult manage and to distribute, right? And to create a format and make it so that everybody can receive this content. So I think we're starting to run out of ideas for how we can improve the 2D video experience. Because I think as a human society, we really want to consume data that even more matches how we see the real world in natural environments. And so that's why I think it's really getting more difficult. Some people will maintain that the next big step is to keep increasing resolution, right? I mean, think about it. We went from HD to UHD, and now people are talking about 8K. So do we really think it's going to make a difference to keep increasing the resolution? I'm not so sure. So yeah, so let's just take a quick step into that transition because it is getting complicated and it's even getting a little bit worse because now we're talking about going to 8K. The issue is that if you have, in general, a UHD display can do a really good job of upscaling HD content, right? If you have a 4K display and you send it an HD signal and it's upscaling to 4K, are you gonna notice a difference between that signal, the result of the upscale versus a native 4K signal? And we've done experiments at CableLabs and it shows people can't tell the difference. So, and the same will go, I'm assuming the same will go from UHD to 8K, right? Are we really gonna be providing even more immersive experience with 8K? I mean, it really depends on the size of your television, right? And how close you're sitting to the television. Because it's really not, at least for 4K, it's not really made much of a difference in terms of the quality of the viewing experience. I don't know, does everybody, probably I've said something that everybody disagrees with. No? Okay. So, I mean, a closer look as to why. I mean, obviously, the viewing distance really matters, right? If you're going to be sitting really close to the screen, then that's going to make a difference as to the resolution and the size of the display. Most of the average viewers, as I said, cannot tell the difference, and we're contemplating 8K. But I think where 8K is going to make a difference is on the head-mounted displays, right? But let's think about that. On the head-mounted displays, the head-mounted display is sitting on the bridge of your nose. I mean, can it get any closer? I mean, now it's really going to matter, right, that it's 8K, because you want to avoid the screen door effect. And with the head-mounted displays, as you all know, you can also create a more immersive experience by allowing the user to control the viewport, right? If it's a mouse or if you've got the headset on, you can turn your head. And has anybody ever tried this where you can turn your head from left to right, and that's called the yaw, right? And you can go up and down, and the experience still works pretty good, and that's called the pitch. But if you go like this or like this, it's not going to work so well. Okay, what you're going to get is not what the brain would normally experience in real life by the tilting of your head. And so that's a point where now the content is not providing the signal that the human brain really wants to receive. And that is one of the reasons why support of visual cues is very important. Because when you don't support the visual cues with the content in the display, then you're delivering a signal that isn't matching what the human visual system wants, and you can have motion sickness, right, and nausea. So I talk a little bit about these visual cues. The really important visual cues are horizontal parallax, you know, so the scene changes when you're moving horizontally, and vertical parallax and motion parallax. So motion parallax means that as objects are moving, the objects that are in the foreground of the scene should move faster across our field of view than the objects in the background of the scene. And then occlusions. So when object A moves in front of object B, object A should obscure object B, and because that's how it works in the real world. So the experience with 360-degree media and head-mounted displays obviously does not support all those visual cues. And to make matters worse, we have generally gone backwards because we've gone backwards in the sense that the head-mounted displays are using the old stereoscopic 2D video trick, right? Trying to create 3D with stereoscopic video. I mean, that's basically the 3D experience now on your head. So I hate to be such a wet blanket, but I for one, I'm just not able to tolerate the head-mounted displays for very long. And then the social implications, well, with at least the head-mounted displays, you're isolated entirely, and it's really a single-person experience. There's no way to meaningfully interact with others. So I challenge you to put the head-mounted display on and try to kiss your significant other. It's just not going to work, right? Okay, so that's kind of, I know that doesn't, it sounds a little bit down on VR, and I'm not trying to say VR is a waste. I think VR is a natural stepping stone. As I said, we're on this journey, and we're wanting to get to a point where we have able to experience content like we do see it in the real world, and VR is obviously a step in that direction, as is AR. You know, AR is, it could also be a single user experience, right? You've got the Magic Leap just came out last month after, what, 4 years of high secrecy and $1.5 billion of startup cash. But it really remains to be seen how well that is going to be adopted, right? And what is the market that's going to emerge? Although AR, I think, addresses more use cases than VR, right? There's a lot of opportunities there for personalized advertising. But you must be able to support this 6 DOF content. So 6 degrees of freedom. Are you all familiar with 6 degrees of freedom? Roll, pitch, and yaw, and then translation, right? So that's XYZ moving around, and then roll, pitch, and yaw like an airplane. So for AR, you need to have content that will provide all 6 degrees of freedom. Otherwise, it's going to end up being really cartoonish and I don't know, maybe not that compelling. So, as I said, there's been a long evolution of visual media and visual technologies. And again, we are at the point of AR and VR. But what I do think is really important for us to understand is that the next step is really not all that far away. And I've already hinted at what the next step is, and that is what I'm working on very heavily at CableLabs. My whole life is right now devoted to this area of research, and that is the light field. Okay, so some of you said you weren't 100% sure what a light field is. And a light field is, you can think of it as a volume of light rays, which can be modeled by this thing called the planoptic function. And so this is the planoptic function. You've got your X, Y, and Z to describe where you are in the space. And you've got theta and rho, which describes the direction at which the light is traveling. You've got lambda to describe the wavelength, and you've got tau to describe time. So it's a very rich function, and it does a good job of modeling the flow of light. And of course, with light, you need a source, right? There's no flow of light if there's no sun. There's no flow of light if you don't have some kind of synthetic generator of light like the light bulb. And what's really important about a light field is that these rays, they travel through space, right? Or they travel through the room, and the rays of light will hit a surface of an object. And the surface properties, the properties of that surface determines what's going to happen to those rays, right? They're either going to be reflected or refracted, or they're going to be absorbed. And so the question is, can we actually recreate this experience? And as I said, there is evidence that companies are producing real displays that are able to produce a hologram, and it's a real, it's not a cartoonish hologram. It's a hologram that models the way that light travels through our eyes. And so, what are some of the more important things? You want to have really dense, a number of rays per degree. You want to, and if you have a real light-filled display, it'll support the whole 6 degrees of freedom, right? You can move in the volume of the light, and your eyes will be focusing on the objects as if you were really there, as if they were really there. You can support motion parallax, vertical parallax, occlusions, and I think this is the way that we want to experience visual content, and that this is why it's a very important next step for us on this visual journey. So how does this work? It actually, what it's doing is it's producing collimated rays of light that converge at a certain point in front of the display. So these points collectively form an image, and if you're in the volume of the light, you will see the image just like if it's really there. Now, of course, like I said, it's really important to have a very dense pixel rays per degree. It's very important to have sufficient number of rays per degree. And the display that I've seen does achieve a very dense rays per degree. So here's an example of the prototype. It really exists. It's got 16,000, the equivalent of 16,000 pixels in the horizontal direction and 10,000 pixels in the vertical direction, and yet it's only a 6x4 display. So that tells you how dense the pixels are, right? 16,000 columns, 10,000 rows, and it's only a little 4x6 display. I mean, that's probably a pretty dense display. And so I've seen this. The way it works, is it produces a viewing, a cone, right? And if you're in the cone, you see the objects coming off the display like you would in real life. And it's amazing, amazing technology. And of course, it scales, right? So if you can build a bigger display, the idea that for this particular product, this is Lightfield Lab, of course, they're going to build square panels. And if you put the square panels, you can fuse them together and they can operate as a single display. And if you then cover your wall with them, then you've got a whole video wall. You can put them on the ceiling. You can put them on the floor. You can walk on them. So you know where I'm going with this, right? I hope you figured it out that I really believe we're heading towards this holodeck experience, right? The old Star Trek idea that you could walk into a room and experience all these visuals as if you were really there in the scene in the real time. And so that is what they're shooting for. And that is what we're going to be delivering over the cable networks. That's what we're starting to work on. So I think that's pretty cool. And I think that is really where we want to go as a human society, right? We want to be experiencing visual information in a way that is consistent with how the brain receives the information. So, what is missing? We have a lot of work left to do, you can imagine. Some of the things that are yet to be done, we need a media distribution format. So VR and AR, right? There's no standard for how you create that content. And Hollywood's struggling with the storytelling and all that. I mean, for light field displays, we're not going to be supporting light field displays in the cable network until we have a for sure agreed upon standard for how to represent that information. And we actually do have that technology. It was created by a company called Otoy, and I will tell you that what it's doing, it's leveraging all of the, it's leveraging several of the tools that are used in the visual effects industry, right? Because Hollywood's already figured out how to make photorealistic content with synthetic data. And that's what we're going to be using for light field displays. It's not 2D video. 2D video, I think it's you know, I think we've reached the point where we've done what we can with 2D video to make it really immersive. We need something else, and that's what this is going to be delivering. So, yes, we have a media distribution format. CableLabs is working on the spec. We want to, share that. We are planning to share that with everybody else. But first, we just want to make sure we get it right. So that's what I'm working on. I'm helping to write the spec. Let's see, what else? No. So where will you first see this new technology? It will be coming out in the next, let's say, 2 years. And it'll start with location-based entertainment, mostly in like theme parks, shopping malls, signage. You want to start where your customers know they have access to the power that they'll need, and they have access to the compute resources. So you want to start with a really well-defined environment, and that's why you'll see this technology deployed in location-based entertainment first. And then as that is being explored and customers become more familiar with it, the idea is that the content producers will start to realize that they need to be producing content to support this type of display in the home. So you're not gonna see these displays in the home until there's sufficient content, right? With VR, the whole technology was deployed with only, 500 hours of content? Okay, you really need content. And so, what is cool about these use cases for immersive media, well, it turns out you can take existing content and make it, it's a lot of compute that needs to happen, but you can repurpose existing content to work on these light field displays. You can also create interactive content, right? So games with a light field display, that would be pretty cool. And you can use it for training, and it'd be great for education. And in fact, that's one of the visions that CableLabs has with respect to this new technology in education. We have a video that I want to share with you right now that actually gives you the idea of how we see the future.
Dragonflies have been around for 300 million years. I just learned that. Whoa. Us kids have minds like sponges. We're just waiting to soak up everything around us. We're naturally curious and love to dive in and figure out how things work. After all, it's what we're best at. You know, a true sign of intelligence is not knowledge, but imagination. I didn't say that. Albert did. Follow me. Of course, you can't see imagination, but you can see what happens when it's let out. You can explore anywhere you want. It'll take you places you only ever dreamed of. And help you meet new people from all over the world. Where do you live? Like my best friend Alice. She's from Australia. I think it's pretty early there, so she's probably sleeping.
Sydney, Australia is 19 hours ahead of San Francisco, California. Local
that. My teacher, Mrs. Garcia, says it's good to take everything at your own speed. And don't be afraid to get things wrong once in a while. After all, mistakes are proof that you're trying. She says sometimes it just takes a little time before it all makes sense. I feel that way when it comes to math. But I am getting better though. I've still got loads to learn and ways to go, because it takes a long time to get educated. That's cool. But I know that one day I'll be here, working, maybe even in a place like this. I don't really know what I want to be when I grow up. Perhaps that job doesn't even exist yet. Mrs. Garcia says that learning never really stops, because life never stops teaching. That works for me, because I'll never want to stop learning. I mean, why would you? No one knows what the world will really look like when I grow up. Definitely something more amazing than we've even got now. No matter what though, I know that when it's my turn to help make the world work, I'll be ready.
Hey, Millie.
Hi, Mom.
Hi, sweetie. How was school today?
Awesome. Did you know that dragonflies have been around for 300 million years?
I guess you learn something new every day.
I know.
So that was our CableLabs vision piece, and you saw at the end the light field table, right? They were doing experiments, moving the objects around in the light field table. That's also something that I know is coming. And the holodeck experience where they were working on the bicycle at the end, again, part of this light field design. So I think that wraps up my talk. I do want to say thank you to John Carafin, who is the CEO of Lightfield Lab. He provided some of the slides in this presentation, so I want to thank him. And if there's time, I'm not really sure what time it is. If there's time for some questions, I'd be happy to take some. Okay.
Yeah, we do have some time for like some questions. Any question from the audience? So,
Yeah.
So she raised her hand first.
Mine is actually more of a social versus technical. Already, the kids are not reading. So I thought to myself, watching this, like, okay, now there's even less excuse to read. And in the end, when it comes to research and fundamental real thinking, you need pen to the paper and reading paper. That's the only concern I have with some of this.
Yeah.
And I recognize, because I have 3 boys, and some of them are more visual learners.
Sure.
But
well, I have 3 boys as well. And believe me, I have my youngest one who spends most of his time on the video games. And I do think, though, reading is, of course, it's going to remain a fundamental part of how we learn. And I think, though, that the light field tables and the holodeck experience just really supplements that, right? And makes it more real for them. This will never replace reading. Nothing will replace reading. And I think that we can't even pretend that we want to replace reading. And the same with AR and VR, right? They're not going to replace reading. But that I'm a mother too, so yes, I totally get that. Reading is fundamental. So, your question?
Hi. Very interesting. So I've never heard of this, so it's an exposure for me. I'm wondering, from my, I thought hologram is basically you don't have a display, right? You sort of see some projection. So I still don't quite understand what this is all about. I mean, you still project something onto a 2D space, and so I'm still, I mean, it seems very exciting, but I'm still not quite sure exactly. I mean, you showed us the function that it seems to suggest that you are maybe creating the image based on the light from, as a direction of light as well as your position and so on. But in the end, I mean, how do you compare to, existing video? What was the difference? It seems not so clear to me.
Okay.
And also, could you, I mean, you mentioned something from the video that you showed us that, something illustrate this new technology, but could you sort of just walk through that a little bit and talk, point us to what we should pay attention to? Because afterwards you mentioned, oh, did you notice this and
okay.
that? I mean, I just totally don't know what you're talking about, right?
Okay, no, those are all good questions. So let me start with, I think your first question is, how's it working and how's it different from what we have today, right? And so what we have today is, most people think of a hologram as something that is playing back the interference pattern of lasers. That's how you, a lot of people think of the hologram, right? But really what that is using the interference pattern of lasers is one way for how to create the hologram. It's just one way to do it, to create this holographic effect, right? And the holographic effect is to have the radiance image be recreated floating in space. And so the light field display does the same thing with recreating the image floating in space in front of the display. Because what it's doing is different from lasers. It's able to refine and direct individual rays of light. So red, green, and blue together, when they converge at a certain point in front of the display, creates a point that's a certain color, right? Because red, green, and blue are what all the colors our eyes can see. So it's able to recreate all the colors that the eyes can see, and it's able to redirect the rays of light to a certain point in front of the display that creates like a cone of light in front of the display. So if you're in the area of where the light is, the cone of the display, then you see all those rays of light converging to form images that are making real objects in front of the display. Does that make sense? Oh, yeah. Okay. Yeah. I showed it to you, and then I said, oh, and did you notice? Yeah. Okay, so let's see if I can get back to that. Okay, so here's where she's walking into what will be the holodeck, right? You can see all the individual panels. And here's the table. This is another one of the form factors that I think we're going to be really interesting for the light field display. It's projecting the light up, and also it's also producing a cone, right? And if you're looking into the cone, you see the images. Now, of course, it doesn't make sense that, okay, I'll use this as a model. It doesn't make sense that you're going to be like this over the table, right? So there's really not much use for the rays going straight up. They're going to want to project outwards. So I think this is how we're going to be, this is going to be great for viewing sports. A football game, you can be around the table and watch the players. Okay, now, I like football. Oh, I think it'll be exciting. So, are there more questions? Yeah.
Yeah. Well, first of all, going back to the games, and I only have 2 kids, so I'm lagging behind you guys. But when I show them this, they hopefully will stop playing Fortnite and look forward to playing Fortnite with the light display. I mean, this would be really cool compared to what they do now. The real question that I have is that most of the applications in the video and what you started talking at the beginning seem to be location-based. I think that's what you call them, where the source and the processing and everything is local.
Yeah.
So my question is two questions. One, or really one, in terms of resources. You mentioned about compute resources and the need to, I guess, process something so that the display gets done. That's one. What are the resources needed? Not only in terms of compute, but in terms of transmission.
Mm-hmm.
If I was actually doing this, if I was going to do a holodeck in my house, right, so that my kids could play Fortnite, what would I need? I mean, can I still do it in the cable network? Will I need a dedicated media like a cable or a fiber or something? Can I stream it across the internet? What are we going to need to do these things?
So those are awesome questions because that's what we're working on, right? We're trying to make it so that these experiences can be delivered. And of course, we're starting with cable, but there's not any reason why it can't be other platforms. Although I will say mobile, I don't know if a holodeck makes sense with a mobile, right? Because it's not a moving experience. So I think it's going to make sense to start with cable. But you asked about the compute resources. So these particular displays have, like, you could think of them as a display with a game engine bolted on the back. Okay, and so what we want to send is the equivalent of the data that a game engine would use to create the experience. So now, John, the person that is developing these displays right now, is probably the better one to answer the question about how much compute does it take. But he's telling me that I don't need to have all the cable subscribers have a nuclear power plant down the road. Okay, he's telling me that this is within bounds of what would be consumed by a regular in-home display. So, go ahead.
The Media Lab has been sending flight field information since 1988, and they were creating light field displays since 1988 with the PCs of then, and then transmitting it. So yes, you don't need to have your cable subscribers
have a nuclear power plant
that's
down.
it, yeah. It's been done. Maybe not with the quality that these people are looking at, but if they've transmitted, again, light field functions for quite a long time.
Yeah.
And so I think it's within the feasible.
So, but the other question is, like, okay, how are we going to get the media there? And that's what I'm working on with the network architecture. Is, again, the media is not 2D video, right? That makes sense. It's because we want to create a volumetric experience. So starting with 2D video is not where we want to be. So what we're going to be leveraging are technologies that are already being used in the VFX industry, you know, the visual effects industry. You know, Hollywood already has a lot of these tools. And we have a particular media format that is supported by a lot of the VFX tools, and it's been contributed to CableLabs as a royalty-free technology. And so we're going to be using that as a starting point to describe what is the media that needs to be going through the cable networks. And then our members, like the cable operators, we'll have to have more edge compute. We'll have to have improved networks in terms of low latency, and it is a higher bandwidth. All right, it's not like let's say the first form factor for in-home display is like an 85-inch diagonal display, and that's one form factor that I know Lightfield Lab is targeting. And roughly, you could think of that display as needing like 1.5 gigabits with this new media format being delivered over, you know, a high-speed link from cable, and so.
So when you say 1.5 gigabits, that's already compressed, or
yes, yeah.
Okay.
And I think you can understand that there's naturally going to be more data, right? It's a much bigger visual experience than a 2D video. And, but unlike 2D video, it will support the full 6 degrees of freedom. And so everybody knows what the 6 degrees of freedom is, right? So 2D video, getting back to your question, does not support 6 degrees of freedom. Everything, when you have a 2D video, you've captured it with a certain camera resolution at a certain angle with a certain amount of light. And you can't change that, right? Whereas with a light field, if you've got a good description of the surface properties, which is all what comes out of the visual effects industry, we can leverage those technologies and be able to create the much more real-life experience for the light field display. Yes?
Thank you. So connected to what you just mentioned, so where the media comes from. So I think one important question, or one interesting question, could also be the whole architecture of the system, and so the, say, business models that this entails. For example, so when I use like my light field application, or my say rendering system, do I have to connect to the, say, pipe that comes from Disney or Fox or whatever, like give me their wonderful content? Or could this also be a more, say, distributed application where the rendering and the light field generation is maybe done locally, consuming, say, resources, say, from different providers? So like the web today, where I also, can build, say, pages or, say, impressions by just connecting existing resources. Are you also looking into these architecture business model questions?
So yes, okay, so we want to start with the basics, right? This is an entire new display technology, and we want to make sure that everybody can have one of these in their home, let's say. So if you think about how at least a cable operator works, the cable operator is aggregating a lot of content from Fox, from Disney, from ESPN, and it's allowing you to switch, select what you want to watch, right? So that's kind of how I think about it as the very first basic rollout of the service, that we will be collecting these new forms of media that will be able to be selected from your home, and you'll have it, it'll be just like a TV. So that's how I think it'll work. Your question?
So today you have, SD, HD, 4K that you can order, subscribe to, right? Mm-hmm. On the Comcast and so forth of the world. So that stream, is it cached in all those individual forms in some CDN, and then you can stream it? I mean, especially if you do on demand, or is it really streamed from some beginning, whatever, and all the way through the network and all the bandwidth and so forth? And then I would assume then this is similar. It's just another.
Yeah. It's just now streaming light field data.
Yeah, but so the question is, where is the image or the SD, HD, and so where is it stored? I assume it's not streaming all the way from the, the source, because of course that's very expensive from a bandwidth point of view. I assume it's downloaded in some sort of cache.
Okay. So yeah, there's the difference of what like
one's on demand and one is live.
Exactly.
So what is the architecture where the information is stored when it's on demand and when it's live? So for on demand, the architecture is the same, right? For existing services for HD, UHD, you have a mezzanine. Are you familiar with the term mezzanine? So a mezzanine is like a really rich representation of the 2D video. And we bring that into the cable network, and then, everybody does this. And they start with the mezzanine, and then they say, oh, well, my client needs HD, or my client needs SD, or my client needs UHD.
So from the mezzanine spec, the proper format is created, put into the cache, and then it's served out, okay? So that's how it works today with on-demand.
So wait, so there's like one image and then it gets converted to all these other different...
Yeah. We ingest a really rich format of 2D video content.
I see. And then you narrow it down to whatever.
Yeah. And the idea will be
but wait, so is it, so you have the, I mean, I know I'm asking, because actually a research person asked me this, and I was like, I don't remember this stuff. So wait, so you have that in some cache location, and then when I, as a subscriber, say I want HD, then it gets converted in that cache area to whatever my...
Yeah, somewhere in the network, in the cloud,
see,
right?
yeah.
It gets, and actually, I mean...
But this is very different, though, right?
I'm sorry.
But this is very different. You can't just take, I mean, you wouldn't like store this high level one, and then if I just wanted to, you know, an SD version of it, because it's not immersive, then you can't just water it down, right?
Okay, well, no.
So I assume this one will have its own separate.
Yeah. Well, okay,
whatever.
so what's really cool about this new form of content, it is so rich that it could also be used as a source to flatten.
So you could convert it to an SD and an HD?
Yeah. So we will have this really rich 3D representation of the media, and we can flatten it to serve to a 2D SD display, or you could flatten it to serve an HD display, or you could keep it in its rich format to bring to a light field display.
I see. So it's going to do very similar to what we do today. It's just now this will be the richer one.
Yeah.
And then when you do on-demand, I'm not on-demand, when you do live streaming...
That's tricky.
Yeah, I mean, that's too much bandwidth.
Well, well, the bandwidth exists, right? But it's, the question is...
Pay for it.
I'm sorry?
I don't think anyone wants to pay for all that, right? If you have I mean, I'm going to the next level. If you have a lot of different channels or whatever that all do this, you know, just so like today, right? You have all the 4K ones or whatever they are.
Yeah.
And so forth. You know, if you do streaming, I mean, well, I don't know how it all really works. So if you stream all the way from the originating place, all the way, and you don't cache it, and it's going down, I mean, that eats up a lot of bandwidth, especially if you, right? No? I mean, that's...
So
which is why you pay more for the higher, I assume, one of the reasons.
Well,
maybe it's marketing.
You know, so like let's say we're talking about the Super Bowl, right? That's something that's happening in real time, and people aren't going to want to wait until the next day to watch it, right? So there's already a really rich infrastructure to support that kind of sporting events and news, for example. To get the content all the way from the venue into the home as quickly as possible. So we're going to leverage that, but of course it's just going to need more bandwidth. But they already have a lot of bandwidth. I mean, the football stadiums have an enormous amount of fiber. And so, I mean, we're not going to start with the sporting events, right? We're going to start with first the basics, right? We're going to be on demand only for, you know, crawl, walk, run. And I do believe that we will get to that point where the football stadiums and the soccer fields will have all that bandwidth to support this new type of media. Okay.
For this video, what's the camera look like? Do you need sort of camera all over the...
Yeah, that's another good question. So there are, I think the lady from MIT, you're from MIT or? Okay, so there's already been a lot of research and development in these new light field cameras, but really the best way to, I think, create it is to use a camera array. And that's a whole new field, but it's been, you know, Hollywood's already using it. So they already use light field cameras.
Okay, I think there are lots of interest here, and also I'm convinced we should work on night field networking next year. So let's give Arianne another round of applause. And so you will be around a bit, or so I guess maybe during the break she can also answer your questions. So now, I guess we are not going to have a break. We're going to get into the paper session right now. So I will ask the speaker of the next paper to come up. Thank you, Anne. That's very nice. You want me to introduce yourself? Sure, I can do that. Okay. Yeah, sure. So we're going to have two papers on AR, and so I'm going to kind of a lazy session chair. I will ask the speaker to introduce herself. Go ahead. I think so.
Okay. Hi, my name is Surin. I just finished my undergrad at Princeton, and I'll be starting my PhD in electrical engineering at Stanford in just a few weeks, actually. So this is my summer break. So I'll be talking about some work that I did in collaboration with some postdocs and also professors at both Princeton and Purdue University. So I think everyone in this room is very well aware that AR is really emerging in a lot of different forms. The Keynote did a wonderful job of really illustrating this. So at the most basic level, we have sort of the mobile space, but also, Microsoft and other companies have been developing these much more immersive head-mounted displays, or HMDs. And there are also peripherals that can kind of transform your smartphone into an HMD. And kind of looking more into the future, car companies like Toyota and BMW are even looking at how AR functionality can be built into the windshields of vehicles. So imagine as you're driving through sort of a busy city and passing by a bunch of restaurants, you see like Yelp reviews overlaid directly onto those restaurants as you're driving past them. So there are a lot of really exciting possible future directions there. There's also, applications for just visualization in general for different collaborative projects and also for military situations. And I think a lot of different countries are already beginning to adopt AR for their training. But sort of putting on more of a Black Mirror type of lens, and I think we also need to think about ways in which AR can be potentially very distracting or also very dangerous. So there are a lot of potential security concerns. So imagine, wearing AR-enabled headsets or even, glasses, contact lenses, and, what if you're kind of using this in your everyday life? And there are all these different applications kind of competing for your visual attention. So on the left is sort of a visual illustration what that might actually look like. Going back to the vehicle windshield example, what if you're driving and there's like a pedestrian crossing the road in front of you, or there's other vehicles driving in front of you, and an application that you're using either intentionally or unintentionally displays a hologram in such a way that these elements are blocked from your view. So that could be, really potentially very catastrophic, and I guess it gives new meaning to the term killer apps. I'll give a quick overview of some of the past work in AR security and privacy. Most of the work has actually focused on input privacy, so that's looking to make sure that third parties like cloud services and other applications aren't actually seeing too much of your data. And these different AR devices really have a wide array of different sensors, and not only that, but they're collecting information about how you yourself are interacting with your environment. So there's really a rich set of data to kind of protect. However, there's been very little research on what's called output security, so that's a little bit different. But so not only should we prevent these third parties from seeing too much about your environment, but also we should make sure that we regulate what these third parties are displaying to the user and make sure that this output is safe and also fair. So we don't want apps sort of intentionally obscuring other apps just to kind of hog your visual space. That's the focus of this talk, and in particular, so our group kind of looked at how do we come up with adaptive security solutions for output security. So adaptive means that depending on the environment that the user is in, we should sort of have a different security policy that kind of fits well with the environment. So mainly we're building off of ARIA, which is a system that was built at University of Washington just last year. So ARIA defines sort of a set of rule-based policies, and it's kind of like a table of sort of like match action pairs, like in routing, I guess. But basically, ARIA will kind of analyze your environment, analyze where the holograms are in your environment, and kind of check a bunch of conditions. If any of those conditions are violated, then ARIA will kind of take a set of actions to try and mitigate potential security concerns. So as just a very simple example, if a hologram X is too close to the user, so it's like blocking the user's view, then ARIA will make X transparent. So that's sort of the main action that it takes, is making these objects transparent. It'll also kind of limit the speed at which they can move across the display. So they kind of implemented these simulations to illustrate what ARIA does. And so you can see, like, if you're driving and there are a bunch of sort of cowboy pedestrians in front of you, there's some advertisements being displayed and mail applications. So ARIA will produce this kind of filtered output. And basically you can see these rules, these policies in action. The advertisements kind of disappear, and also the email app disappeared. And now the user can really see the important real-world information. Based on this, we kind of had two key observations. The first one is that, notice on the right, the user can no longer really benefit from any of these apps. They can no longer see their email or the advertisements, so really a lot of the utility is lost. Secondly, you can kind of imagine that if you define a set of rules or a set of policies for one environment, that might not actually generalize well to a lot of different environments. So we kind of need to consider how these policies can actually adapt depending on the environmental conditions. So what we proposed is, on top of sort of this transparency action that you can take on holograms, what if we can actually kind of move holograms around and change their configuration so that the user can still benefit from them, but that they're in sort of a less maybe distracting or obstructive position. So here's a person standing in front of you, maybe a pedestrian. They can be covered up by a bunch of apps. And what we're saying instead is, can we sort of just move them out of the way so the user can still benefit from using these applications, but now they can see the pedestrians? And so you might be thinking at first, is there a way for us to actually define these kind of manual or heuristic-based policies to kind of perform this task? But imagine there are tens or hundreds of different objects, and there are also a lot of moving pedestrians, moving vehicles, a lot of dynamic stuff happening in the environment. It's kind of a non-trivial idea of how you actually move these holograms so that they both don't interfere with each other and also don't interfere with real-world information. So it's a lot of complicated things to think about. So a natural next question to ask is, can we have a computer kind of automatically generate these types of security policies that we want, depending on the environment? So we looked into using reinforcement learning, in particular, a particular family of RL algorithms called policy optimization algorithms, and these have been becoming sort of really popular in the robotics AI community, but we're kind of seeing ways in which it can really benefit AR as well. So just at a high level, the way that our system works is you have this autonomous agent sort of learn through trial and error by interacting with a simulated environment that kind of randomizes the dynamics of the real world objects and also different holograms. So it kind of tries taking different actions on the environment, receives a kind of reward in return, and through this kind of feedback cycle, it eventually learns a security policy that fits well for that simulated environment. And so in our work, we used deep reinforcement learning. So that basically just means you kind of have a neural network representation of a policy. In the input layer, you have like the state of the environment that's observed by the agent, and the output layer tells you what action you should take to improve the security of the system. So the idea is these policies you should be able to actually deploy directly in the display module of an AR device, and we're kind of seeing already how this can be feasible because the next version of, say, the Microsoft HoloLens is going to have a dedicated processor just for AI functions and basically just implementing different neural networks. So what policy optimization is it tries to solve sort of this optimization problem that tries to maximize the expected cumulative reward of the agent. So you have this parameter vector theta that kind of defines your policy. And for example, in neural networks, this can be like the set of weights and biases that you have in your net. So that's kind of your optimization space. So basically you want to maximize this cumulative, this sum here over some time horizon, and the agent wants to maximize over some notion of reward, which I'll talk about in a little bit. There are a bunch of methods that have been proposed to actually solve these kinds of optimization problems. Most typically, you kind of find an estimator of this objective function, an estimator of the gradient, and then that can allow you to kind of solve this problem. So as I mentioned before, there's a neural network representation of the policy where you have this input layer that represents the state. So somehow you have to kind of quantify your state and kind of encode it into this vector. Goes through a bunch of hidden layers, and then in the output layer you should get some sort of also an encoding of an action that you should take on the holograms to improve the security. So I'll go over sort of how we actually define this AR security problem as a reinforcement learning problem. So first, the states are sort of the configuration of the real world objects and also the holograms that are trying to be displayed by the applications. So basically it's just a way to quantify what's in your environment at a given time. The actions that you can actually take are moving the holograms, so either changing their sort of location in the environment, their rotation, also their transparency, as the ARIA system did. But we actually tell the agent how well it's accomplishing this task, the security task, by giving it a positive reward if it's increasing the visibility of real world objects. So that's kind of like rewarding it for improving the security. But you can imagine if we only have sort of this positive reward, one thing that it can figure out is, oh, what if I just get rid of the holograms altogether? That maximizes the objective function, right? So we kind of need a balancing force to prevent that. And so we also kind of provide a penalty saying, don't move the holograms too far from their original position, so keep them relatively close to where they were originally. That also kind of keeps the applications happy because I would assume they wouldn't want too much tampering to happen, of their holograms. So more specifically, our reward function looks like this. It's a little bit difficult to look at, but I'll go into each part. So this first part is what I mentioned about the positive reward, where you kind of want to increase the visibility of real-world objects, so kind of maximize the XY plane distance between the real objects and the modified AR objects or holograms. So also this Z-plane difference, you want to maximize, or rather, you want to make sure that the modified holograms are not actually blocking the real-world objects. This last component goes into that balancing force that I talked about, where you want to sort of also minimize the distance between the modified holograms and their original positions. So these constants, alpha, beta, gamma, are just tuning parameters that kind of adjust the importance or the weights of these different components. So I just want to point out that this is only one example of a reward function that you can use. There are potentially, infinite other rewards that you can use. They're each likely to kind of result in different policies and different behaviors, but we found this one to work pretty well. So I'll talk briefly about where the computation actually happens. That goes into a tiny bit of sort of fog computing and edge computing. So we kind of envision these different distributed fog servers or edge nodes. This was kind of mentioned in the keynote earlier. That are kind of geographically distributed, and you have different AR devices that are kind of moving in this environment, and those that are within the vicinity of a given fog server can maybe benefit from these computational resources. Sort of more along the lines of our own approach, the fog server can maybe perform these simulations themselves kind of offline. So it performs these simulations, produces the policies, and then in the next phase, if there are devices nearby, they can actually distribute these policies. So the devices can download policies and run it themselves, or if they're more sort of resource poor devices, maybe they can kind of send their state to the fog server and receive an action in return. So this really kind of helps to mitigate maybe some of the potential latency and bandwidth issues that we talked about. So I'll go into some kind of preliminary experimental results that we collected. We built an AR simulator similar to the one that I showed in the ARIA system. And what's important to note is that this is both the experimental test bed, so it allowed us to kind of collect results about our method, but also it's the training environment itself. So I mentioned that the FOG server maybe performs these simulations offline and produces the policies that way. And this notion of sim to real transfer, so the idea that you produce the policies in simulation and then transfer it to the real world, has been gaining a lot of traction in robotics. So I'll go over some other metrics that we collected, comparisons, and also a user study. So we built the AR simulations in the Unity game engine, so most typically it's used to make games, but here we used for AR, and we used it with a new toolkit, which is called the ML Agents SDK, and also TensorFlow, and a new policy gradient method called proximal policy optimization. So here's an example of what that looks like. So it's kind of similar to the earlier example I showed you in ARIA, where the left side shows kind of the unfiltered output. So you can't really see anything. The user's view is completely blocked by these kind of simulated holograms. The policy that we generated with our approach kind of produces this filtered output where the user can now see sort of the important sign that's directly in front of them, but also kind of benefit from these different holograms, which may represent, applications. These adaptive policies also we can easily compose with other policies to kind of offer more sophisticated security measures. So you can imagine that when we're using these types of machine learning approaches, there maybe are some potential mistakes that can be made. So to kind of safeguard against that, we can include the transparency policy that ARIA used. So in this example, our policy decided it wanted to place those two holograms sort of in the front there. And if they were opaque, then you can imagine it would kind of block some important things. So adding that transparency policy on top of that kind of allows us to merge our strengths of this RL-generated policy with sort of the existing approach of increasing the transparency. We also tried it with some kind of moving dynamic objects, so these might represent pedestrians, and then our policy is able to kind of adaptively move around these holograms to improve the security there. This is just a quick demo video, very simple, showing example of one hologram. So on the left is the red one is the unfiltered one, and then the green one shows the filtered output. And notice that their trajectories remain pretty similar, but yeah, the agent kind of figures out how to adjust the trajectory such that it doesn't kind of block that sign anymore. Okay. So how do we actually know that these policies are kind of converging and actually working and the agent is really maximizing its rewards? So we kind of plotted the cumulative reward as a function of the number of training steps. So you can see it kind of increases very quickly and then kind of plateaus in that very familiar kind of pattern of convergence. In terms of how long it actually takes to train, for these very simple, sparse environments that I showed, it took only 2 or 3 minutes to train, and you can imagine as you scale up the number of objects or the complexity of the state space, that time might increase. And looking at frame rate, if we include the policy, then the frame rate is degraded slightly compared to if you don't use a policy at all. But even as you scale up the number of objects, the frame rate remains well above 60 frames per second, which is a very smooth experience. And we came up with a couple of sort of novel metrics to figure out whether our policies are actually doing better compared to the baselines. So the blue line is if you don't have any policy whatsoever. The yellow line is the transparency policy, so basically essentially what ARIA would use. And the red line is our own reinforcement learning policy. So what this is showing is something that we call obstruction, which is the percentage of the user's display that's being actually obstructed by holograms. So you can see that our policy does improve in that respect. Kind of the trade-off, though, is that since you're moving holograms further away from their original positions. They're kind of further separated from where the applications originally intended to place them. So we also defined sort of the separation metric, which is kind of a weighted average of like the transparency difference and also the kind of location difference. And you can see, there's slightly higher separation, but it's a trade-off between how much security you want and how sort of close you want to keep it to the original configuration. Finally, I'll go over just a user study that we did. There are 9 people. We showed them these kinds of pairs of images where you have the unfiltered and filtered outputs. In this case, on the left, we showed them these sort of ARIA-generated outputs. So they would sometimes be transparent if that's what ARIA decided to do. And then the right side showed our reinforcement learning policy. They rated these statements from 1 to 5. So the first one basically says, users found that the apps generated by our policies were less obstructive, so they could sort of see more elements of the real-world environment compared to the ARIA image. On top of that, they were more useful. So not only were they sort of improving the security, but also the utility of these apps. And they all kind of agreed that the RL-generated images they preferred compared to the ARIA images. So just to sum up the talk, I think everyone is really excited about AR, and it's sort of the next big computing platform, but we also need to start thinking about potential security concerns. So we propose using reinforcement learning to kind of produce these adaptive policies that can kind of move holograms around and decide sort of the best course of action to improve security depending on the environment. I went over some results that show sort of promising potential of this approach. So there's good convergence, frame rate, user approval, and it improves this obstruction metric. And we're sort of working on some new things. In particular, one paper that we have under submission relates to sort of the last bullet point. So we're looking into how we can actually use machine learning, not only to improve the security, but also kind of to personalize these AR experiences and learn from user preferences where they might actually want holograms to be placed. So I'll just acknowledge some funding sources. They're shown here. And thank you very much for your attention.
We have some time for a couple of questions.
Yeah, thanks. Super interesting, and I think also super relevant. So, how far do you think one could take this? So right now, I mean, you are maybe selecting or repositioning holograms in real time. So do you think in the future you could also, do more, say deeper manipulations of the reality that, are actually not holograms, but you could maybe manipulate what the user sees without actually, as a detectable hologram, but you could lead him to think there is something in front of him or something.
So are you asking about like what the adversary could potentially do? Or,
for example, what do you think is the technology potential in doing this in real time? So do you think that's...
So that's a really interesting question. So I guess first of all, in our approach, we mainly looked at sort of the exact position of holograms. So another thing you could look at is sort of the rotation. That's another important element. But also, we're only looking at kind of visual elements in this paper, but AR could potentially include other types of actuators, like haptic feedback. You could have audio. Those are two things that could potentially also kind of disturb the user in several ways. So I think looking at other mediums would be really interesting too.
Hi, very, very interesting work. It looks like when you're repositioning, you're mostly looking at what is blocking my view and putting it somewhere else. Have you looked at, and I was just thinking about this as you were showing that, as I'm driving down the road, there may be things that if you move out of my way and put them somewhere else, they're not relevant anymore. The first example that you gave of the Yelp review of the restaurant, well, if it's showing over there, sure, it doesn't obstruct my view, but it doesn't tell me anything, right? It's not relevant anymore to the object that was the restaurant in front of me, right? And the other thing that I was thinking is, have you thought about that? You know, repositioning things that actually make sense repositioning.
Right.
Like,
right,
you know,
yeah.
I got mail, okay, it's okay if it's over there because, you know, it's not relevant to the position of the screen. But then the other thing was about time, about relevancy in time. So it's okay for me to wait another 5 minutes to know that I got an email when I'm driving, for example. So maybe not just moving it out of the way, but showing it to me later, right? In terms of deciding what do you move out of the way, what do you show now, what do you show later? Just have you looked into that, or maybe there's something else, maybe in the last bullet that you show there, or other work that you're doing later, where you're actually learning my preferences?
Right, so I think that's a really good example of where incorporating the user preferences would be super important. Maybe sort of there could be a settings page when they're first setting up their device where they can kind of specify these things, or they can provide like explicit feedback, which could kind of serve as like a training set, and you can do some machine learning on that. So that's a really good point. The first thing that you mentioned was also a good point, that maybe you don't want to position holograms in terms of like the global coordinate system. So actually, that is something that we thought about sort of in the research process, and we kind of decided later on that these states should be represented according to the user's local coordinate system. So the policies are learned according to sort of the user's view and where they are. So it's not just a fixed point in the world, it's sort of according to their own experience.
Okay, so I also have one question for you then.
Okay, yeah.
So I guess you are talking about you are doing this kind of training offline in a way. So how often do you update that training? So do you just train it once, or just?
Right, so that kind of goes back to the idea of using different fog servers to perform the training. So I guess we assume each fog server is kind of responsible for a small kind of geographical space, and maybe that fog server knows something about the context of the environment, so they can incorporate maybe statistics about the environment that it knows, maybe using different kind of sensors that are around the city. It can kind of collect visual information about that. So the idea is that these fog servers can have very detailed simulations about the environment, and I'm not sure exactly how often it should be updated. Maybe there can be some kind of analytics detecting like when there's been like a sufficiently large change in dynamics of the environment, and
so basically your assumption is that the policies are mostly location-based, right? So if you change the location, you should change to different set of optimal policy. But even in the same location, over time, you should also update your policy.
Exactly.
That's
yeah, exactly. Yeah.
Okay, so let's thank the speaker.
Thank you.
Take your time. Well, normally it takes a second. Okay. Let me just switch there. All right. I'm Dirk Kutscher. I'm a senior technical director at Huawei, Germany. Actually, this is not work done by me, so I take no credit for this work. This is work done by Lemuel, Jeff Burke, and Zhang at UCLA. Unfortunately, Lemuel had last-minute visa issues, so they asked me to present. So again, it's their work. I know it fairly well, so that's why they asked me to do it. So often when we, so I'm a networking researcher. Often when we, as networking researcher, think about what can we do to support AR in the network, we often think about, we have to build better pipes to increase the performance, get the latency down. We have to maybe optimize, the efficiency of perhaps virtual machine platforms at the edge, or these kind of things. So what I want you to take away from this talk is that, well, there are actually a number of additional important, say, requirements or like, issues that you have to look into. So if you were to kind of realize the, say, maybe more pervasive or universal vision of AR. In general, I don't think I have to tell you what AR is, but it's quite, useful to just remind us, about, say important key concepts. So there's a really nice taxonomy paper by Gruber and all on describing, really the key ideas of, say, different AR conceptions. And so he describes it as a continuous, omnipresent, and universal augmented interface to information in the physical world. Okay, so, sounds familiar, but what this really means is, when I live my daily life, I move from like one context to the other, like from this meeting room to a restaurant or to a boat tour here on the river. And basically, I have AR support around me, giving me the adequate, say, information for the different context. It's always there. It's universal, so I can rely on it everywhere. But also everybody, can rely on it everywhere. And so we are now starting, to see like the first implementations of AR apps that can run on your mobile device. So mostly for shopping or some personal vanity things. Here on the left-hand side, you see like an airport navigator concept, just similar to what we just heard. So like bringing you useful information, advertisements perhaps, and in one, say, consistent display. But so if you look at these, initial apps, so these are essentially point solutions. So they are, developed totally, independent. They're not sharing any technology. They're not sharing any, say, assets or something. So right now we're seeing like we basically have silos of different AR apps, and it's difficult to leverage resources like in the web today, for example. And so performance is certainly a key requirement. We know that. But so here in this talk, I want to explain that you also have to look into say questions like how do I actually interact with the physical world, and maybe sensor information or cues that I get from the local environment. So how do I discover resources, potentially also compute resources that could help me in rendering something, and what was also kind of important in the previous talk, how can I actually trust what I'm presenting to a user? So potentially I want to connect to say virtual assets or say information sources in an airport. How can I actually be sure that this is not an attack, but this is useful information, or so the rendered say image is actually something trustworthy? And then finally also, so how does the ecosystem in the end really look like? Is this something sort of like AR that the big corporations control, or do we actually, remind ourselves how the internet, successfully grew by essentially enabling permissionless innovation, so a rich set of, competing applications and so on. So, so you can see there are really quite interesting additional questions to just the performance. So, and so this team here is looking at AR, so from a, say, broader architecture, but also networking perspective. And so they are using so their version of information-centric networking called named data networking, NDN. To experiment like with new concepts for AR. And so one notion that is important is indeed context. So in order to do something useful, we normally assume that AR apps need context data. So for example, from the, say, environment, to give me the, say, helping or useful information. So this could be like spatial-temporal information at location and time, but also, of course, cues from the smart city or the building or whatever. And so as I mentioned, so we really want to be able to know exactly what we're getting and so whether we can actually trust that information. And so if I walk around in this pervasive computing environment, well, I don't want to necessarily rely on, for example, Google or another centralized provider to authorize my communication or to give me the list of available resources. I want to be able to detect or discover this myself and establish communication relationships myself. And so this idea of provisioning local resources and processing this context locally, this is currently really difficult to achieve. And so the question here is, how can we do this? How would the, say, business models and also the ecosystem look like? Today, as I mentioned, when we build AR applications, so we often use it, like, of course, with the technology that we know. So TCP/IP, web protocols, say VM, edge compute technology. This basically leads to a model where we kind of use connections, so to cloud service, for example, where the applications typically reside. And so it's kind of a, pipe model, if you want. And so we discover resources in the cloud. And if we want to, say, inject some local resources, we have to, go to quite some extent to make this happen. So we have to, redirect traffic using DNS. We have to terminate TLS at the local proxy, for example. So these kind of things. So we kind of see that the network model kind of implies a certain way of building AR systems and applications that could also be quite limiting at some point. So typically today, when so we run, for example, the Google AR app or something, it's kind of using the centralized cloud at least to establish trust and giving me a list of resources and so on. So it's actually not really possible if I want to communicate with, say, like a building information system locally, so directly, to set up this communication relationship. And this is essentially the reason why we have these many vertically integrated apps, or these silos. And so one of the, say, activities that this team here is doing is kind of trying to think about the design of AR browsers in the future. So say more like general purpose, like web browsers today. So what would this require? How would the user control it? Switch between apps or context perhaps? And so what we don't want is that the, say, legacy network and security architecture constrains us so much in developing these new concepts. So here's an example. It's not, say, totally new to people who know AR, but it's kind of pointing at some important problems. So imagine you have Carlos and Sally here who want to meet up in the city. So Sally is in her car AR context. So we just saw the idea of presenting AR application in the windscreen, perhaps, and it's using that to find her way, perhaps, or her car gives her interesting additional information about advertisements. If they want to meet up in a big crowd, the smart city environment could actually help them to find each other. You would hope that the face recognition wouldn't be done by a central provider or even the government, but maybe just using local capabilities, local facilities. And so often we think about AR and networked AR is something that, is using the super well-engineered high-speed 5G or next-generation network. But what is if something goes wrong? So we cannot rely on the infrastructure anymore. So here the idea is perhaps there's an earthquake, one of the persons get buried under, building walls or something. So we still want the available infrastructure to work and maybe help the first responders to find them, to present, useful hints. So this is is motivating the fact that well, we have lots of resources in a smart city, but if we are requiring to access centralized servers and networks to use them, it would be kind of limiting. So for this idea of pervasive AR, we really need to kind of rethink the computing paradigms as well as the communication models and business models. And so these are not really, these questions are not really tied to network performance directly. So I can just make this a bit quicker. As I said, we really want to be able to leverage all the available resources, be able to trust them, and also use the best available compute service, for example, that helps me rendering my display, for example. And so in that sense, one important concept is of edge computing that could support this. So is of course performance. So we want to reduce latency. We say, okay, we move the rendering perhaps closer to the user. But another important, so latency, sensitivity is important, but another one is also like privacy or trust sensitivity. So of course, if I have a AR application that does face recognition, maybe it's actually not acceptable that this is done, somewhere in the cloud where I cannot control it or where I don't trust the system that does it. So maybe it's actually good if the video stream or the annotations in the AR video actually don't leave the local environment. And so these things are kind of difficult to realize with the, say, pipe and centralized communication model that we have today. And so what we have today, essentially, so of course, as we have seen in these first examples of apps, we are able to build AR applications, but many of these functions that I mentioned, so discovery, establishment trust, and so on, finding the right resources, the network cannot do much to support this. So we connect to a cloud, and then everything we do on this level has to be done on the application layer, and it's kind of done repeatedly for different applications again and again. And so in the NDN work here, so they're trying to leverage a new network design where they want to move away from the like TCP/IP model of communication. So in the, say, internet today, we are communicating from like one end host to the other. And so we are building something like essentially virtual circuits on top of that. So with TCP, TLS, and so on. So in the named data networking approach, the idea is, say, basically taking the next step in this direction, moving away from this, maybe telephony network-inspired approaches, by just making the network work on the abstraction that you access named data. So you don't really care as a host or as a user where the data comes from, but the data is named, secured, and the network kind of knows how to get it to you. And so this enables, say, a different function split, if you want, in the system. So we don't have this, clear separation between what applications can do and what the network can do, but we are kind of enabling the network to do more useful functions for applications. So we can ask for named data that makes sense to applications, and the network can then help us to find resources, find the, say, closest or best possible maybe most cost-efficient compute service, for example. And in that system, security is not done based on connection-oriented security, connection-based security, but we are securing the data itself. So the data is signed, can be encrypted, and so on. So that also means the, say, trust anchor does not come from the, say, connection endpoint. So I don't need to talk to the Google server. I can just get the data and, you know, validate the authenticity, and so it can come from a local cache, it can come from a local network environment. And so this enables a quite flexible way of dealing with communication. So you can enable things like multicast in a much more elegant way, because where you're not talking about connections and flows, it's just data is coming from different sources. And so the idea here is that this kind of network, so where the network supports the application better and so does not lead to this siloed way of communication, would also enable, say, a more competitive, more viable ecosystem in the end. And okay, so let me maybe, I said this already. So the naming concept in NDN is really to you know, yeah, move those application relevant names say to the network, so the network can also, you know, decide okay, I have like 2 or 3 ways to reach to this, you know, asset or compute service. I do dynamic load balancing in the networks, things that are also really hard today. And so that's an important concept. So often when people talk about these networks or ICN or NDN, they think, it's about caching. So that's not the case. So it's really, you know, about conceiving a different function split between applications and networks, and so enable a more distributed, more dynamic way of communication. Okay, so as I said, so in order to realize these, say, really pervasive and say also, you know, more dynamic AR use cases, we really have to think about other things than just performance. So resource discovery, most importantly, trust and security in my view, and also enabling these different new business models. So just as an example, resource discovery in IP. Today, I mean, we have things like, you know, so like Apple Talk or multicast, DSN, these kind of things. But so in, say, commercial networks, what we normally do is we do some tricks with DNS and then redirect traffic to some maybe CDN node or compute node or whatever. So this, of course, you know, is problematic because the name resolution, you know, yields an IP address that may only make sense in a certain network. If I'm thinking about multi-access or multi-homed systems, it's kind of nasty. And also, you really have to terminate the security association or the connection at a certain point. In NDN, so the idea is really that I don't really care about, you know, connection endpoints. I send requests for things I want to discover, and the network has forward information that gets my request there. And if I want to, you know, use the Google AR service, for example, and well, and it happens to be in the Google Cloud, okay, the network will get me there. If Google decides, okay, I run a local, you know, copy or proxy of that system, the application doesn't have to change, and no traffic needs to be intercepted and redirected. It's just, you know, forwarding in the network that enables this functionality automatically, if you want. And yeah, if I have, say, a richer, you know, application that requests resources from, you know, different providers, if I kind of need to reuse resources, the network can would cache them, and so I wouldn't need to, you know, retransmit all these things over and over again. how do we make what's time?
We can maybe wrap up in 2 or 3 minutes.
That sounds good. Security and trust, I think this is really going to be, say, the most important question in these, future networks. So you really have to think beyond, optimizing performance or building faster pipes. You really have to think about how can I enable local communication in a trustworthy manner. And so, of course, I mean, we understand how crypto works, but one question is also how manageable is it really? So if I, for example, in the NDN context, sign data or encrypt data, so if I do this on individual data objects, of course, there needs to be some support that automates this for the application and for the user. So this is one of the research activities of this group, to basically provide an infrastructure on top of this basic signing and encryption framework that allows me to build applications where I can specify, for example, different roles in an AR app, for example, and then do all the validation or the signing automatically. And yeah, as I mentioned before, and also we kind of discussed a bit in earlier talks, so one question is really how do we think that like the, say, AR-enabled internet would really look like? So would it be that only the, say, big corporations, like maybe social media today, would actually be able to provide AR experience? Or is it more something like we actually knew from the beginning of the internet, where we had a permissionless innovation system, and everybody, could provide applications, digital assets, but perhaps also compute resources that could be used to enhance performance or enhance local trust and privacy. So this is something where, so this group is kind of thinking, you really have to consider, say, network performance, but also network architecture, and figure out how this, affects the, say, the overall system ecosystem in the future. And so you really also want to have, experimentation facilities where we can try out new things in a local context without having to move to a totally different way of building networks or building applications in networks. Right, and so this is basically the focus of the, say, NDN AR work of this team. So to not only work on the networking aspects directly, but really do this experiments in these other directions. Okay, so wrapping up, so maybe I think I mentioned this. So wrapping up, we really should look beyond the, say, mere performance aspects, and so let's think about more how we can, motivate or move the computing community towards, say, also the other bigger questions. So how can we actually build AR systems that people would like to use, and where innovation is possible, and where we can have a high level of trust in the apps that we are using. And so the thesis here is that the current communication models, and also the ideas that people often discuss in like connection-oriented say implementations, are really constraining what we can do with the technology that is getting more available. And so edge computing is a particular enabler, of course, but if you do edge computing, say, in the traditional connection-oriented way, you are basically not able to leverage the full potential. So we are so advocating a more distributed, say, more flexible system, where also the user and maybe also the network can work together in a better way compared to what we have today. All right, that's it. Thank you. I'm happy to answer some questions.
So Indians, people have been working on this for a while, so similar like AR, VR, what's the killer app? Do you see, is this the killer app? Or do you see, to get NDN really off the ground? Or do you see it already starting to get off the ground?
Right, so I think, I mean, this applies to many, say, future network proposals in the past. I think it's a mistake to expect the existing, say, big players in the field to innovate fast in the space. Because, I mean, many of those, well, they have the existing business and so on. So what we are seeing now is that there are more and more startups that actually use this technology, maybe not exactly, you know, this one particular protocol, but the concept of accessing named data in the network, securing data, caching individual data objects, and so on. So this is used by you know, startups that build particular applications, and this is super exciting.
But is it like the IoT applications or an AR applications, or like is there a class of application?
Well, I think there are like maybe two classes. So one is indeed, say video-oriented applications, so video streaming also, especially video streaming that supports mobility and the capabilities of, say, like broadcast, multicast of layer 2 networks better. And the other class of application is perhaps more, say, like a distributed applications. So also in IoT, where I don't have the model that, well, I basically talk to a cloud server all the time, but I have more like local communication and you need to be able to trust things locally directly.
Other questions? Okay, so let's
Thank you.
thanks speaker again. And so now it's coffee and tea break. We'll come back at 11. And so I will have like what, 15 minutes. So the next session will be like on VR 360 video streaming. Okay, thank you.
call this a tactile.
So that is not much data, because that's what I was wondering. Like, it could be, you know, it depends on how it's created.
So
When
did you arrive? When did you arrive? Oh, okay.
then it won't be data heavy. Yeah, that's what I was wondering. How are you gonna? But today, don't they?
Oh, you're present?
This
Oh, okay.
one. Yeah, I was thinking.
I see.
You kept
Did
saying
you
no.
get a visa or something? Did you get a visa?
No, not visa problem. They're master students. They already
100G is already.
Oh.
which is different than this. This is just their like coursework.
Oh, I
So
see.
they couldn't persuade them to come and present.
I see, I see.
Their new life.
Oh, okay, sure. They already graduated, right?
Yeah.
Okay, I see.
Well, this, if you really need a lot of memory, yes, you need objects.
So you're still advising PhD?
You can see.
Resolution. No.
You want to
So what do you see as, so
Oh, okay.
let's say you
Actually,
have.
enjoy life now.
So they're gonna do the algorithm there.
Yeah, right.
So then what gets.
They still work on some like
Comcast,
360 video streams.
No, the stuff I work on now, they more,
is that,
less.
that's formulated regularly. Yeah. Okay, so yeah, what's that bandwidth? I don't know.
Okay. Yeah.
1 gig, 10 gig, 40 gig.
Okay. Yeah.
Still not graduate yet. There's one that's working on social networks.
Okay.
Should interns have the
What's there now?
Yeah.
If that cannot work, I can try another laptop.
Please.
the last piece of work is
Resolution is changed.
Gaming?
Yes, normally it won't like be that one.
Yeah, I think it's still. Yeah, I think Hanson was criticized recently a lot.
we think the problem is interesting.
Okay.
So it's not their job security.
Maybe the display
Oh.
I know, yeah.
Tens of millions of users and
Not like 10.
we can see the
if that cannot work, I can try another laptop. Do you think it's a good idea?
Here laptop.
So we are trying to go beyond just looking at but also try to figure out some maybe some way.
Beyond that,
Say
Is there any like social component, social factor when you start?
well, if we do it the traditional way, we have to
beyond 10G, and you're like, wow, that's a bigger.
to make sure that this person is the bigger one to what extent and how they behave with it.
Okay.
But we are
Just the history of fiber that.
that's a big undertaking. So we are trying to see if we can
I will try my friend's laptop.
Yeah, that's what I like. Okay. How many of your friends are dictators or kind of thing? Okay, so you.
Can you help me make sure this is working? I think this side. This is the old. Okay. Sorry, is this how come it's not appearing? What happened that it disappeared? I don't know what I did.
So HDMI maybe that. No, I don't think we need.
Did that ever get solved? Where they?
So you just came for this? You come for the?
Well, actually, I was here Monday because we had another workshop in the meet. Right, so we had people there to present. And in between, I go out a little bit because my family is here.
Oh, okay. Good.
How about you? If you're in tomorrow afternoon? Yeah, we'll do my tomorrow morning as well. It's good. I mean, I go to the Buddha castle. Yeah, right. Yeah. And also there's a fisherman's yeah, yes. Next camera. I think we should get started.
This is okay.
Okay, nice. Blue color is missing?
Yeah, the color is missing, but I don't know. All the blue colors cannot be shown in the screen. Also the orange one missing.
Orange one?
Yeah.
I think you should change the color deeper.
I think it should be okay because it's just background, right?
Yeah. Just background.
Yeah.
I'm not sure. Yeah, this one totally not the same one.
Yeah, I think it probably is hard for us to fix that or not. Yeah, hopefully, yeah, it will be fine. Looks like, yeah. Okay. Yeah, thank you.
And
Yeah,
Mung. We can, but it doesn't meet me.
这个蓝色你试一下这个。
Yeah, probably it's fine.
This is fine for me.
But mine looks strange.
I think just get the main message across. That's fine.
So,
Okay.
What happened? How come it's disappeared again?
Slides maybe. Slideshow?
Huh? What? It's already. How come it's not showing?
Then do the slideshow again. Then just do the slideshow.
Wow, it's back to the other one again.
Yeah, it's showing up there.
What happened to the color thing? Your
Maybe resolution.
You know, it's my laptop is the old one, so I don't know. Nowadays you have the mobile phone, you just don't need the laptop anymore.
Right.
It's just
Yeah. You have a USB.
I have USB. If there's one Okay. Oh, it's not advancing. And it's not advancing for some reason. Try later on because I cannot even fix this problem.
This is the frequency problem.
Can you give me a USB? I try my computer so whether it works.
Okay, is it? Okay. Because if you try again, maybe he needs to fix again. It worked before, and then somehow after we take it apart, it doesn't work. Okay.
I mean, you want to use this one, you can copy it to here.
You want to use this one? Okay, so let's get started. Right. So the kind of a third segment of this workshop is VR, and especially on 360 video streaming. We have three interesting papers, and the first one is actually from Chinese University, Hong Kong. I will let the speaker to introduce himself.
Okay. Okay, thanks, Yang. So this paper actually worked by two students I supervise, MSc students. So they finished the work, already went to their new jobs. So I have the honor to present for them. We also have an industry collaborator, so that explains there's quite a few authors here. The background is that in recent years, as we probably, people in the industry are of course very familiar with that the cameras nowadays, they are integrated with computer vision technology, software, so they can do a lot of things. And other than doing a panoramic video, VR, and all this, you can actually even create other effects, like removing certain things or adding things. Anyway, we are fortunate to collaborate with a startup company who is in the business of making these kind of cameras, and they actually have a product which won a consumer show award, which is shown here, and so they are quite advanced in this area. So we are trying to kind of work with them and try to study the problem of how to stream the 360-degree video in an efficient way and with good QoS. So the other background thing is that nowadays in computer networking, more people are looking at using machine learning, reinforcement learning, all these things to study how we can achieve better user experience and to have more performance in streaming. So one example, we actually read a paper from SIGCOMM last year. They used the machine learning to study, based on previous network conditions, try to study how you can improve the dash protocol to do streaming. So in our case, we're not studying that problem of how to adapt to the bandwidth, but we are more studying how to adapt to users' attention. Okay, so that is the focus for our work. But I think the problem is the same. It's just how to use data and to enhance the performance of the protocol. There are actually different approaches to this problem that we're studying. One is called the foveated streaming that are used in computer games, online games a lot. They actually don't do pre-computation. That in real time, they will, based on the user's attention, they will do encoding of the video in different ways to emphasize certain things. There's also this tile-based streaming, which is very popular. I think maybe later on there's some papers talk about this. The third approach is based on, so tile-based streaming is you do some offline pre-computation, organize the video into tiles, and maybe multiple copy for each tile, and then adapt to users' attention. Certain tiles you use high resolution, other tiles you use low resolution, and do some adaptation to network bandwidth and also users' attention. So the approach we are studying is based on this copy-based streaming. I don't know whether this is the right term, but we use this term. And basically, you create multiple copies of the video. Each copy, emphasize a particular point of view for users. So depending on the user's current focus, you will try to adapt the copy to give the best effect. So this copy-based approach, I think, is used by Facebook, by some industry people, but the tile-based approach is also very popular. So compared to the other approach, the copy-based approach, I think, requires considerably more storage because you're creating multiple copies of each of the video, so each frame. So you have to, I think, increase the storage, but it requires no computation in real time. In a sense, if you have a tile base, you still have to stitch things together. So there's some real-time computation. Also, this approach, potentially, it may have better quality. So this is one of the topics we are studying. So actually, our collaborator, implemented this already. They are kind of more ahead. The engineering-wise, they already implement this stuff. So we just, this is a recording of their streaming using their copy-based approach, and it kind of works. You can see that when the user attention is moving, and then they're rotating the view, giving you different copies to look at. So we actually just trying to formulate the problem as a systematically to study how to improve their strategy. Okay, so we actually haven't done too much. We just in the process of formulating this problem in a more systematic way to study it, rather than just taking the engineering approach. But engineering-wise, it's actually already exists, the implementation. So just a little bit background. What we're talking about is a video that is, a three-dimensional video, spherical, taken by, multiple cameras. So you have a, 360 3D video. Of course, for each copy, you are projecting the video into a 2D space. And there are different ways to do the projection. You can project like in the map, equal rectangular. Or you can use, this barrel approach and to project certain horizontal video, and then the two ends you can use less different representation. And then there's also a very popular one called the cube map. You treat the video as a cube, and then you can project the video with different resolution for different faces of the cube. And to make, there's also another version of cube map, because the cube map at the corners, then you tend to be, tend to be not so smooth. So there's one version of the cube map called the equal angle cube map, which is the approach that our collaborator used. So the other thing, after you do the projection, you can, apply this pixel mapping. So giving, different areas of the projection, different amount of pixels to make it clearer versus other areas less clear. So again, this is just a little background material. I'm not an expert here. I just explain some of these techniques, which may be very, sort of well understood by most of you. So for us to study this problem, we make some assumptions to simplify the problem. The one assumption which people criticize actually in the review is we just try to focus on adaptation to the user attention. So in this paper, we actually assumed the bandwidth is enough. Okay, so we're going to, given the 360 degrees video, we're going to just giving certain part of the video with high resolution and other parts with low resolution. And then after the encoding, the bandwidth is actually enough. So our problem is only to decide which copy to give to the user in a way that we can maximize the QoE. Okay, so maximize the user experience. So if we formulate this problem, so this allows us to focus on the problem of adapting to user attention rather than at the same time adapting to the bandwidth fluctuation. Okay, that would be a much more complicated problem. So in our problem here, we still have two problems, and we call it, one is called the switching algorithm. That is, you have multiple copies. Okay, different copies have different areas which are high resolution versus low resolution. And as the user's attention moving around, and you have to, the switching algorithm in real time has to decide, in a few seconds, what is the copy to stream to the user. Okay, so that is a switching problem. The other problem is the offline problem. That is, given the video, you have to decide, how many copies to create, and then maybe each copy you focus on which area that is high resolution, and so on. So I'll talk a little bit, mostly about the first problem, but a little bit about the second problem. So just quick summary of what we did, so you know what to take away from this talk. So basically, as I said, the whole thing already implemented. Okay, so our job is only trying to, formulate it as a problem. We can do some systematic evaluation. So what we did is we have to, formulate some objective, right? So for this purpose, we define a QoE function. Now, another criticism we got from the reviewers is, oh, your QoE function is not that good. Okay, so it's, but I think for our purpose, this is just, like a starting point. You create some QE function, and then you can use this to, to formulate it as a problem. You can apply reinforcement learning. You can apply machine learning to try to improve based on this QE function. But after that, if you found out that, you may gain some insight in this process, but if the result is not that good, then you can later on come back and revisit and kind of adjust your QE function. This is a point I will discuss at the end, okay? So the other thing we did was to, we did some measurement of the user attention trajectory. This is just, we actually used one measured trajectory for our study. And the third thing we did was to, once you have this user trajectory, how do you, visualize it or present it, okay, so that we can appreciate the result of the switching. So we have proposed a polar representation to visualize, which I think is interesting. We'll show later on. And then what we did is we compared the different strategies, and so you get some insight and how well different strategies. We just evaluate some obvious strategies. Okay, you can appreciate how well they work. We also did some simulation of for what-if scenarios. If you have more bandwidth versus less bandwidth, if the user move faster versus slower, and so on. So the QE measure we did, granted this is a very simple one, okay? So what we define is that what the user is looking at is focusing on one particular direction, okay, which is represented by just a Gaussian curve. And so there's a center of the focus, and then it spread out. And similarly, the encoding of each copy is also represented by this a similar curve, and I think it's the pixel density is the green curve. Okay, so you combine these two together, you get the QE. So if the curve completely covers the user's attention area, then the QE is 1. If it doesn't cover very well, then the QE tapers off a little bit. So the red one is the computer QE as you shift the user's center along the x-axis. Okay. So this figure shows the measured user attention. Okay. So the x-axis is time. Okay. So it's different frames, and the y-axis is the 360 degrees. So another thing I forgot to mention is that in this study, we just focus on the horizontal. Okay, we assume that the video is just 360 degrees horizontally. We kind of ignore the North Pole and the South Pole. So so if you look at this video, the user is kind of starting from time 0 is kind of moving around and then move back. So the y-axis is just the radio describing in the 360 degrees. So one problem with this representation is that it wrap around. You'll see that at about 1,000 frames that the user has reached 360 degrees and go back to 0 degrees. So it's kind of a discontinuity, not very nice. And so this is a problem. The other thing we have in this figure is the color. Okay, on the curve, the color actually represents the QE. Okay, so it goes from 0 to 1, right? So based on the QE definition. Now, the one idea we had is to use a different representation. This one avoids the wraparound. So basically, use a polar representation. The users again is moving around the attention around the 360 degrees, and now here, as time go on, the axis on the radius is time. Okay, as time go on, you're going to a bigger circles, and again, you can use a different color to represent the QE. So this representation avoids the wraparound problem. Okay, of course it also has some problem because you know, the distance is different. In the beginning, you know, it's small circles. As time go on, it goes on the bigger circles. So that part is also not so ideal. But it's an interesting alternative representation of the user attention over time. Okay, so I said in our study, we basically defined a QE function, and then we want to evaluate different strategies you can use to stream the video, to do the switching. So, so we use the 3 user attention trajectory. One is the measure one I showed you, and we also use 2 others. One is we call the scan trajectory. So this one is just the user just start from one point and just keep going in one direction, okay, at a certain speed. And we adjust the speed to be the same as average speed of the measured trajectory. So the third one is a random trajectory, which means that it's a random walk. The user starts at a certain point and keep going left or right randomly, again at a speed which is you know, sort of normalized to the speed of the measured trajectory. So these are the 3 kind of trajectory we used. We could, I mean, if we continue to do this studies problem, we should do more measurement. This is another feedback from the reviewers. You should look at more. I mean, we just measured one. We did more measurement, but in this study, we just used one measured trajectory. So the problem is with the switching is, you know, we are assuming that there's a certain delay. Basically, you know, you are streaming a particular copy which covers a certain area with high resolution, and you are trying to predict, you know, at the delta t later, what is the user's attention and determine whether you should switch to a different copy. So that is the problem. So the problem, the challenge is that, you know, when you want to switch to a different copy, it takes a little time before you can accumulate enough video to have continuity. So the, you know, there's some details about how the other effects, you know, that can affect the delay. You know, for example, the videos, there are only certain point in the video, certain frames you can do the switching, not based on the encoding. So you can, so it's not, you can switch anywhere. And so this is the, but in our simulation, so what we did, what the student did is just to create a simulation environment. So it's based on a model. Okay, so in our model, simulation model, we actually, it's a little bit different than the real situation. We assume a constant delay. Okay, we have to, you know, to start to determine the new copy. Okay, to use the new copy. So so this I think I already explained what the stream switching algorithm is trying to do. So now for the switching algorithm, actually we evaluated several different ones. One switching algorithm is we just assume, you know, whatever you are looking at currently is we don't predict anything. You basically, you know, unless we detect the user is looking at something different, we assume delta t later the users continue to look at the same thing. The second strategy is we call simple Markov estimator strategy. That is, we assume you know, whatever the direction the user has been moving in the past, he will, you know, with the Markov probability that he will continue moving in the same direction, you know, a certain small amount. Of course, this is random, so it could also change direction and go the other direction. Okay, so this is a simple Markov model of the user behavior. The third one is we actually try to look at the user's attention movement, the speed of that. So if it moves very fast, okay? And then we will predict it will continue to move very fast in the same direction. So that is the third strategy. And of course, the fourth strategy is offline. You assume that you know exactly what the user is looking at. So we compare the result of these four different strategies. So this, for the simulation, basically you, we simulate the three cases. One is the measured user attention trajectory, one is the scanning trajectory, and the last one is the random, okay? And then we assume the very first frame, you just randomly pick a frame because you don't even know where the user is looking at, and then you try to use switching to adapt. And then we assume the certain ratio for the available bandwidth versus the playback rate. Okay, so the playback rate is less than the available bandwidth. Okay, so that's the assumption. So this is the result basically for the measured trajectory. This is the first one. Okay, this is the real one for a particular video. The simulation result is here we actually go back to using the first representation. We didn't use the polar representation, okay, but this is more convenient to represent, to show the switching strategy what copy we are using. So each bar there is, depending on, there are 4 levels which correspond to the 4 different copies. So if it's the bar at around 50, that is the first copy, and then at 100 something, that's the next copy, and so on. And then I think the green one represents the offline best copy to use. And the red one is actually the copy, the switching strategy picked to use. Okay, you can see from this figure that the switching strategy didn't always pick the best copy, and sometimes it's grossly wrong, and then you will have very poor QoE, which is shown in the bottom figure. Okay, for the scan trajectory, you can see it's the same thing, but because it's more regular, so the performance actually turned out to be, it's easier, it's to adapt, and performance is better, and there's just a certain delay. There's no, mistake in terms of picking a wrong copy. And this is the random trajectory. In this case, again, you have some wrong copies are picked occasionally, so the switching is not doing as good. So this is a comparison of the different strategies we looked at. The columns are the different trajectories. The first one is a measured one, and then the scan and the random. And the rows are the different strategies we evaluated. The baseline is, of course, not so good. And then the Markov improved the baseline a little bit, not too, not too much. Of course, we didn't, we haven't done the machine learning trying to optimize the Markov strategy. We just assume a very simple-minded Markov strategy. The distance-based one actually improved the baseline quite a bit. Okay, so and the distance-based one actually is the one that our collaborator implemented, and so they actually did a reasonable job. And so the last row is the offline optimal strategy. So this is just some discussion of the simulation results. The scan trajectory. So different trajectories pose different challenge to the switching strategy, and the scan trajectory is the easiest one for the switching the strategy. So the performance also came out to be better. And the random trajectory and the real measured one, they are similar, but in fact, the real user trajectory also is quite challenging for the switching strategy. Okay, so this is
the result we saw. And the other thing we did was we asked some, we changed, adjusted some parameters to see how things get, whether improve things or not. So one thing we adjusted is the ratio of the playback rate versus the bandwidth. So we can make the playback rate very close to the bandwidth. So when we get too close, we don't get time to change copies. Okay, so we may have to just not switch. And the x-axis represent the ratio between the bandwidth with the playback rate. So when it is 1, that means they are the same. You cannot afford to switch. Now when it's 1.3 in the other extreme, that means you have quite a bit of extra bandwidth to allow you to switch. So in that case, the QoE is very close to 1. Actually, you're doing very well. But as the bandwidth and the playback rate get closer and closer, the QoE actually start to drop quite fast. But the interesting thing is, after a while, when the bandwidth is so close to playback rate, you cannot afford to switch. The performance is slightly better than switching. So it's saying that actually, when you're doing switching, if you don't switch smartly, you can have worse performance. This is not, this is showing that we haven't done enough work to make the switching algorithm as good as it could be. Okay. So the other thing is we also changed the user's attention, the speed of user attention movement. Again, the same result happens. If the user started moving too fast, yeah, okay. So let me just get to next. So the other thing we look at is the segmentation. And again, we actually found, again, some negative result. That is, when this figure shows that as we increase the number of copies, I expected we should do better in QoE. It turns out that we did worse. So again, it shows that you have to be very careful with the switching in order to take advantage of the increased number of copies. But here is a positive result. That is, if you know where the heat map of the user attention, okay, you can design your segmentation to have the copy sort of align more with where the user is looking at. And that you can help improve the QoE quite a lot. You can see that the two figures, the left one is the one that has a lot of blue, which means good QoE, and it's when we align the heat map with the copy design. Okay, so that's so the conclusion is that we, in this work, we try to formulate the smart switching problem, and we did some work, but we've also found out that there's some surprising results, and that is the switching is a hard problem. If you are not doing a good job, you could make performance even worse. We also, the other thing is, after this work, we realized that we probably need to continue to adjust the QoE function. One thing is, in the QoE function, we don't have considered the smoothness. That is, although you may, at any moment, you want to go to the best QoE definition, but because if you change too much, it's also not good for the user. So in future, we may incorporate the smoothness also into the QoE. So I stop here, okay? Any questions? Thank you for your attention. Yeah.
For one or two quick questions. So actually, you show some curve about the bandwidth and the playback rate ratio. So yeah. I didn't quite understand. So let's say if the ratio is 1, you don't allow users to change the direction? Or what?
Yeah, if the ratio is 1, then if you switch, then you don't have time to buffer, and then so basically switching stops actually when the bandwidth is too close in our implementation, in simulation. So that yeah, that's how the evaluation was done.
So you're doing kind of VOD, right? You allow prefetching, right? So
Yeah.
in principle, right? So if you allow prefetching, even if the ratio is 1, you can still do it, right? So
yeah, you have to do it beforehand. Yeah, but
right.
but switching means that you are doing it following the user's attention. If you don't have extra bandwidth,
I see.
You cannot switch, right?
Yeah.
So.
And also, I think I saw in your kind of the first batch of results, you have, let's say, 4 copies, right? They are long overlapping. So
right, they are not overlapping. As we increase the number of copies, I expected to do better.
Right.
So actually, that result is kind of a negative result. I think it shows that, I think that this problem is a little bit similar to the multipath TCP, right? We listened to some talks about multipath TCP. It is, in terms of the idea, it's very good. But if you don't do it carefully, multipath TCP can make things worse because you can oscillate. And during oscillation, the performance actually get worse.
Yeah,
so this is a kind of similar problem we find. So this is probably one of the useful takeaway from the.
I mean, I think it's definitely interesting because when you have overlapping copies, and you would expect when you switch, you'll be much smoother.
Yeah,
so
exactly.
The quality will be much better.
Exactly. So in this study, we haven't managed to take advantage of the increased number of copies. So that's negative results. Yeah.
Okay. So let's thank the speaker again.
Yeah. Thank you.
So you want to use your own laptop?
I'm not sure.
Let's give it a try, then I will see how it works.
Yeah, thank you.
Just wait a bit. That's it.
Oh, still cannot work. Still cannot work.
Why?
I mean.
It's okay. I think it's just do like this. I think we don't have time to adjust this.
Can I use yours?
Sure, you have USB.
Okay, thank you. USB is here. Yes. Yeah, and here is the USB.
No, you need to copy.
Yeah.
Whether it's better or not, from here. It's okay. Maybe the same. We'll see. Is better? Not the same? Let's go with this.
Okay. Thank you.
Okay. So why don't you just introduce yourself?
Sure.
Okay, so let's get started.
Hello everyone, I'm Xue. Today I will talk about predicting the head motion in 360-degree and VR experiences. The title of our work is the predictive view generation to enable mobile 360-degree and VR experiences. This is a joint work with my advisor, Sujit Jianzhong Zhang, and Madhukar Budagavi from Samsung Research America. Today, more and more people enjoy using the head-mounted display. We also call it as HMD to experience the VR world. However, as these two figures shows, the current sorry, but I cannot find my clicker. Yeah, here I cannot find it. Clicker, I should slide here. Yeah, I want to say this, but I cannot find the clicker. I need to say this.
You want to show this on the slides?
No, not just it.
Hmm?
Because I need to slide it down, but here I cannot find my clicker. Yes.
You cannot see what your...
Yeah, I think I should say it.
let me see. You want to what?
Yeah, because the slides show when I use the presenter viewers. Not.
No, just wait a bit. Oh, you see, you cannot see all the comments here?
Yes.
That's just a different version of...
Yeah, presenter view.
Yeah. Okay. So, let me see.
The clicker is not found.
Oh.
Yeah, can I use my... I don't know why.
So, can you just look at the slides and talk?
Because I have a lot of notice here.
Oh, okay.
Could you help me find the clicker, because now I cannot move the clicker.
Okay, just 1 minute. It's okay, take it easy. You want to do this present view, right? Okay, let me try it. Okay, let's just do it again here. No, she can't, just the font is different, I think, somehow. Let's try this, and same thing here, right?
Yeah, but I cannot. Could you move this to be released? Remove this?
No, you want to click this, something like this?
Yeah, but I should look beside it. Oh, yeah.
Just two fingers here. Oh, you can do it.
Yes.
Right? Okay, let's do it again here.
Thank you.
Just 2 fingers to do
Yes.
it.
Yeah, thank you.
Let's try it again here. Let's bring here, and you should be able to do it.
Yeah, thank you.
Okay, go ahead.
Yes.
So you have to use 2 fingers. 2 fingers together.
Okay.
And like this. Right?
Yes.
Like 2 fingers together.
Okay, thank you. Sorry for the waiting. Today, more and more people enjoy using the head-mounted display. We also call it as the HMD to experience the VR world. However, as these two figures show, current HMDs are far from perfect. For instance, some HMDs are rendering with the tethered PC, and thus they are not mobile. And some HMDs are rendering on the attached mobile device, making it quite clunky to wear. So how to make the HMD become wireless and lighter? One possible solution is shifting the computing tasks, including the rendering procedure, to the Azure cloud, and then streaming the videos to the HMD. Thus, Most computer tasks are achieved on the edge or cloud, and HMD can be wireless and lighter. We call this as cloud or edge-based solution. Here is an example for the cloud-based solution. The head motion as well as other controls will be transmitted from the users, then the field of view. We also call it as the FOV is rendering on the cloud. After that, we will transmit the rendered video to the VR glasses. However, here are some challenges of enabling the cloud or edge-based wireless VR. Since the VR HMD devices make the requirements of bandwidth as well as the latency steeper than cloud or edge-based video streaming. For example, in VR applications, user experience is much more sensitive to the video artifacts. This may lead to significantly higher video quality needed. Also, the head motion will significantly increase the latency sensitivity, and this may cause significantly higher frame rate and bit rate needed. Here we show the result of a simple experiment on virtual classroom and racing game. Here are three settings. The first is using the PC monitor, representing the cloud or edge-based video streaming situation. The second is using the Oculus and without the head motion. The third one is using the Oculus and with the head motion. In this table, we can see when users wear Oculus and have head motions, there is much more bandwidth consumed compared with other cases. When we use the 4K resolution for virtual classroom, it is around 70 megabits per second bandwidth consumed, and for racing game, it is around 100 megabits per second bandwidth consumed. Also, the latency requirement is much steeper compared with the cloud or edge-based video streaming, which is around 20 milliseconds to provide a good user experience when wearing the Oculus and have the head motions. This will be much smaller than acceptable latency when we watch the video in a PC monitor. Therefore, for the head motion, the cloud or edge-based wireless VR will require very high frame rate and bit rate, and also needs to satisfy ultra-low latency. To achieve ultra-low latency, here are some possible solutions. The high-level idea is that we can render and stream the 360-degree video instead of just stream the field of view. In this way, the user can obtain the needed view immediately when they have the head motion. However, if we choose to do in this way, as is shown in method 1, if we render 360-degree video on a cloud, there will be very high bandwidth consumed for streaming 360-degree video. Or in method 2, if we render the 360-degree video on the server, there are higher computation needed for rendering the whole 360-degree view. To further address the problem within the method 1 and 2, we propose to do a machine learning-based predicted pre-rendering. As these two figures show, our proposed method is to base on the head motion prediction, pre-render, and stream predicted FOV in advance from edge device. The advantages of this approach is we have no rendering or encoding delay, and we have minimal communication delay with significantly reduced bandwidth. Also, as figure A and B shows, the edge can be either RAN in figure A or a local edge or mobile device in figure B. Our approach of predictive FOV generation is implemented on MEC or LEC and then stream the video predicted view from the edge to the user. So now the most important question is for this solution is it possible to predict the head motion? We do a series of experiments to prove this point. We can predict the head motion by learning the head motion pattern from a relatively large data set. We use the data provided by Samsung and transfer the Euler coordinates to the coordinates in a rectangle using the equirectangular projection, and we want to address both bandwidth and latency challenges with the head motion prediction. As we mentioned, the common approach of streaming only the FOV still cannot address the latency problem, and thus we need to do the head motion prediction. We call our approach as predicted view generation, as these two figures show. Note that this procedure will be implemented on the edge server. In our predictive view generation approach, only predicted view is extracted for the 360-degree video cases or rendered in case of the VR applications and transmitted to the users in advance. Here is the system overview. Users will transmit the head motion data, and on the edge server, we will do the viewpoint prediction, where the viewpoint refers to the center of FOV. And after that, we will do the FOV generation, and then transmit the encoded video of the predicted view to users in advance. This figure illustrates several important concepts in our approach: the tile, the FOV, and the viewpoint. In this figure, each tile is 30 times 30 degrees in size. The green dash lines given an example of tile, since the 360-degree view is 360 times 180 degrees in size. It has 72 tiles in total. When wearing the Samsung Gear VR as the user HMD, the FOV is around 90 times 90 degrees in size. The orange dashed lines presents an instance of FOV. The viewpoint is defined as the center of the FOV, which is marked with the orange arrow in this figure. Here we give a brief introduction about the dataset we use. The setup is Samsung Gear VR with sampling frequency as 5 Hz, meaning 200 millisecond duration for each sampling points. The head motion traces are collected from over 36,000 viewers for 19 360-degree or VR videos. As for tails options, we choose the 30 times 30 degree for each tail, and thus we will have 72 tails in total. Here we show some VR dataset statistics, as well as the head motion speed versus time in one video sequence. This box plot shows the head motion speed distribution, and you can see in the most of the time, the 75th percentile of the head motion speed are around or larger than 50 degrees per second. And this shows the challenging situation of doing the prediction, since the viewers may change the viewing directions fast as well as frequently. We also show an example of the attention heat map. We define it as a series of probability that a viewpoint is within a tail for n viewers during a time period. In this figure, as the legend shows, brighter tails attract more attention, and viewers are more likely to look at these areas. This shows the feasibility of performing the viewpoint prediction, since in a given time period, some areas always attracting more attention than remaining areas within a 360-degree view. We can see some multiple tails, as high as 11 tails in this example, have relatively high probabilities, indicating the difficulties of predicting viewpoint accurately. Next, I will talk about how we do the viewpoint prediction. We predict the viewpoint position for 200 milliseconds in advance using the head motion trace in past 2 seconds. We propose a multi-layer LSTM network to do this task. The input features are tail-based one-hot encoding representation for viewpoint traces as 72 times 10 metric, since there are 72 tails and 10 timestamps in 2 seconds. The label for training is whether the viewpoint belonging to each tail as 72 times 1 metric. And after training the model and learning the head motion pattern, once we gives the head motion in past 2 seconds. The output of our model is the probability of the viewpoint belonging to each of the 72 tails for the next 200 milliseconds. And here is an example. The blue lines shows the head motion trace in past 2 seconds for a user, corresponds to the time from 3 seconds to 5 seconds. And we want to know where this viewpoint when time equals to 5.2 seconds, corresponding to 200 milliseconds afterwards. In other words, using the tail concept, we want to know which tail the viewpoint will be belonging to. This figure presents the prediction of our Chiang model, the probability of viewpoint belonging to each of the 72 tails in next 200 milliseconds. In this figure, you can see the yellow tail has the highest probability as 37%, and green as well as the blue tails also have a relatively high probability, which are 24% and 11% respectively. The left figure shows the LSTM model we used to do the viewpoint prediction. We used the training data and test data as these settings. In test session, we used the new users, which are different with the viewers in the training data. For the first layer and second layer, we both have 180 and 28 LSTM units. And the fully connected layer, we have 72 nodes. We explore 4 deep learning or classical machine learning models for viewpoint prediction, the LSTM, stacked sparse autoencoders, the bootstrap aggregated decision trees, and weighted k-nearest neighborhood. And we compare the performance of these 4 models in the following slides. Specifically, the stacked sparse autoencoder have 2 fully connected layers with 180 nodes respectively. Bootstrap aggregated decision trees in that examples with 30 back decision trees. And the weighted k-nearest neighbors have 100 nearest neighbors. And next, we will talk about the FOV generation method we use. Firstly, we select M tails with highest probability predicted by our LSTM model. Then we compose the predicted FOV as the combination of the FOVs for each selected tail. Finally, we transmit the predicted FOV with high quality while leaving the rest of the tails blank. Alternatively, there can be the strategies of transmitting the rest of the tails with low quality. The left figure shows an example of the FOV generation when we select the top 2 highest probability tail provided by the viewpoint prediction model, which means M equals to 2. The yellow area illustrates the predicted FOV consisting of the 26 tails. It is the combination of the FOVs for the 2 selected tails. And in our current method, we build 120 times 120 FOV around the center of the selected tail. By doing this, we can guarantee that when the viewpoint is within the predicted tail, the actual FOV is larger than 90 times 90 in size. You can see in this figure, the FOV will be 90 times 90 degree when the viewpoint is at the corner of the predicted tail, and 120 times 120 when the viewpoint is in the center of the predicted tail. Then we define the FOV prediction accuracy as the probability that the actual user view will be within the predicted FOV. Note that the FOV prediction accuracy depends on the LSTM model accuracy and FOV generation method, and thus reflects both the performance of our LSTM, or the prediction model, and FOV generation model. We can see a trade-off between the FOV size and the FOV prediction accuracy. The prediction accuracy is 100%, meaning that the user view has 100% guarantee of being within the predicted FOV. If the predicted FOV is the whole 360-degree view, but this will have very high bandwidth. By selecting more tails, which means larger M, with high viewpoint probability, we can achieve higher FOV prediction accuracy, but we also have very high bitrate. Thus, the final predicted FOV depends on the number of tails M selected. We can use the choice of M to achieve the desired trade-off between the FOV prediction accuracy and the bandwidth consumed in transmitting the predicted FOV. The choice of larger M leads to higher bandwidth but better FOV prediction accuracy, while smaller M causes lower bandwidth but higher risk in FOV prediction accuracy. Here are some experimental results. This figure shows the FOV prediction accuracy and pixel savings obtained by selecting different numbers of tails, which means the choice of M to generate the FOV. In this figure, the FOV accuracy just refers to the FOV prediction accuracy. The blue lines shows the FOV prediction accuracy obtained by different methods and are assigned with left y-axis, while the green lines represent the pixel saving corresponding and are assigned with right y-axis. We can see that as number of tails M increases, which is represented in the x-axis, the FOV prediction accuracy continuously increases, which is shown in this figure as the blue lines, and the pixel saving simultaneously decreases, which can be observed in these green lines. This shows the trade-off between the FOV prediction accuracy and the pixel savings. This figure is obtained when we use the medium motion sequence to do the training and test. And then I will show you another result. In this figure is obtained when use the high motion sequence, which means more difficult to predict the head motion. You can see the FOV accuracy decreases compared to previous figure obtained in medium motion sequence. In these two tables, we show more experimental results using more video sequences. You can see that it shows possible to achieve high FOV prediction accuracy while significantly reducing the bitrate. In both of the tables, we set the FOV prediction accuracy as around 95% and compare the pixel savings achieved by each model. You can see all FOV accuracy are around 95% in the tables. Then we can observe that our LSTM model achieves significantly larger pixel savings than the other three models. Our LSTM model can achieve around 95% FOV accuracy with around 55% and 43% pixel savings for medium and high motion sequence respectively. For relatively low motion sequences, in the table below, it achieves higher pixel saving to achieve 95% FOV accuracy. In summary, among the 4 machine learning models we evaluated, our LSTM model performs the best in terms of the FOV accuracy and the pixel savings. Here is a summary. We proposed a predicted view generation approach in order to reduce the latency and bandwidth needed to deliver the 360-degree videos and cloud or edge-based VR applications, leading to better mobile VR experiences. We present a multi-layer LSTM model, which can learn general head motion pattern and predict the future viewpoint based on the past traces. Our method presents good results on a real head motion trace dataset and shows great potential to reduce the bandwidth. Our planned future works include developing adaptively streaming algorithm using our training model That is to say, we will stream the tiles with different video quality based on actual bandwidth condition. For example, we will stream the tiles with high quality if that is predicted with high probability. And since we focus on the head motion prediction in this work, our future work also includes extending it to 6 DOF, the 6 degrees of freedom, by doing the viewpoint, considering the body motion as well as the hand motion. Yeah, that's it. Thank you for your listening. Yeah.
Questions?
Predetermined, right? So
yeah,
as you move the user's focus, the number of tiles you need to optimally cover the user's field of view may be different, right? Yeah. Did you look into that aspect, or you assume it's the same number you need? You understand my question?
Yeah, so you mean in this one?
In this picture, for example, you show these two cases. They are covered by the light color ones, right? But if you pick a position in between those two, maybe you need more tiles than those two positions, right?
Yeah, I know, yeah. So here in this work, we assume that with the Gear VR, the FOV is 90 times 90 degree. Yeah. Currently not, but I will discuss it with my advisor as well as the Sensor Research America. Yeah, that's it.
So, in your current kind of prediction, you use the past 2 seconds to predict the next 200 milliseconds, right? Yeah. So have you tried, let's say, using longer history window to predict farther away?
Yeah, that's a very interesting question. Yeah, we have tried in our experiment, but we found that when we set the time window as 2 seconds, 1 second, and 3 seconds even more, the 2 seconds give us the best results. Yeah, maybe we can do more exploration in this field. Yeah.
Right. So, but how about the prediction part? So, if you want to predict 1 second away, or 2 seconds away, or 5 seconds away, how much you can push this?
Currently, I cannot give the conclusion, but I think we don't need to predict really far away, like 1 second or 2 seconds, because if we do things like that, the accuracy will decrease. Yeah, that's it.
Right. Okay.
Thank you.
Okay. Thank you. Okay. This is your USB, right? I can use my own computer. Is this your USB?
No, it's not mine. This is okay.
Also introduce yourself.
I can introduce myself. Hi everyone, my name is Dongbiao He from Tsinghua University. Today I will present the work joint rate and FOV adaptation in immersive video stream. In recent years, there has been a significant interest in virtual reality applications, including 360-degree videos, and typically it will cost a lot of more bandwidth compared to a regular video, and up to 6 times more bandwidth will cost when transmitting 360 videos, and the user will only use 20% of the transmitted data that is a part of the video that is actually viewed by the users at any given moment. Furthermore, 360-degree videos typically require a higher resolution in order to provide a high-quality viewing experience, which further increases the amount of data that has to be delivered by the network for 360-degree video streaming. So, for improve the network utilization, viewport-based strategy is often used in immersive video streaming. So, a traditional immersive video streaming architecture is composed of two elements, a server hosting the video content and a client streaming the video using the protocols such as HTTP. At the server side, the content will be divided into multiple tiers, and each tier will encode at different quality levels and temporarily segmented. And each segment has different lengths according to the real application requirements. And in order to start a video streaming session, the client first downloads the video to retrieve to the client, and with a specific quality level, and the read adaptation in the client side will choose the appropriate read according to the network conditions. And in the 360 video streaming, they will have another component that is the viewport adaptation, that to choose the data the user really wants. So once the quality and the viewport have been decided, once the viewport and the read decided, the user will request the segment from the server, and the server will transmit the data to the users. So for 360 videos, there will be two more things to be determined. One is the read, and the other one is the viewport. For viewport, there are lots of prediction algorithms, and recently, yes, there are some AI technologies for prediction, and it requires large data sets for training, and will cost more computation overhead in clients, and different video may have different user behaviors, and we might build different models for the prediction, and the prediction may be inaccurate, which will lead to viewpoint deviation. So in our paper, we provide a much more simple solution that is joint read and FOV adaptation. And it consists of three major steps. First of all, the delay measurement, and the second one, FOV computation, and use FOV computation to adapt the read transmit to the user. So first of all, let's focus on the delay measurement. The client will start to require a content at T0, and the request will set to the server. And after a TC time, the server will respond the data to the client. And the client will buffer the data into a buffer, and there will be a TB buffer delay. And after that, the segment will start to play at TC plus TB, and it will last for TS1 time. So when the first segment finished, we should provide the second segment, and continuous we should provide the segment one by one. And there are two major requirement for the QoE considerations. One is the inter-segment. There should be no video freeze between segments. For example, the TS1 and between TS2, there should be no delay between them. And for the inter-segment, this is the particular things 360 video have. There should be no viewpoint deviation in each segment. So how do we use the delay measurement to estimate the FOV computation? First of all, we should define a parameter to illustrate the FOV and user behavior. First of all, we would transmit the sphere to the tiles, and the length of the tiles is pi. And when giving a time interval, the user would move inside a specific zone. From the figure, we define the maximum horizontal distance to measure the user head movement in the given period. And the D in this figure is the distance within a given time interval. And from the definition, we can draw the table from the dataset available in MMC 2007. From the table, we can find that the user moves shortly during a given time interval. For example, we can see that there is a 90% users probably that the user will be viewing a view FOV that is within the distance 0.096 at time 100 milliseconds. And from the initial FOV, when we enlarge the time interval to 750 milliseconds, the distance of the user change is within 1.11 with 90% probability. And even given a 1 second, there are 85% users will change only within the 0.956 distance within the dataset available. So we will find that the user in a short time interval, it will move very shortly, and only part of the sphere of the view should be transmitted to the user. So how to use the relationship between the distance and the delay? So let's define tau as the choice of FOV. Tau is a time function related to the D, and when D is 10 to pi, the tau can be infinite, and that means the user can look everywhere in the sphere. So if we give a small d, the user will face a viewpoint deviation. Some part of the data user wants has not been transmitted to the user side. And if we give a larger d, the user will see everything they want, but in a relative low resolution. But compared to case 1, the user will be a bit more happier about this situation. So we define 3 different parameters: the segment S in S, and the network TN, and the link complexity. And we should measure the S to meet the requirements put forward previously. And we have the equation shown in the slides. For a given tau, and the tau should meet no viewpoint deviation. That is, the tau must be larger than the transmit of the segment. And in another, we should not have video freeze. That is, the segment S is related to the link capacity. We should not transmit much more larger size of the S. And then we can have the segment S. From this equation, we will find that the choosing of FOV tau should certify that tau is larger than Tn, the network delay. And we can recall the table previously. We can find that with the growing time, that means the network delay, the FOV distance should be larger. So we can have a mapping with the network delay to the FOV distance. That is our choice of the FOV. Once the FOV is determined, we should measure the sending rate. The basic strategy is very simple. If the network is responsible, less tails of FOV with high resolution should be transmitted. If the response of network is low, we should transmit with the FOV with longer distance and with much more tails, cover more things in the sphere. And also we have an enhanced strategy, and this is based on the basic strategy. As we know, the different tails in the sphere might have different probability to be seen. So we can use this probability as the weight to allocate the bit rate for each tail. And this is a work based on the study of navigation likelihood published in ICC 2008. So we use the rate measurement, FOV and network delay to control the transmission of the FOV. So there is a very important issue that when the network state changes greatly with the fluctuation of the sending rate, that means the available link capacity varies according to the time. So we have one goal that control the sending rate in a steady mode. That rate can be steady increase or steady decrease or remain static, but we cannot accept dramatically change of the sending rate. That will have a bad effect on QoE. So we setting two thresholds for control the rate, R low and R high, and adjust the sending rate with the delay estimate from the network with these two parameters. And the solution is very simple, and we have 4 conditions. Once the new delay is less than the R low, that means the network is very responsible. We can allocate the max rate to the sending rate. And if the network delay is larger than the R high, we should apply a smooth decrease factor to decrease the sending rate. And when the new delay is between the R low and R high, we should use another parameter, additive increase parameter beta, to steadily increase the sending rate. Once we set the rate larger than the capacity, we should set the rate equal to the link capacity. And then we come to the evaluation part. We use trace data from the data set mentioned before and use a simulated HAS algorithm. And we select 2 link capacity and the 0.5 Mbps as the low link capacity and 1 Mbps as the high link capacity. And we use 5 comparisons to illustrate our strategy. One is AF represent our strategy, and D1, D1.35, D1.5, and D5 represents the different distance, the static distance choice of setting FOV. And we measure a much more simple QoE matrix, that is average bitrate, FOV mismatching frequency, that is viewpoint deviation, and the network delay. First of all, we can see our performance of the bitrate. Since we use R low and R high to control the setting rate, the setting rate is steady grow up with the time, and our solution is just behind the distance of D1, and we can achieve 94% of bitrate with D1. That is transmitted small size of the FOV. So our solution could achieve the average bitrate between setting rate 1.0 and 1.35. And when the link capacity is low, our solution tends to transmit more spheres to cover more ties for the users. That is, we transmit more than 80% of the data in distance equals to pi. And for the FOV deviation, our solution could capture the network delay, and according to the network delay to choose the FOV. So our FOV deviation is very, very low compared to the other strategies. And finally, for the QoE score, we use the basic bitrate and frequency mismatching and the delay to measure the QoE score. And our solution has the best performance in the trade-off between bitrate and FOV deviation. From the table, we can know. And at last, we can conclude our work. First of all, we have the FOV adaptation, use the delay measurement model to cope with the viewpoint prediction, and then the rate adaptation touch the buffer-based control algorithm to ensure the continuous playback with network latency. And the advantage of our solution is very simple. For predict the prefetch FOV with a network delay estimation, but there is a major disadvantage, that is we should have more segments with different lengths for various network conditions, and the segment should be very, very small when the network is not responsible. If the network is good, we can just prefetch a little of FOV for the users. And that's all. Thank you.
Any question? So, I mean, if I understand correctly, right, so your FOV selection is mostly based on the delay measurement?
Yeah, most on delay measurement.
Okay. How about the rate? Has any impact on your FOV selection? So let's say if your bandwidth is high.
Yeah, the bandwidth is high. We just select a small part of FOV because the network is very responsible, and we just send a small part of the FOV with high resolution.
Well, I mean, bandwidth high does not necessarily mean the delay is short, right? So I'm saying if the bandwidth is high, but the delay is also long,
okay.
What do you do then?
We have also measured the network delay. It maybe have the relationship to the bandwidth, but we actually use the network delay. And in most situations, if the network bandwidth is large, we assume that we have the short network delay.
Well, I think my main point actually is if the bandwidth is high, you can actually afford to download more data. So
yeah.
that way you are less kind of vulnerable to prediction, let's say, error. So in that sense, you should do this kind of FOV selection, not just based on delay, also based on the bandwidth. So if you have whole lots of bandwidth, why don't you download the whole thing, right? So you're not going to have any error at all.
Yeah. But in our design, if the delay is not large, we just pick the most important part of the FOV, because when the user changes the user changes its navigation or the angles, they can quickly get the content they want. So when the network delay is not large, is small, we just transmit part of the data, but the network is not responsible, is within a high latency. We transmit most fields, but with low resolution.
Okay, so you are basically depends on this kind of reactive solution, right?
Yeah,
so
yeah.
Detect the user. Okay, you're not doing much kind of prediction there.
Yeah, we do not prediction. We just use the network delay to allocate the FOV perfection.
Okay. Okay, let's thank the speaker again. So with that, we conclude the workshop, and I would like to thank all the speakers and for sharing with us your vision and your results. And of course, I'm sure everybody's going to go back and get more work done. And I hope to see you guys somewhere else in some conference, maybe next year workshop sometime. Okay, thank you all.
Welcome for this half-day workshop on self-driving networks. We have one of the co-organizers, Jenny Rexford, here. We have the other co-organizer, Nick Feemster, who couldn't make it, and I'm the third co-organizer, Walter Willington from Nixon. So welcome for this experimental workshop on self-driving networks. It sort of came together over the last, I don't know, 3-4 months when Jen and Nick organized an NSF workshop, I guess, was on self-running networks. and And so we thought maybe this might be an interesting topic for SIGCOMM, because it connects sort of latest developments on programmable networking with sort of ideas from stream processing, and together you combine it and hopefully get towards this vision of doing real-time detection and reaction to events, so that you can manage networks in essentially real time. And so we thought this is a topic that sort of covers a number of interesting issues related to systems, algorithms, stream processing, machine learning, deep learning possibly, and all this stuff. So we ended up with sort of 6 papers that we accepted. They will be in 3 sessions, and the basic idea is each paper has 10 minutes, and then there is 5 minutes discussion. So we hope for some extensive discussions. So we invite you to participate. If certain topics require more time, we will have half an hour at the end of the workshop, where we again invite you to participate in sharing your views of some of the concept ideas, what has been missing, what you think may be important and hasn't been stressed enough. So anything there on the discussion side, it's really up to your participation. So with that, I hand it over to Jen, and she will introduce our keynote speaker.
Great. Thank you, Walter. So the first talk, this session's going to have 1 keynote talk and then some technical talks as well. So I'm going to introduce our keynote speakers. We're really fortunate to have Jeff Mogul here. He works on fast, cheap, reliable, and flexible networking infrastructure at Google. Until 2013, he was also a fellow at HP Labs and has also been at DEC Compact after receiving his PhD at Stanford. So he's been a real stalwart in the community for many years and is involved in many of the standards we use every day and downloading content from the web. And so I'm really interested to hear his perspective on the topic of today.
So good afternoon, and thank you all for coming. It looks like it's actually a pretty full house. So I'm going to talk a bit about self-driving networks from a point of view of somebody who's never actually worked on a self-driving network per se, but some of the work we've been doing is maybe aiming in that direction. I would argue, starting from the point of view that if you think about self-driving cars as an analogy for self-driving networks, let's think about how we build a self-driving car in 2018. We take a very recent car. Nobody's building these with old cars. We had lots of sensors, computers, and AI software, and then we train it and test it and train it and test it until it's working safely. And I think a lot of people were surprised at how fast this worked out. That I think, maybe if you'd asked even the experts in the field 10 years ago, they might not have said you could be looking at trials by 2020. But that may not be a great analogy for self-driving networks. So think about taking a modern network, adding lots of sensors and computers and AI software, and train it and test everything until it works safely. What could possibly go wrong? Well, one thing about self-driving cars is that they start with a car that pretty much any fool can drive. If you've ever seen somebody, try to learn how to drive a car, you don't have to be very smart to learn pretty quickly how to drive a car. And most people get through the world without too many accidents, too many fatal accidents. So presumably by analogy, if you wanted to build a self-driving network, you'd want to start with a self-driving network that any relatively smart operator could run without frequent outages. Well, the problem is that the first kind of thing exists. We can buy these cars, and really the second kind of thing doesn't exist. As far as I know, no one has ever built a network that larger than a few nodes that even the smartest operator can't run without occasional and fairly long outages. So the problem, I think, is to think about, well, what make cars and networks different, but also to think about what are kind of the things that got us to the point where these cars are actually safe enough that we can put people in them and not be in fear of their lives. Well, to backtrack one step, I think the important thing in terms of networking is, in order to be able to rely on our networks, we have to have some concept of safety. And one way to think about safety is service level objectives, or SLOs, for properties like uptime and bandwidth and latency. And from what I've seen, I mean, I work for a company that probably knows what it's doing to a certain extent. We have large numbers of very skilled network operators, and it takes an awful lot of effort to maintain the SLOs in our network. It's not something that just sort of happens and once in a while somebody gets a pager. My concern is that trying to replace humans with AI for a problem that is unnecessarily hard could be a mistake. So the talk is really about how we meet that challenge. And in particular, what can we learn from the car industry? So an alternative title for this talk might be, nobody would build a self-driving Corvair. So what's a Corvair? Raise your hand if you've ever heard of a Corvair. Yeah, so some of us are a little bit older than the rest, I guess. It was a compact car made in the US by Chevrolet for about a decade. And it apparently, according to Wikipedia, was the only American-designed mass-produced car to have a rear-mounted air-cooled engine, which was an innovation of sorts, but it was also a problem. This is a picture of a Corvair, as you might expect. It became sort of the paradigm case of an inherently unsafe car. This is largely due to a book written by Ralph Nader called Unsafe at Any Speed. There were some subsequent studies that showed that maybe this book wasn't quite fair to the Corvair, that all the cars in the market were pretty bad at that point. But the book is interesting because it analyzes why the Corvair was unsafe. So this is a book that was published in 1965, and it explained basically how car designers failed to consider safety when designing cars. They were much more focused on things like how much chrome you could put on it. And as a result, what kind of problems people had with these cars, and they were actually pretty bad. He picked particularly on the Corvair, although there's many chapters in the book, and only a few of them really are about the Corvair. My understanding is that the publication of this book led to the kind of outrage that led to the kind of laws that led to the kind of safety features we now sort of take for granted. It also launched Ralph Nader as a public figure, but that's a separate issue. So what might people in this community learn from automobile design? Well, I think I would summarize the point of this talk by saying that any control system has its limits. Whether it's a human control system or an automated control system, if you try to operate the control system with an underlying plant, basically, that is running outside the domain of what the control system can handle, you're going to be in trouble. And if you push the system beyond those limits, you'll get crashes of some form or another. But one way to think about this is sometimes the problem isn't in the control system. If the underlying system is impossible to control, then it's not the fault of the control system. Okay, so let's talk about the Corvair a bit. And it's actually, this goes 60 years ago, so it's not really about self-driving at that point. Ralph Nader asserted that the Corvair, by its design, was inherently unsafe. So there were a lot of expert drivers who wrote for auto fan magazines who said, this car is a lot of fun to drive because sometimes it can be challenging. Well, real drivers found themselves in real trouble unexpectedly as the result of some of these challenging features. And in particular, in some cases, you could get into a maneuver that didn't seem like it was that risky, and you would not be unable to recover, and the car would flip over, and people were killed or maimed or whatever. It was quite a lot of accidents. It turned out that some of the problems that caused the car's instability were the result of intentional design choices. This wasn't a complete accident. And Nader alleges that these were due to bad intent, but I'm not going to go there. I don't think it's necessary to debate whether GM was malicious or not. Now, given these properties, if you're going to build a self-driving car, you would not use a Corvair because you'd have to have an especially wonderful control system just to keep the passengers alive. And also, you might find that you as the designer of the control system might get blamed for the accidents that weren't really your fault. I would argue that today's communication networks are a lot more like 1965 Corvairs than like 2018 Volvos. And I'll try to talk about that in a little bit of detail, but I'm not going to go into great depth on that. Just for sort of background, I know you're probably not automobile engineers. I'll talk a little bit about what went wrong with the Corvair design. Pointed out that when you were trying to go around a corner quickly, sometimes the car it has a quote from Nader, it abruptly decides to do the driving for the driver in a wholly untoward manner, basically completely unexpected and wrong. And the physics behind this is that they used a kind of an axle that is seldom used in cars today called a swing axle suspension. And that sometimes when you're going around a corner, one of the wheels would basically tip over far enough that it would start to basically tuck underneath the car, would lose contact with the road, and then the car would probably go into a skid and might flip over. It turned out that because it was a rear engine car, there was a fair amount more weight in the rear of the car than normal. And General Motors thought, well, we need to make this car more stable, so we'll recommend an interesting distribution of tire pressure. So if you ever put air in your car tires, there's probably a little sticker in your car that says what pressure you should use, and it's probably about the same pressure in the front or the rear. But for this particular car, they recommended 15 pounds of pressure in the front. I don't know what that is in metric, and 26 in the rear. That's a not quite 2-to-1 ratio. This was a recommendation that GM used instead of actually spending a little bit more money to build the proper kind of suspension. So tire pressure, really, this was what kept people alive in these cars. Well, Nader's point was that instead of all the stability being inherent in the vehicle's design, the operator, the driver, or the owners, you have to rely on that person to maintain the right pressure differential. And he argued that any policy which burdens the driver with monitoring these pressure differentials closely and persistently, now, cars leak air, things are going to change temperature, can't be described as safe or sound engineering. Or in most cases, you would go into a gas station, you'd ask the attendant to put the air in the tire, and they didn't care either, partly because nobody knew why it was actually that important. The owner's manual didn't say the car will flip over if you get the tire pressure wrong. And then also, if you had more heavy passengers than normal, or you put some more stuff in the trunk, then you actually had to change the differential, and nobody knew what the right pressure levels were. So does this sound a little bit familiar? If you've ever had to manage a router of any major complexity. So just like cars, networks can be unstable in various ways. And I guess I'm repeating myself, but basically saying we really can't expect an automated control plane to cope with an arbitrarily unstable network. And so I think the point that I would like to push in this talk is that as you're thinking about building self-driving networks, it's great to think about the control systems, the machine learning, the AI. It's also probably important to think about how do you make the networks controllable so that you're not actually solving the wrong problem. And in particular, it may be that you might have some regions of instability, but you like to bound those so you know where you are, and you'd like to know, you'd like to make those unstable regions as small as possible, or maybe contrary-wise, the stable region as large as possible. Now, one aspect of this, it may be that sometimes you may actually have to push some of the stability control into the network itself, that a dynamic machine learning-based control system might not be rapid enough to respond to the kinds of things that happen on a short term. Just as cars today have things like traction control and anti-lock brakes that allow even the self-driving car operation control system to not have to worry about those very fine timescales. I think this is probably stuff that everybody's seen before, but for example, one thing that causes instability networks is you actually have multiple control systems that are trying to operate different aspects of the same network. So for example, we've seen our traffic engineering system, which is a fairly global and relatively long timescale system, interrupt badly with the TCP congestion control system that's relatively short timescale and relatively distributed, and they don't talk to each other, and so you get into a situation where they're not necessarily working with a common goal. Another problem we've seen is that the control system is just too slow. So for example, a link might flap more often than the control system can handle. Sometimes it's a matter of scale. If you have a testbed network with 3 links and one of them is flapping, your control system can probably keep up a bit. If you have a global network, the size of AT&T's or Google's or Microsoft, and there's 7 or 70 links flapping, that may be more than the control system can actually handle. You never reconverge the routing system. And then there's also interesting mechanisms like the accidental large-scale synchronization that Sally Floyd and Van Jacobson wrote about back in the early 90s. I'd encourage you to read this paper if you don't believe this thing can happen. So again, maybe we should be fixing these problems directly rather than trying to build control systems that can save us from these. Another issue is the so-called Byzantine fault. People familiar with the term Byzantine fault? Yes, no? Raise your hand. Yeah. Okay, a Byzantine fault basically is a system where it's not fail-stop. The system doesn't fail by stopping. It fails by giving bad answers. And so it's you can think of a system that's lying to you. And there are actually a whole bunch of examples of these we've seen in production, other people have seen. For example, a routing system failure that randomly drops packets in, or worse, randomly forwards them to the wrong destination. It happens. There's an example, which if I have time, I have a diagram to explain this, but basically switches that report bogus link utilizations, feeding that information into an automatic control plane can result in interesting failures. Or we've also seen in situations where you take a routing configuration and you push it to a routing service and it says, yes, I got your new configuration, but actually it's lying, it got half of it, and so maybe half of your routes have suddenly disappeared. So again, one of the issues is the difficulty in controlling systems that are sometimes hard to control. And Nader's argument in the book was that the auto industry kept pinning the fault on the driver, saying, well, the problem with auto crashes is drivers need to be better educated. It's not the fault of the auto designers. But again, I think we should think about that. So here's some examples from the car industry. One of the problems that I think was a problem with the Corvair, was certainly one of the cars described in the book, was the way that the transmission was designed. So raise your hand if you've never driven an automatic transmission. You've never driven an automatic transmission? Yes. Okay, everybody's driven an automatic transmission. This is the standard shifter design that almost everybody would be familiar with in an automatic transmission. However, back in 1960, this is the standard one on the left now. On the right is what some cars used, and it turned out to be slightly cheaper. There was like the little mechanical linkage that you could leave out, and you could end up with the reverse at the bottom of the shift pattern, just next to the low gear. Okay, what's wrong with this? Well, it turns out it's actually a little bit hard to, if you're actually trying to, like look around you and you're trying to do the transmission by feel, you might aim for low and put it in reverse or vice versa. And this has, of course, the property that the car goes in the absolutely wrong direction from what you're intending, and plenty of people were killed or injured because a car hit them because of this. That's not so good. The standard pattern, the one we're all used to, places the reverse in a different place so that it's impossible to switch from a forward gear directly into a reverse gear or vice versa. And this makes accidents much less likely. And people long before 1960 knew this is the right thing to do. But they had to be, I think, probably encouraged through lawsuits and laws to make this actually the official standard. Now, it turns out that we have seen slightly similar problems in network control systems. So I'm going to give you a very oversimplified version of the problem that we've seen. So we want to maybe automatically decommission a bunch of switches in the network because it's time to retire them and take them out of service and put them in the scrap heap. So the script that does this does a database lookup to find the list of switches that meet some criteria, and then it takes this list and it passes it to an automatic decommissioning system that sends off robots or humans or something to unplug the switches and throw them away. Now, supposing that you run through the script and that at some point you get a failure sometime during step 2, and the operator scratches his or her head and says, oh, I should probably rerun the script. All right, so what happens when they rerun the script is that it turns out that all the switches were decommissioned. So the result when you rerun the script of step 1 is you get an empty list because there are no more switches that need to be decommissioned. Well, it turns out that due to a perhaps not particularly smart programming style, the input to the second system says, if you see an empty list, that means everything. Why would anybody give me an empty list unless they wanted to specify star? Well, okay, bye-bye all your switches. That was a problem. This is not quite exactly what happened to us, but close enough. So, an example of where a an imprecise interface could be a problem in an automatic control system. Okay, it turns out that this transmission problem was actually, there was another problem with the cheap transmission on the right. Because a lot of people had two cars at their households, and one of them would use the good transmission pattern and one would use the bad one. And well, sometimes people get into a car like that, you know, I might get into my wife's car and I'd shift thinking it was my car, and all of a sudden, boom, you've got the same problem. You're driving in reverse when you think you should be going forward. Now, this is an argument for standardized interfaces, not just for humans to take advantage of, but control systems that might have to deal with a large combination of equipment from different vendors. You'd expect them to be more likely to get into accidents if they have two different systems to deal with. So there's actually a paper, a workshop paper about 5 years ago, pointing out some of the dangers of the ambiguity in the open flow interface. And I think a paper earlier this week mentioned some ambiguities in the P4 interface. I'm not going to go through this example. There's another issue of the too many standards. So the first one was about imprecise standards. The other one is about too many standards. There's different ways to express firewall rules for different router vendors. Cisco does one thing, Juniper does the other. I've heard it's extremely difficult for humans to translate a Cisco firewall rule set into a Juniper one or vice versa. And so, of course, well, what do we do when we have too many standards? We create another one. OpenConfig is now the next big thing. So we've solved the problem, right? Maybe. I think people may have seen this one before. But hopefully, OpenConfig will win, and we will, of course, kill off the other 14 standards. Another thing about cars is that not all the car crashes in the world are solo crashes. I mean, the overturns and the shifting wrong were the mistake of one driver in their own car. But there was quite a lot of effort, again, to pin the blame on the drivers rather than the cars. And so Watch Out for the Other Guy was this advertising campaign in the early 70s. I'm not sure how long it lasted. And I apologize for the sexism in the ad. It turns out that older cars made it relatively hard to watch out for the other guy because side view mirrors were an extra cost option. You might find that hard to believe, but people didn't spend the extra $15 to get mirrors. And the mirror on this is the driver's side mirror. The mirror on the passenger side was even more recently an option. There's some interesting stories about the invention of car mirrors. I'm going to skip that right now. So self-driving network systems actually do also have to watch out for the other operator, because in many cases, the network you're trying to manage is going to have other people trying to manage other aspects of it. So somebody might be working on the power system. Somebody might be just moving a rack around. The other day I read about somebody in our data center who had to replace the wheels on a rack. Well, that means that you have to disconnect it at least partially. Maybe your cloud customers have peak workloads you weren't expecting if you're a cloud operator. And also, there tend to be very few networks are islands, so you're dealing with the operations of the networks adjacent to you. For example, maybe you're one ISP and you have network operators from another ISP who are doing something at the same time, and you have to be capable of tolerating that kind of thing. Or accidental BGP hijacks would be another example. Another issue in the car domain was that people for a long time believed that humans just couldn't survive car accidents. The car hit something at 60 miles an hour, you were doomed. Well, the issue there is that it's not the car hitting the wall at 60 miles an hour that kills you. It's you hitting the car at 60 miles an hour because the car has suddenly stopped. That's what kills you. It turns out that it's not even that bad. If you're in a well-designed car, you're probably not, well, at some level, you're going to survive the collision, except for the fact that the 1960s cars were badly designed. So, for example, the steering column could impale the driver because it was rigid. You don't realize today that the steering wheel column in your car has some sort of energy absorbing thing, so it's not going to kill you when you get into an accident. There's a whole bunch of other things that Nader described in the book. Don't want to do that right after lunch to describe all the injuries, but in network failures, we often find the same kind of thing. We do postmortems or outages. And so, for example, a control plane may be able to handle a single failure, but not lots of them at once. Or you may have a failure in the network that triggers some recovery code, and that hasn't been tested adequately. So that's what actually causes the network as a whole to fail. The recovery code may have a much worse influence on the network than the original fault. Or it may be able to handle a single failure, but it wasn't tested with multiple failures. One example we had was a system which was detecting a data plane problem. It could successfully route around. It would dutifully log this, sending log messages to a remote logger, but it was happening too often and the remote logger was backing up, so flow control, buffer builds up, buffer uses up all the memory. Uh-oh, this controller fails not because it can't do anything, but because its log entries have filled up its memory. So we've seen that in practice. So we have all sorts of ways of surviving car crashes. I'm not going to go through this slide, but in particularly with networking, we might be able to do similar things where we separate the control plane into a relatively simple and very autonomic kind of control plane, and then a more complicated one. So for example, in our networks, we typically have a fairly complex centralized traffic engineering system, and then we fall back to something like IS to IS or OSPF, I can't remember what it was, so that if the traffic engineering system dies, we still have some control over the routing of the network. So I'm going to go through some quick examples of the system called Bandwidth Enforcer that was described at SIGCOMM 3 years ago, and it's basically what we use to throttle the traffic coming into our wide area network. So in this picture, Bandwidth Enforcer, let's see if I can use my pointer here. Here's the network, here's some VMs, here's some various measurement and rate limiting things. Bandwidth Enforcer gets network monitoring data through various systems and then computes an admissible workload for each of the hosts and contributes it back to their rate limiters. So if Bandwidth Enforcer dies, we've designed the system so that the rate limiters don't just all say okay 0 or okay unlimited. They tend to make some reasonable choice when the control plane is down. And if all the data sources that feed Bandwidth Enforcer die, it still tries to make reasonable choices about throttling assignments, but it also may assume that the network is either slowly degrading or slowly getting better, depending on what your philosophy is, so that it has some idea about, well, how stale the data is that it's most recently received. Now think about what happens, as I mentioned, when the router lies about its utilization. So you have a router down here that's saying my link is 100% utilized when it's not. So the monitoring stack faithfully reports this to Bandwidth Enforcer. Bandwidth Enforcer starts throttling traffic to try to reduce the load in the link, but the load doesn't go down because it's always 100%. And so it continues to throttle the traffic down until the actual applied load on the link is 0, but it still says 100% utilization. That's a bug we've seen in practice. And there's really nothing you can do here except to think about heuristics that you can use to find the fact that there may be some bad sensor in your network. So again, in a self-driving network, you have to be able to cope with the possibility that a sensor is giving you bad information. The typical operating system people's approach to Byzantine failures is Byzantine fault tolerance, but we don't want to buy 4 routers every time we have just one link. One more thing, because I only have 18 seconds left, is that self-driving cars rely on excruciatingly detailed maps, which we didn't have 50 years ago. And we couldn't have built a self-driving car with 1950s maps. I think also we can't build a self-driving network with basically 2018 maps. Most people don't actually have enough detail about their network to actually do the kinds of things that you might do to control it properly. Testing I'm going to skip, and I will just go to my conclusion, which is to say I'm trying to scare you a little bit that maybe self-driving networks isn't as easy as you might have thought. But think about it in terms of how can we co-evolve the control plane and the underlying network to make self-driving networks work out. And as Jen in her keynote said, you need to fight to enable things. In particular, fighting to enable self-driving networks is looking at it through this lens, not just looking at it as a machine learning problem. So I've done 25 minutes, and I guess I have like 5 for questions. I guess we have microphones. Does somebody want to be a mic runner? Margaret has a question.
First, why don't we thank Jeff first?
Okay. I feel like I'm going down memory lane, reminding me of all the problems we hit. So I thought you were going to make a recommendation. So I guess my question, I mean, I have several, but are you recommending that the vendors should be more robust, because to leave it to the end user, then you end up with all these things, and if depending on the end user, if they're not sophisticated, then they start going down this path of learning as the network crashes and so forth. And of course, you know, the vendor can't do everything. And then you have multi-vendors, so then there's that issue, right?
I don't look at it as purely a vendor problem, because if you think about the way we build our networks, we get equipment from various vendors, including both traditional vendors and self-built equipment, but most people will be buying things from vendors. And then we might also get an SDN control plane, which is, you know, open source or self-built or commercial. And also you have to configure a routing system, which is sort of the, you know, it's a multi-vendor kind of thing. BGP is everybody, right? It's not just Cisco or Juniper. That's the sort of underlying system that I expect the high level will be controlling machine learning, right? So it is of course important for your vendors to have configuration interfaces that are reliable. In particular, for example, OpenConfig doesn't just have a syntax for configuration, it also has some rules about the transactionality about that configuration interface. If you have a non-transactional configuration interface and it can fail for mysterious reasons, it's going to be a whole lot harder to build the self-driving control plane. So yes, that kind of thing you can ask for from your vendor, but also thinking about, you know, are there things that you might even just design the topology of the network so that it's harder to get into weird states because of, you know, maybe a single failure. I don't think I have good answers for that. We have another question in the back there, so maybe you should, you know, sort of self-service the mic handling. I think the microphone is mostly for the recording.
Oh, well, no. I'm not. So thank you for this thing. You have scared me a bit, more than a bit. Do we need to rethink protocols so that, you know, we build protocols to just do their job today, as opposed to, hey, this network will run itself, and so what do we want to put in a protocol? What kind of control system should be in the protocol itself? To your point about don't push everything into the self-driving system. So do I have to rethink ISIs? Do I have to rethink BGP? Or come up with new protocols so that this whole thing might actually work someday?
Well, to a certain extent, the original SDN revolution said, if you can centralize your routing system and get out of these decentralized algorithms, distributed algorithms, you're better off. So that, you know, people have actually tried that. I think the other issue, for example, I pointed out that TCP congestion control and traffic engineering sometimes interact in an unfortunate way. I'm not sure you want to re-engineer the TCP algorithms as much as the end host sort of control knobs that allow maybe a more standardized way for a centralized throttling system to do the right thing. And also, one of the big challenges is to understand when large flows are entering your network. And there have been techniques used, for example, to look at the size of socket buffers rather than just measuring the packets in the network. But even that only works if there's sort of the right conspiracy between the application and the kernel. So some of this may actually push back to more ways we interface with the application and the transport protocol as opposed to the transport protocol itself. Okay. I think the gentleman in the blue shirt. Yeah.
So yeah, Andreas Blank, TU Munich. Thanks for your nice talk. I believe it's a bit far-fetched. What would you say, I mean, about not self-driving net, but for instance, self-driving testbeds first, so let machine learning help us to discover actually problems we might not see. If we implement for applications, we are testing them, but what's about like machine learning enhanced testing services?
Yes, actually, we've done some of that, although I saw some discussion the other day about the hard to interpret behavior of the system that looks at the test data. The machine learning system looks at the test data and tries to figure out what's a problem, what isn't. When it doesn't work the way you expect it to, it's very hard to know how. So I think that's a central problem for machine learning, is the interpretability or the debuggability of the system. I think it's still worth doing, but it somewhat shifts the problem from what network engineers are used to a very different kind of problem domain. So, you know, the typical network operator doesn't have a machine learning expert on staff. And I don't know how to get out of that one. One more question? If we have one. Walter has a question. Yes.
Me as well, no? So, I mean, so I think I appreciate very much this cautionary view, because I think that's very important. But then at the same time, I'm still trying to sort of see what's the way forward, and to me it boils down to some sort of question. So I mean, I always sort of say, I think it's possible to automate the things that we know what we want to automate.
So let me to cut the question short, because I'm sure we're out of time. One way forward might be that when you're doing the sort of typical machine learning things, and you're realizing that either the control surfaces, the actuators in the control loop, or the sensors are making your life difficult, you might want to stop on the machine learning for a while and go fix that, rather than keep bashing on that problem with machine learning. That there are things, if it's not impossible to fix in the underlying network, it might be better to go figure out how to fix that if you run into something that is making your machine learning arbitrarily hard. If the machine learning is going well, I just keep doing it, right? Is that a good answer?
Yeah, I wasn't even going yet to the machine learning piece. I just wanted to
I know nothing about machine learning, so I'm not the right person to.
No, that's why that's why I'm trying to boil it down further to. I mean, you know that there are operators who do things manually that they would love to have automated.
Oh, of course, yes.
Because you can pretty much describe it in detail.
Yeah, and they're tedious and repeatable.
So this you want to get rid of in terms of you want that.
There's that, but
hand over.
More to the point, the things that are hard to do, the things that you need smart operators to do, I think my argument is when you find that it's difficult to automate that, you should look into the reasons why it's difficult, and perhaps it's because the underlying system is badly designed for that.
Thanks so much, Jeff. Really appreciate it. Thank you. So now we're going to have 3 short technical talks, 10 minutes with 5 minutes for questions. And the first talk will be given by Junaid Khader. So he's an associate professor at the Information Technology Institute in Lahore. And before that, he was an assistant professor at the School of Electrical Engineering and Computer Sciences at the National University of Sciences and Technology. And he works on using computer systems and networking for ICT.
Thank you very much for the introduction. I'm very happy to be here and present before this distinguished audience. This is joint work with 2 of my students at ITU Lahore, Tausif and Osama, and our collaborator Gareth Tyson and Queen Mary. So what we're proposing is that we should be using systems thinking to see the big picture of how the various subparts, the various subsystems interact, some of which was highlighted in the last talk, in which we saw that you could have optimizations that conflict with each other. I have only 10 minutes for this talk, let me see, it's not working. Stuck. Maybe you can remove this. Perhaps take this out and back in. Not working. Self-projection problem. Okay, so we're back again. The talk, which is only going to be 10 minutes, so I'd have to rush through, will have 3 parts. The first thing would be to introduce very briefly the problems that we face if we don't have systemic thinking. If we are only optimizing the parts, then some problems arise, and I will be describing those. After that, I will be introducing what systems thinking is, which is a field which has been honed over multiple decades. Since 1950s it started, and there are many schools of systems thinking and complexity science. So I'll just be giving a very high-level overview of tools and insights that exist in this field. And finally, I'll start to contemplate what this would imply for future networks in which we are embedding significant artificial intelligence. So to motivate systems thinking, initially, let me just describe what a system is. So a system must have three parts. It must have elements that have interconnections, and they're all working towards a common goal. So this is how we define a system. Obviously, there are many variants of this definition, but these are the important aspects. So an example of this would be a car. So the purpose of a car is to move from one place A to another place. No part of the system can do this alone. So you have many subparts of a car, but they all have to interwork together for the car to work properly. So just as an aside, in terms of systems, we are mostly interested in complex adaptive systems. These are systems which typically have humans embedded in them. And we know that social systems are very complex to analyze. So some properties of these complex adaptive systems, these systems are very tightly coupled. So you cannot just come in and change one part of the system without affecting everything else. The system has an integrity. You cannot just do one thing. Everything influences everything else. Also, another important thing is that these systems have dynamic effects. So if you make a change, it will not only cause something in the immediate short term, but it will also have many knock-on effects. Some of them will manifest themselves in a very distant place, in a very distant time. And there are trade-offs. So sometimes you may have a solution that is good for the short term, but it may be harmful for the long term. And typically what we are doing as engineers is having a very myopic short-term view. So in complex adaptive systems, there are typically trade-offs. So for example, sustainability, systems thinking is often used there. You could industrialize for many decades, but now we are seeing the effects of that. And in complex adaptive systems, you not only have non-intuitive things, but you also have counterintuitive effects. So sometimes you want to improve the system, but when you intervene, you're actually causing the system to go worse. So some problems due to non-systemic thinking. Many of the problems that we are facing now, as Einstein is quoted, we cannot solve today's problem using the thinking that actually brought these problems into effect. So 5 problems. The first thing is, we have incorrect mental models. Our mental models are often very narrow in time and also in space. And often we are also just dealing with one part of the system. So we are just working with a protocol, we are just working with one autonomous system, or whatever level you're working at. So this is illustrated in this illustration through the fable of the 6 blind men and the elephant. And we know that each blind man is only seeing one part of the reality, but you have to somehow integrate and have a holistic lens through which you can integrate them. And systems thinking is the science which basically aims to provide you tools and insights for this. The other thing is that we often have unintended consequences. If you're working with point solutions, piecemeal solutions, you're just, if you're surrounded by blocks on all sides, you're just knocking down one block without thinking that you may be triggering a domino effect, and this thing may come to haunt you at a later time with much greater velocity and with much greater consequences. Another thing related to this is that, when we are talking of problems, you could think of your problems at different levels. Typically, we are just talking and thinking superficially about the symptoms and just curing the symptoms. So systems thinking is not only about networks, it is about all complex adaptive systems, and it has been mostly applied to the management of social systems. So we see that typically we're just curing the symptoms. Our short-term solution takes the symptoms away, but the systemic structure is still there. And without refixing those, the problem will emerge in another way. Another thing is that we are typically fixated on optimizing the parts rather than the whole. So taking the same car example, for example, you drive a normal car and you have discovered that Mercedes is building excellent engine. And you cannot simply take that and put in your car. The car will simply not start. The reason is that the parts will not interwork together. Similarly, if we are just focusing and improving the individual components, it may not be necessary, and in many cases, it can lead you to even worse results. Finally, we have policy resistance. If you have a social system in a future self-driving networks of which humans would be users of, if you want the users to behave in a certain way and you have a policy, it may be that because of your policy, the people will react very differently, and the problem then changes. This is why we call these systems complex adaptive systems. The second part is then, what is systems thinking? Since this is a very high-level introduction, we can think of it as linking structure to performance and seeing how the interconnects are working, what delay elements are there, what kinds of feedback loops are there, and using that to understand why we are seeing the performance and the problems we are facing, and also to improve performance. A salient aspect of systems thinking is that we have closed loop thinking instead of open loop thinking. Whatever causes that you implement, whatever interventions that you make, it will have effects, and the effects will change the environment, and it might change the problem. So you need to take a feedback view to this. And there is another thing that is very important. It's highlighted in systems thinking literature, something called as systems as a cause thinking. The underlying reason is that every influence is both a cause and an effect. So if you are influencing something in one way, it is also influencing you back in some other way, because we are typically working with feedback loops. And then because of that, you have multi-loops. You may be actually causing the problems that you're facing. So to illustrate this, let's consider the case of a couple, Sam and Pam. So we see that Sam is behaving very badly, and this leads to the hurt feelings of Pam. This is an exogenous point of view in which we are only seeing just one-sided errors. But a more complete view would be to think, what are the feedback loops? And it may be, if we take an endogenous point of view, where endogenous means originating from the inside. It is originating from the inside of the system. So maybe there is something that Pam is doing which is causing Sam to be mean, and this is working both ways. So we see that earlier we were just focusing on this. But when we take the endogenous view, we see that both of the people are causing the problems they're facing, while at the same time only blaming the exogenous factors. Some tools in this domain, there are many tools, and there are many schools of system science. You might have heard of complexity science. That is also dealing with systems that has parts, that has the behavior of emergence because of the nonlinear interactions. We have qualitative tools as well as quantitative tools. So with qualitative tools, we build complex webs of feedback loops in which the basic building block are just three things. It's a reinforcing loop, we have a balancing loop, and we have delay elements. And we can then model the interaction, the interrelationships of subsystems rather than just study the things in isolation. But with this, you only have a qualitative insight, and obviously this thing is never finalized. It's open to reiteration and improvement, but this causes you to think about how you're influencing other things rather than just focusing on one thing. We can also make it quantitative by integrating what are known as stocks and flows. You can have differential equations. In fact, the science is grounded in control theory and the modern theory of nonlinear dynamics. And like I've mentioned, it has been developed over 50 years or more. It was started in the 1950s at MIT by Jay Forrester's group at the Sloan School. Finally, coming to the third part, which is the use of systems thinking for the internet and for the future AI-driven self-driving networks. So in the paper that Jen and Nick Feimster wrote on networks that must drive themselves, in the abstract itself, they are highlighting things that would be very much aligned with the things I've just mentioned. So for example, you need to have high-level policy goals and a holistic view of the underlying components. You need to have real-time closed-loop decisions. These are things that another community has been studying for a long time, and the point of this paper is just to highlight the insights from there and to initiate some work to study, because for self-driving networks, the human aspect will become more and more important, the ethical issues, the security issues. As highlighted in the paper, we've referred to a paper by Keshav, who recently wrote a paper called The Paradoxes of Internet Architecture, in which he said that the internet was designed according to certain goals. And these are the goals which are listed in the order they were assumed. And it's written there in the original paper that if we were to just change the list, the design would be different. So Keshav argues that many of the problems that we see today, spam, privacy, security, quality of service, the failure to provide quality of service, actually stems from the design choices, because as is an axiom in systems thinking, systems are perfectly designed to do exactly what they're achieving. So if you see problems, it is because of the system and the underlying structure. And you cannot resolve those problems without fixing the underlying structure. Once we draw the underlying structure, the systems thinking field has many templates that we can match against. These are known as system archetypes, and some examples of misbehaving systems are presented. Fixes that backfire, they solve a problem in the short term, create bigger problems in the long run. Like network address translation, for example, it fixed the symptoms without actually changing the underlying systemic cause. Limits to growth is improvement accelerates in the beginning, but it suddenly stalls due to some constraint. Shifting the burden is to have addictive short-term solutions without going to the actual long-term solution. These are all archetypes that are well known. Tragedy of the commons, it's observed often in networking environments. Success to the successful is important because of the various ethical concerns and the concern that some corporations are becoming very dominant and they are playing a big role. So we don't want them to influence everything because that may create issues. To finalize things, just to highlight, the ethical and security policy issues are very much amenable to a systems thinking study, because these are the kinds of study people have been studying in the management sciences, because as has been shown in recent work, even algorithms make ethical choices. And so we must not be blind to that. There's a book, Weapons of Math Destruction. And then the question is that who will take the ethical decision? And once we give the role of taking the decisions to the network, and if it's taken an ethical decision, who has the agency? Who is responsible if some minority or if we are following up on some stereotype? So we may be taking a wrong decision, and we must, for a democratic, free society, we must have some checks on that. Also, when you intervene in a system, you cause many problems. In fact, in medical science, there's something known as iatrogenesis, the problems that the doctor gave. So if you are curing someone with a medicine, it will probably lead to many more problems. So in a similar way, when you have an intervention, it may be, for example, designed to optimize your performance, but it may create more security risks, more privacy risks, and so on. So to conclude, I feel that in the book we have, in the paper we have communicated that system thinking is a useful tool for studying networks in general, but also networks that incorporate AI and self-driving networks. And we need to study both the effects. As the first talk also highlighted, there are potential negative effects, and also we can use it for lots of advantages as well. So that is the end of my talk, and I'm happy to receive any questions.
Thank you. Okay, so we have time for a quick question while the next speaker sets up. Patrick, are you here to? Oh, perfect. Yeah. Anyone have questions or comments?
So each time I hear in this context of complex adaptive systems theory, I cringe because I doubt the value of that sort of systems thinking as applied to engineered systems. So engineered systems, I think, are very different from the sort of type of system these studies have been looking at, and are missing out on essential pieces that are critical for engineered systems. And I haven't seen anything that convinced me to the opposite.
Right. Yeah, that's a valid opinion, and perhaps it's true that most of the application of complexity science and systems thinking has been in the fields of management rather than in engineering systems. But having said that, there are many tools that we can use, and you never know, they may be very useful. For example, complexity science has agent-based modeling, which is a tool that you can use and people are using for wireless networks, and we can never predict how it will go.
Great. Thank you. So our next speaker is Patrick Kalmbach, who studies computer science at the Technical University of Munich. And his research focuses on artificial intelligence, including reinforcement learning, stochastic optimization, and probabilistic modeling of communication systems.
So thank you for this nice introduction, Jennifer. So yeah, I'm going to talk today about empowering self-driving networks, and I hope you will see at the end of this talk what this is about. And first of all, self-driving networks, what do you mean with it? And it has nothing to do with cars, and I actually got this question a few times in the last days. So it's more about networks that use measurements and data analytics to control themselves, to really make decisions on their own without the need for human intervention, or at least taking the human intervention a little bit out of the loop. Why do we need this? So if you look at a current situation, we see that we have a human operator. He looks at data measurements, and he uses this then to take control decisions. And at the moment, this works. So the system works. It worked also previously, and it might also work in the future. But if you look at, for example, current trends in what we can do in traffic engineering, we see that we have here increasing complexity also in the control decisions that we can take. And now the question is, what happens here? At what cost can we keep this system that we have at the moment? At what cost can we keep this running? And now if we look into, okay, maybe we can use a machine to actually make those control decisions, when we might ask ourselves, okay, this is probably related with a lot of high risk. So what does the machine, how can we verify that it does things right? What about if it does just stupid things? How to verify this, how to build this? So this can be quite hard. So there is maybe a huge initial threshold that we have to overcome, but there might be a point where this is actually worthwhile to look at. So there might be a point where actually machines can outperform humans. So what we want to look at today is the use case of reconfigurable topologies. In this case, you can have, so each node can connect to every other node potentially, but there is a certain degree constraint, so you can only connect to so many different nodes at a time. So what you can do with this is basically you can have, for example, a ring, you can have a topology like this, but you can in this case not have an all-to-all connection because you have here a degree constraint of 2, just like for illustration purpose, or you can have also parallel edges. And we think that to use this freedom that you have here in this scenario, here you really have to use automated control, especially for real-time decisions, because humans will not be able to cope with the huge complexity of this configuration space. And what is the configuration space, and what do we expect from self-driving networks in this context? Well, here you see, for example, all the different topologies you can have in a free node network. Now there might be a request that you have to serve. So you have to make sure to actually serve this communication between those two nodes. If this is requested, you have to meet the requirements that might be associated with this communication. There might be SLAs, there might be other requirements that you really have to meet. And still, you might be left with some headroom. In this case, you still have two edges with which you can play around. And if you think about an online scenario where requests come and go, then there might become new resources available. You might take up new resources, and then the question is, what are you doing with the spare resources? How can you maybe also make something useful out of it so that you later on can easily accept more requests? And if you look now in this case, we have, for example, those three additional topologies that we can form with those two headrooms. And now our requirement to a self-driving network is to use this headroom in an intelligent way. So now I did it. I used this I word that is thrown around a lot lately. But it's not always clear what intelligent, acting in an intelligent actually means. So what do we expect of intelligent actions? And I don't know or can't really say. And it's also ongoing to like philosophical debate, which has a long history. But there are a few people that look really into this, and they looked at living organisms, and they saw that they strive for states and positions where they have a lot of future options. And they may also take momentarily disadvantages into account to just reach those states with higher future possibilities. What does this mean in our case? So again, we have our free node network. We have this edge that is already taken up. Now we can, for example, say, okay, cool, we place this additional edge. So now we can, if now a new request comes in, we can only, for example, serve immediately an additional communication between those two nodes. And if we have like a request like this, we would have to do a reconfiguration. If now the network places the additional edges it has in this way, it can basically serve all possible requests that could come up in the future without having to do any reconfiguration at all. So that's basically what we would say, okay, this is what it means to be prepared for the future. And this is what we would say also kind of interpret as an intelligent behavior. But how can we formalize this notion of preparedness? And this is where empowerment comes into play. So empowerment is an information theoretic measure that quantifies how much control an agent has on its environment. It was formalized like 10 years ago in the robotics community, and it works like this. So you have an agent that lives in an environment, which looks in our case like this. We have our network, we have a request in it, we have the edges, and now you get a sensor reading out of this. So the agent perceives a part of this environment. In our case, for example, it just sees, okay, I have a request here. That's all it sees, nothing more. Based on this sensor information, it might take a certain action. For example, okay, now I'm placing this edge here. There might come in some new requests, some additional things that the agent cannot really influence. It has no impact on this. And this leads then to a new state of the environment, which then triggers a new sensory input, which triggers a new action, which triggers a new state of the environment. And now you see basically in this caution-based network that the action the agent took at a previous time step might have an influence on actually the sensor input it has on the next time step. So it kind of can send information through the environment to itself. And that's exactly what empowerment is about. Empowerment tries to maximize this information. Basically, the agent tries to maximize the information it can send to itself via, through its actuators via the environment to its sensors. And this is the notion of preparedness that empowerment uses. And this is done by maximizing the mutual information between the action that you take and the future sensor reading. This sounds somehow a little bit confusing and might be at the beginning hard to grasp, but it has been shown to actually really lead to behavior that we would immediately label as intelligent. And now, what do we see here as advantages of this empowerment thing? So it's first thing, it's agent-centric and it's local. So this means that it can be computed only by looking at the information an agent can actually obtain. You don't need, for example, a complete world model. You don't need to specify the network in detail, how it works, how it acts. You only use the information that can the agent see through its environment. It's also semantically unbiased. You do not impose an external reward system. You do not tell the agent what is good or what is bad. This is only based on this empowerment framework, and this also makes it somehow universal. So you can use this framework, you can use a specific setting in a data center network or in a wide area network. On the other hand, what you still need is a model that tells the agent how its action can actually influence its sensor. And this is not the same as a world model. This is not telling the agent how exactly a network works. But still, it's usually not there. You don't have it. You can learn it from data. You can also use model-free approaches. But here we also have still a lot of open research questions specifically for networking. What do those two things mean in networking? So here we can really have a deeper look at. So now I want to talk about the experiences that we had or the results that we obtained when applying this empowerment framework to reconfigurable topologies. So the actuators that we considered were placing an edge, removing an edge, and doing nothing. So the agent just leaves the network as it is. We have had a look at, or have a look at two sensors here. The one is the number of routed flows in a timestamp, and the other one is the set of routed flows. So basically, this one is much larger than this one. And what the agent now tries to do is it tries to greedily maximize its empowerment. And this is basically the result. So here you see the nodes, and on the left, right side here you see empowerment, and now this is actually a log scale. And now what's happening is that the agent at the beginning greedily places edges, a lot of edges, just totally random, but this enables him at the beginning to actually, for the first time, get observations. What's now happening what's happening next is that the agent places even more edges, and when it starts to somehow restructure the edges. And it does so to further increase its empowerment, and at some point it reaches a kind of a steady state. It's around 350 time steps, and after the state it cannot increase empowerment any further, so it's kind of reached a portion of this configuration space that is somehow reasonable or somehow good for this agent. So maybe it's graph isomorphisms, it's somehow similar topologies, we didn't really investigate it, but what the agent did is basically it was able to rearrange the edges, restructure its environment in a reasonable fashion. And the end result of this is, so we compared the topologies we created with this empowerment approach with the topologies we created with a robust optimization formulation and a corresponding simulated annealing heuristic. And here you see the relative performance to this robust optimization formulation. And here, the two empowerment versions that we presented here basically were significantly a lot better than simulated annealing, and also better than the topology generated with this robust optimization formulation. So in summary, what we have seen so far, what we have showed so far is that an empowerment-driven agent is able to actually create a good topology only by taking this action perception loop into account. The lessons we have learned on the way is especially here, this empowerment versus intrinsic goals, really hard optimization statement. So we discussed a lot about this, we thought a lot about this, what does it actually mean, what does it refer to, and we came to the conclusion that empowerment can be used really as a secondary objective. So you have your hard constraints, you have the things you really have to achieve, and then you can maybe use empowerment, really like we proposed here, to make use of the headroom you have. Also, what we saw is that if you have very high-dimensional state spaces, high-dimensional action spaces, this framework has its problems, similar to when you have reinforcement learning. And what we want to look at in the future is, for example, empowerment as a universal utility function. So if I now use empowerment to manage my headroom, what impact does this have on quality of service measures, for example? Are they implicitly also optimized as well? We don't know. We want to investigate. And we also want to look at sensor evolution in communication networks, basically use empowerment to obtain or find out what information we actually need to obtain a task in a good way, or what information we potentially could need to obtain a good performance. And we also want to look into unsupervised learning of control strategies. That's it from my side, and I'm happy to answer all your questions. 。 . 。 。 。 . 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。
。 . 。 . 。 . 。 . 。 . 。 .
。
While the next speaker sets up, any questions?
So it almost looks like this empowerment is somewhat related to a notion that people look at in sort of systems design that aims for evolvability of a network. So you build a network and in a way that hopefully is able to evolve to future configurations that you have no idea really what you are aiming for, but the system is flexible enough to get you there in an efficient way, and you don't have to completely redesign everything from scratch to get to your endpoint. Is this related to this?
Yes. So it sounds like this is related to the topic. I'm not sure the formalism were used to achieve this. So in this case, the cool thing is that you have operate over this perception action loop, and in this way are able to define actually.
I mean, you seem to have this metric seems to help. I mean, seems to give you a quantification for how you get, and that seems to be not there in sort of the generic setting. But from a design perspective, there is this goal to design systems that have this property.
Yeah. Yeah. So the idea is the same. Yes.
Okay, let's thank the speaker. Thank you. Here, the last talk of this session will be given by Arthur Jacobs. He's a first-year PhD student in computer science at the Federal University of Rio Grande do Sul in Brazil, and his research interests include network management, network function virtualization, and artificial intelligence. And he's going to give us a talk on refining network intents.
Thank you, Jennifer, for the introduction. Hello, everyone. Good afternoon. So let me put this a little bit up. Okay. So I'm here today to present our work on refining network intents for self-driving networks. So as it's been said here today, a self-driving network is a network that ideally runs itself. However, to do that, it first needs some guidance or guidelines on what to do and how to operate. So that guidance is what we call here in this high-level architecture an intent. Of course, that intent means a high-level descriptions of what the network should do without worrying how to do it, okay? So, of course, that intent has to then be processed and turned into proper network configurations, which, of course, a self-driving network would then monitor itself, collect data, use the data to learn, and adapt. So the focus of our work is this first part right here, which is deploying network intents. Well, nowadays, if we're talking about traditional networks, you could probably represent an intent using traditional command line interfaces, and which is very hard to do, very hard to manage. If we're talking about programmable networks, you can probably use OpenFlow or P4 programs to specify some behavior, which is still a method very prone to mistakes and very hard to do, which is why many have proposed high-level network programming languages, such as PGA, Janus, which is an extension of PGA, Netcat, or Cocoon, which still put a lot of strain in network operators, because each time they have to learn a different complicated network programming language. And so what we thought, our intuition was, can we go a step further and use natural language to do that? And so we asked ourselves, how could we deploy network intents expressed in natural language? And to do that, we proposed a network intent refinement process using NIO. Our main idea of our process is to use natural language to express the intents, but since using natural language can be cumbersome, we use a second intermediary step with NIL. NIL is a network intent definition language, very simple and very easy to read. We designed it specifically to ask for confirmation from the operator to guarantee that the intent being deployed is exactly what the operator wants. And so to give you a little bit of better sense of what our process is, please consider this example. We set up a small experimental scenario using Mininet and Sonata NFV. Sonata NFV is a framework for chaining network functions. And so in this small example, we have like an iPerf client and a traditional HTTP web client communicating with two distinct servers over two OpenFlow switches. And consider now that in this example, a network operator wants to deploy the following intent. Please add a firewall and a intrusion detection system from the iPerf client to the server. Well, to do that, the network operator would only need to reach a client that is either his smartphone or a computer and type that intent into a Google Assistant, for example. We're using Google Assistant as an example here, but it could actually be something like a Facebook Messenger or Google or Amazon Alexa. And so attached to this Google Assistant is a chatbot interface we developed using Dialogflow. Dialogflow is a Google proprietary tool to develop conversational interfaces for multiple platforms. And so we take advantage of Dialogflow to extract the important information from the speech. In this case here, firewall, IDS, the middle boxes the operator wants to chain, the origin and the destination of his intent. And so these extracted entities are then sent to the intent translator, which is in fact a sequence-to-sequence learning model using recursive neural networks. This sequence-to-sequence learning model receives as input all the intents, all the entities extracted from the intent one at a time, and outputs then a fully fledged Nile intent. And as you can see, Nile is very easy to read. You can clearly see what are the endpoints involved and what are the middle boxes involved. So even though a network operator may not know the syntax, it will still understand what it does. And so after, of course, this intent is then presented to the network operator to ask for confirmation. And at this point, the operator may either reject or confirm that intent. And we use that feedback to incorporate it in the sequence-to-sequence learning model so that the system improves over time using the operator feedback. And so we then, of course, having confirmed the intent, we then send it to the intent deployer, which is responsible for compiling and deploying that intent into an actual network. And so in this case, we developed a simple NIO compiler to Sonata NFV commands. But of course, ideally, this would be a fully fledged compiler for any destination network such as P4, OpenFlow, or things like that. But so here, okay, the intent deployer compiles the intent into commands and then finally deploys into the network, giving us the final result here, in which all the traffic from the iPerf client has to pass through the firewall and an intrusion detection system before reaching the server. And so to evaluate our proposed solution, we focused on two main aspects. The first one was the accuracy we could achieve with different sizes of data sets for the sequence-to-sequence learning model. And the second one was the impact the feedback has on the accuracy over time. And so to do that, we used 5 different data set sizes with 100, 500, 1,000, 2,000, and 5,000 entries of pairs of entities and output Nile intents using a 20% validation split. And so each of these data sets were generated automatically using different combinations of middle boxes, endpoints, traffic matching rules, time, QoS metrics, and all operations supported by Nile. So regarding the first aspect, we can see here that for data set size of 5,000 entries, we get a sufficiently good accuracy in the translation process with very small confidence interval. But for 2,000 and below, we don't have a good enough precision. And so in these cases, what would happen is that the sequence-to-sequence learning model would generate a lot of syntax errors in the Nile output intent. And so, but also you can see that to train that 5,000 entries dataset model, it took almost 3 hours. So a considerably large amount of time. And so considering the second aspect, that is the feedback, we can see here that we did 30 rounds of feedback for each of the dataset sizes. And we can see that regarding the dataset size, the feedback improved considerably the precision of the model, especially for lower dataset sizes. For example, you can see that for a 2,000 dataset sizes, And 20 feedbacks, we achieved the same accuracy and precision as with the 5,000 data set size. And so to sum it up, to summarize, we posed the question how to deploy network intents expressed as natural language, and we proposed maybe an answer using our refinement process in NILE for confirmation, which is a process that requires very little technical knowledge and uses feedback from the operator to learn over time and improve. But of course, this is still ongoing research, so we still have a lot to do, such as fully implementing of NILE compiler to any destination network and further evaluating the end-to-end proposal. So that's it. Thank you.
Great, thanks so much. Do you have any questions from the audience? Yeah.
Hi, yeah, very interesting talk. So
thank you.
I have very little knowledge about machine learning, but yeah, are you saying using your proposal, you're trying to use machine learning to allow like user to specify very general goal and you will use your compiler to automatically generate code? Is that what you're...
Yeah, that's the general idea. Like extracting information from natural language and turning into finally network configurations.
Okay, so user or like programmer does not need to have any domain-specific language, domain-specific knowledge to do that.
What do you mean, like about the topology?
So
or?
If in your example, user said, I want to several like firewall or something from one source to one destination,
Sure.
And then for this sequence learning process, what exactly does it do?
It takes the sequence-to-sequence learning model takes the extracted information from the natural language, which is the middle box. The middle box is involved, and actually translates that into a NILE intent, so we can present it to the user.
But can you go back? Maybe go back to the example page, if it's possible.
Which slide?
Yeah. So on the left, this is a compiled NILE intent. So this is transformed from the language through the intent translator translated into the okay. And this is the compile. Okay, I see your point. So, but in this way, if there's a network state change, how would this intent? Would that be automatically updated or?
Well, ideally, yes. This is just like a tool to deploy intents from the network operator. But if the network changed, then a self-driving network ideally would adapt. But we didn't tackle this in this work.
Okay. Yeah, regarding the network automatic update, yeah, our group has a Trident paper on the Ming conference. You may want to take a look at it.
Sure.
Something similar or shared feedback.
Sure.
Thanks.
Yeah, thank you very much.
Okay, great. Let's thank the speaker. Okay, so that's the end of the first session. We have a break now. We ran a little bit over, so we're going to have about a 15-minute break instead of a 30-minute break. So we're going to reconvene at about 3:45 for the next session.
I can say.
Okay, let's get going so that we can finish in time. So we have the second session of this workshop. Again, we have 3 talks, 10 minutes plus hopefully 5 minutes of discussions where people actually ask. And so it's my pleasure to introduce the first speaker. First speaker is Danny Chen. Danny is a first-year graduate student at Princeton, working with Zhang, and he will tell us about microbursts.
Thanks very much for the introduction. So for a network that can drive itself, we need a switch to detect and correct some problems by itself. For this paper, we try to tackle a particular kind of problem in network, that is the rapid build-up queue, or microburst. We want a switch to detect microbursts and who caused it. And so we may take some immediate action to correct the problems. So first of all, what is a microburst? So in normal cases, the packet flowing to the switch relatively slowly or slower than the outgoing rate. So the packet buildup or the queue buildup is minimal. However, in some cases, the packet could burst into the queue. That means like the queue will build up and then it will have higher latency and packet losses, and then the burst could be gone. This phenomenon could be very short in the microsecond time scale, and then later on the queue will just grow short. So if we look at the packet or the queue length over time, we should see this pattern that in normal cases the queue is actually relatively short, but in some very rare cases the queue can grow very long, and then immediately it will just fall back. So we call this phenomenon microburst. Microburst is well known to exist in data centers. However, we may be surprised to learn that microburst also exists in carrier backbones. This is a 24-hour queue length record taken from an internet backbone switch from a major carrier. As we can see, there are 3 microburst incidents over a 24-hour period. Well, this doesn't happen for every link, and this doesn't happen every day, so it's really hard for us to catch this already. Worse, we need to zoom into a smaller time scale or zoom into data plane. At microsecond time scale, any human intervention will be too late, or even talk to a remote controller may be too late for us to take action. So we know microbursts exist everywhere, but why do we care? As network administrators, we often have several conflicting goals. First, we want to avoid packet loss, especially those caused by congestion. Second, we want to use cheaper switches, which means we have shallow buffers. And thirdly, we want to run the network at higher link utilization, so we can save some costs as well. And finally, we want to support bursty workloads. We can't just ask our clients not to send bursty traffic, so we have to support them. It sounds impossible to achieve all these goals simultaneously. As a first step towards all these goals, Snappy tried to identify the flows responsible for microbursts and enable evasive action to be done in data plane and protect other flows. Yeah, we try to make it possible. So the first question is, who caused the microburst? So if we want to identify the flow that caused microbursts, we need to know the relative flow size in the queue. So for example, if this is a queue and these are all the packets, we want to know that the packet in green flow have 5 packets in the queue and packet in orange flow have 2. This is already a very hard question. Snappy tried to answer a simplified version. That is, if a packet belongs to a heavy flow, that is whether one packet belongs to a heavy flow, and also we only care when the queue is very long. However, even a simplified version of question is really hard to answer, and let's see why. So say that we maintain a strawman solution. We have a table for all the flow sizes. So when the packet enters the queue, we can add a counter, and then that's easy. And then when the packet leaves the queue, we want to reduce the count. A new packet coming in, we add the count. This creates a problem for us. Because packets are leaving and coming simultaneously at line rate, we need to maintain some data structure in memory and access to this memory from 2 ends of the queue at line rate. This is very hard for any hardware. Snappy tried to solve the simultaneously add and delete problem by using snapshots. So let me try to explain what a snapshot is. Each snapshot will record a very short period of traffic, and then we merge different snapshots together. And we never delete from snapshots, we only add them. In some sense, we're forgetting about the oldest snapshots, which means we're batching deletion. As a quick example, when a packet goes into the queue, we will add a packet to first snapshot. And then when another packet comes to the queue, we can add it to another snapshot. So in this example, every snapshot would hold 3 packets. So when the packet leaves the queue, we do nothing. Again, we are using add-only snapshots in this case. And so the third packet comes in, we add to the snapshot, and now snapshot 1 is full. We can start to add to snapshot 2 and 3 and so on. So say that we have a burst, and quickly we fill 2 snapshots. So now this packet comes in, and then you add itself to the snapshot and enter the queue. And now we realize, well, the queue is sort of long. It's above a watermark. It's above a threshold. So we want to care about, okay, who are these packets? Or which flow are a majority in these packets? We can't really answer that. We can answer this part approximately by using these snapshots. So say that when a green packet, this snapshot corresponds to this part of the queue, and this snapshot corresponds to this part of the queue. So we can make some approximated judgment. So say that another packet, so based on the snapshot, we can have approximate count. Another packet comes to the queue. It belongs to the green flow. We first add to the future snapshot and put into the queue. And then we realize, there are like 8 packets ahead of me. A was approximately 6, so we should look at 6 divided by 3. So we should look at 2 snapshots. And then we get the number 5, which is my flow size. So 5 is pretty large, so I am a large flow. I'm hurting others. So maybe this packet, we should do something about it. We can mark it, we can drop it, maybe we can report it to controller, or take other sophisticated actions. Again, this result is available before the packet leaves the switch, so we can take some action within the data plane. So there are 2 observations. The first observation is when the queue is long, we have lower relative error. That's because we have this quantization effects at the end of the snapshots, but because if the queue is long and the snapshot is shorter, we will have higher accuracy. And secondly, because we only care about heavy flows, not every flow, we can use approximated data structures like sketches inside each of these snapshots. There are a third observation here, that is we don't need infinite number of snapshots because the total buffer size or total queue length is bounded. We have only a limited number of snapshots we need to look at. So we only need to maintain, say, edge snapshots and then round robin between them. Say that we have edge snapshot in this case. Now we are writing to snapshot 3. So all these snapshots are full, only 3 is empty. When the new packet arrives, we could put it into snapshot 3 and also erase the oldest one. And then new packet comes and old packet is gone, new packets are come, old packets are gone. So at the end of the day, snapshot 3 is full, but snapshot 4 become empty. Now we can shift the rows of all of them, and we can start writing a new empty snapshot again. This way, we can only use a very limited and constant memory size in the data plane to achieve our goals. Now we show some evaluation result about Snappy. So in this figure, first we try to evaluate the accuracy of this system. So in the y-axis is how precise can we capture the heavy flows. Here by heavy, we define it as any flow occupy more than 1% of the queue size. In our data center trace, that's a significant number. So if Snappy reported some flow that is supposed it's heavy, we'll compare it with the ground truth in our emulation and see whether it's truly heavy. X-axis shows the memory size per snapshot. That is how many counters in the approximate data structure or coming sketch we're using. We can translate that by 4 bytes per counter if you wish. As we can see here, on the top we can show that if you have 128 snapshots, which is a lot, you could almost perfectly identify all the heavy flows. But that's too much for today's programmable hardware. However, even if we're only using 4 or 8 snapshots, given enough memory, which is not a very large amount of memory, we can already achieve a very decent accuracy in achieving our goal, finding heavy flows. And by the way, 4 or 8 snapshot is completely achievable in today's programmable hardware. Furthermore, we want to also look at Snappy, whether it can also report flow sizes for small flows. Remember that we don't only care about large flows. Maybe we can also get flow size for small flows to see the flow distribution or other metrics. Here we plot on x-axis the actual flow size in the queue for every flow, and y-axis is the estimation. So as we can see, we have very low absolute error, less than 50 kilobytes per flow. It could be very large relative error because there are a lot of tiny flows. But as long as those tiny flows are not mistakenly reported as large flow, then we should be fine. And for large flows, we can see this interesting quantization effect. That's because we are only looking at integer number of snapshots, so either 3 or 4 or 5, so we can have this laddering effect when reporting large flows. So in summary, Snappy tried to avoid the problem of simultaneously add and delete by using different number of snapshots and merging them to query. Although in our programmable data programmable data plane devices or programmable switches, we can do only limited computation. We can use these approximate data structures to try to avoid these limitations. And finally, because microburst is really short, we really want to capture them, we have to do it in data plane. Snappy enable us to capture the microburst in data plane, find which flow is causing them trouble, and then take immediate action in the data plane. Some of our future works including the continuous process of deploying the Snappy into the carrier backbone switch to really figure out who is causing the microburst in the backbone. And also, we're considering varying the queuing model to include non-FIFO queues, like priority-based scheduling. And also, we are thinking about variations on flow statistics, such as what if it's a group of flows, not just single flow that cause the burst. And also, given the measurement of Snappy, it enables us to do a lot of different actions, like weighted actions. So for example, if you know that you are 50% of the queue, maybe you can drop these packets at 50% probability, or maybe the square root of 50%, or maybe the square of 50%. This kind of issue can also enable us to have more sophisticated congestion control and congestion avoidance. I'll conclude here. I'll be happy to take any questions. Thank you.
Okay, do we have any questions? Yeah.
Andreas, to Munich, could you elaborate a little bit more again? First, thank you for the talk, but could you elaborate a little bit more again? Why do you have to do this division into these small snapshots? So from this statistical point of view, why not, just for my understanding, thank you.
Yeah, thanks, that's a good question. Basically, if we don't divide them into smaller snapshots, only large ones, then because we cannot do delete from the data structure, or we can't operate from two ends, we need to have the smaller quantizations such that even if we don't need to do deletions, we can approximate the different lengths of the queue by looking at different number of snapshots. If you only maintain the very large ones, then whenever you are query on a large interval. We cannot choose from, like, say, 1, 2, 3, or 4. You can only say either it's 10 or 20, or maybe you can only look at 10. Right now, if queue length is different, then we can look at different snapshots. Yeah.
Anybody else? There we go.
Way back from the Microsoft, let's talk. So to the best of my knowledge, there are actually many microburst detection products, such as Deep Insight from the Barefoot Networks and Broadview from the Broadcom. So what is the uniqueness of your solution?
So basically, existing solutions can tell you microbursts exist, and some flows suffer from it, but they are not really trying to answer a question about who caused the microburst, or which application is causing the microburst. So they can allow you to see the figure that I showed earlier. So basically, you can see all the figures about, like, the queue length goes long and fast short, and it tell you every flow how many congestion it suffered. But it's not really telling you who caused them or which flow is causing others to suffer.
Okay. Thank you.
Thanks
Thank
again.
you. Thank you. Okay. The next speaker, please come forward. So the next speaker is Jin Wu. Jin is a lead engineer at Alibaba Group and leads there the network modeling group. And before that, he was at Big Switch Network, and he will talk about Netcraft.
Thanks a lot for the introduction. Good afternoon, everyone. So I'm Jin from Alibaba. So today, I'm going to talk about how does Alibaba actually manage its network configurations. So this is a joint work with many of my very hardcore software and networking engineers in Alibaba. So first, let's look at what Alibaba network look like, daily operation look like. So right now we have like tens of vendors across the network, from the top of rack to all the way to the backbone core routers. So now we have like tens of data center architectures and backbone architectures, different versions. So they are all running in production in parallel. So currently we have like daily regular network updates. So the reason for that is because we have like a network expanding every day, and also we have like architecture change frequently. So that's why we have that. So first, let me give you guys an example of what does network update mean in Alibaba. So here is the example. So we have 2 data centers running in the same city. That's DC1 and DC2. So all of them are connected to a one router. That's the setup. Each of them has different AS numbers. So basically they run eBGP between each other. So here the arrow over there means the direction of the BGP updates. So that's the initial update, initial setup. So with this setup, we can tell that both the intercity and the intracity traffic is all carried by the one router. So it turns out this to be bad. So the reason is because the call router, the one router, the interface on the call router is very expensive. So in this case, we kind of wasted the call router interface to carry the traffic within the same city. So to make things right, we are going to update the network. So what we do is like this. So we insert another switch, a relatively cheap switch. We put it in the middle and make the connection like this. So the consequence of this is all the intracity traffic now is carried by the main switch, but the intercity traffic is still carried by the one router. So that's what we were doing. So what we did was we kind of automated this entire process. So we made the automation from the initial state all the way to the target state. So how did we do that? Let's take a step-by-step walkthrough. So this is the initial state. So in this picture, again, the arrows stand for the BGP update direction, and the dotted red line stands for the bidirectional traffic. So at the beginning, all the intercity and the intracity traffic is all carried by the one router. That's the initial setup. So the first step we did was, we started to pair the main switch with the call router, with the one router, and with the data centers. And at this step, we only announce the routes from the DC to the main, and then main to the one router. That's the direction. So with this setup, even though we have this new peers, but actually this new main doesn't take any traffic, simply because it's one is unidirectional, and another thing is it has a longer AS path. So at this point, the traffic is still like this, remain the same. So the next step, we started to do more things. That is, we started to announce prefix routes from the one all the way to the DC. Now this part, the part is okay. So with this setup, the traffic goes slightly different. The intercity traffic is still carried by the one. However, the intracity traffic, because of ECMP, now is carried by both the one router and the main switch. Okay, so remember, so the next step is it's kind of not that intuitive, but it's still easy to understand. Is we started to prepend AS in the AS path between the WAN and the data centers. So we make the AS path longer. So after we're doing that, all the traffic starts to shift to the MAN. And so at this time, everything is fine. It's okay. Now we started to remove all the neighbors between the WAN and the data center, and that's it. So that's a high-level walkthrough of what we were doing. So, but if we look at it in a more abstracted way, what we were doing is actually something like this. So the operator, instead of making configurations to the network gears directly, they started to, right now they are working on the network models. So they change the data structure, they change the data in the network model. We call that update intent or design intent. So after that, the system is gonna come up with a transition plan. So everything, the transition plan is generated automatically. So in parallel, there is also a configuration generator which takes a few modular configuration templates and generates the transition configurations. And we put them together, fit it into the configuration executor, and then conduct the plan in the network. That's what we were doing in a more abstracted way. So in this talk, I'm going to focus on this configuration modular template. and the network model. So let's first look at the configuration modular template. So there has been like tons of works talking about how to manage configuration, how to modularize the configuration. So we are doing it in a slightly different way. Let me explain. So the key message I would like to deliver here is first, in Alibaba's network, incremental configuration update is a must. We have to do it. Second is like modular configuration plus action is a must. So the second part is kind of confusing. So the first sentence is easy to understand it because like we have already talked about it. So the second part, I'm going to explain what does it mean. So in this previous example, what we did in the first step is we activate the new neighbor. So basically that means we configure a whole bunch of BGP peers and policies in the configuration on both sides. So that's what we do. But forget about all those peers and policies. What matters is actually just one configuration. That is neighbor peer IP activate. So only after we type that, so this piece of configuration will take effect. So we call this configuration snapshot is called a peering, but what matters is the action. So not only that. So for example, in the third step, we actually prepend the AS in the AS path, right? So, but we cannot just blindly prepend the AS, that's it. We cannot do that. The reason is we have to wait until the network converge and check if that configuration actually take effect or not. So we actually have this it's also related to this BGP peering module, but the action is a check. We need to check if it's effective or not. So last but not the least, so in the very last step, we have both deactivate, which is we deactivate the BGP peering, and the undo, which is clean up all the redundant configuration in the very end. So currently, so right now I just gave you like a few examples of action together with configuration module, but actually there are more actions in our implementation. So this is the modular configuration. A natural question to ask is, how do you define a module configuration? So the short answer is simple. We would like to have an atomic operation, and that atomic operation is our module. So a more complex answer is, I would say it like this: a Cartesian product of protocol and the configuration block. So again, this is not that easy to understand. So let me explain. So this is a very straightforward configuration for interface. So I use different colors to represent different protocols for this interface. So if we break down this piece of this configuration block, it actually consists of 5 parts. So the first part is we need to assign an IP address to this interface. That's part 1. Okay. On top of the IP address, what we did is what we have is we need to have an interdomain routing protocol, which is ISS in this case, and we also have a BGP related configuration. That is, we need to put this interface into a particular VPN. Okay. And on top of that, we also have QoS related configuration and also ACL. Okay, so right now we can see, given a configuration block, which is usually separated by this hashtag in like a vendor switches, so we actually break them down into different modules. So even just for this piece, we broke them down into 5 modules, and multiply the action I talked before. It's actually there are many modules in our system. So now I finished to talk about how do we manage the configuration modular templates in our system. So the reason I talk about this configuration modular templates first is because that's the very root reason for the design of the following system. So now let's go back to look at the network model, the actual network model. So in the network model, eventually we pick a hierarchical network model. So what it means is we break the network into layers. So on the very bottom, that's a physical layer. So in this example, we have 2 data centers, one router, and they have links connect to each other. So that's a very basic physical model. And on top of that, we have an IP graph, which we assign IP addresses to different interfaces. And we also have pod channels, which multiple links are served as one giant link, and they share one same IP. And on top of that, we have like a protocol layers. So we have this, we break the network into these layers. So this is actually a very, very natural deduction from the modular configuration, because for every module configuration in my previous slides, they have a counterparty here in this hierarchical model. They have like almost a one-to-one mapping. Okay, so also this model is aligned with like operators' understanding of the network, so it's very intuitive and easy to understand. So that's our model. So, so given that, for the rest of the system, okay, please read the paper. We briefly discussed the high-level idea, the design of the rest of the system. But now I would like to discuss, people will ask, what's the difference between this netcraft, your system, and OpenConfig? So actually, we leverage OpenConfig a lot. We use OpenConfig as modular configuration for some of the vendors. However, we are also making like improvements for OpenConfig. So what we are advocating in the OpenConfig community are 3 things. First of all, we emphasize that please structuralize the network, not an individual device. That's what's missing, like in current OpenConfig. So another thing is we desperately need the explicit atomic operation support, which means either you do you finish this task or you don't. You don't like end up in the middle. So the third thing is, so almost all these standards tries to you know, hide the vendor diversities. That turns out to be a big problem for us. So rather than that, we advocate that we should explicitly manage vendor diversities, don't hide them, because all the very worst accidents happened because of this. Okay, so this system has been deployed in production for a year. So these are some high-level like stats. So first of all, right now in Alibaba, 73 of the network updates is done by this system. So right now, the incidence probability due to configuration update decreases by 18 times. So in terms of agility, the time to conduct a configuration update decreases from hours to minutes. Okay, so with that, I conclude my talk, and I'm happy to take questions. Thank you.
Any questions?
So do you end up having a whole backup system for your configs and allow upgrade, downgrades, multiple downgrades, several levels, you know, things like that?
I don't quite get your question, but like,
well, usually there's a bug that hits and your configuration's lost, so you got to recover your configuration. And then sometimes you do a configuration change and something goes wrong, and you realize you have to go back for whatever reason. And sometimes you have to go back many configurations back because you're doing multiple changes.
Yes. So good one. That's a very good question. So I didn't explain. So we do version control. The version control is not in the modular template. The version control is in the model itself. So every time when we screw up, we revert the model, but not the template. So that's how we do it. We do the rollback.
Thank you for the talk. What's the difference to the Zero Touch network from Google?
Good one. So there are, okay, so I think there are a few fundamental perspective differences. So first of all, we emphasize on the incremental configuration updates. So that's a must in our system. So many of the existing systems, they do like a configuration generation. That's true for sure. But after the generation, so they don't do this like an incremental update. So what's popular is we do this warm reboot. We completely refresh the configuration and do a ROM reboot. So I think this is a fundamental difference between Netcraft and many other like configuration management systems.
Hi, can you go back to the lifecycle page?
Oh, sure.
So my question is, it looks like you have a transition planner, right? So transition planner, essentially you need to decompose from the current configuration to the final configuration. You need to go through either several steps, right?
Yes.
And then for each step, you need a configuration,
yes.
right? Then why in your figure here, you direct go to from network model to the configuration generator? Don't you need the input of the transition plan?
Okay, so that's probably, what you understand is totally right. So probably this is like a misinterpretation of this graph or some other reason. But so I would like to say here is this transition plan consists of multiple steps. And underneath that, there's a transition configuration, also consists of multiple, steps corresponding to the transition plan. So what we do is we essentially it's a queue. We pick the first step, execute it, and then the second one, so on and so forth.
Okay, thank you.
Mm-hmm.
All right, thank you very much.
Thank you.
Oh, you have one more? Oh.
Just related to the last question, do you expect the small intermediate steps to provide some stable state, or how do you manage that?
Good one. So right now we only analyze the stable state. For this, like a transient state, we're for example BGP convergence, right? So we rely on the underneath protocol to take care of that. And I admit that during this time period, packet could get lost, right? But that's a granular, yeah, exactly. But that's a granularity we can control.
Okay. Thank you very much.
Thank you.
Okay. And we have our last speaker of the session, Max Demoulin from, he's a PhD student from UPenn. His advisors are Buntao Lu and Lin Park.
Yes.
And he is going to tell us about detection mitigation of a particular kind of DOS attack.
Let me try that again. I can see it here, but it's maybe I think it's not the right HDMI output. Just crashed. What does that mean? Oh, okay. So what should I do?
the right resolution. Can try single display. Refresh rate, 50, okay. All right. Oh, great. It made my computer crash. Sorry about that. It seems that the world is very much optimized for Apple products in general. You can do that too, I guess. It seems that the thing appears on this screen, but not on the big one for some reason. Crash. Oh, maybe you can use your USB key and give it to you. Sorry about that. Seems to be some occurrence of Murphy law. Okay, so sorry about that. So today I'm going to talk about some work we've been doing at SPAN to automate the detection and mitigation of a certain kind of denial of service attacks. So some fact about DDoS quickly. Usually they come in three main flavors. Some which exhaust the resource of the defender. Some of them which are going to make crash your application by provoking a seg fault or something, or some other which are going to maybe delete the data. So you go to a website, there's no more data, etc. I'm going to focus on the first kind. Traditional ISUS attacks have been volumetric. What that means is that as an attacker, you need to match the resources of the defender. So think about ping of the dev, sync flood, HTTP flood, get flood. But there is, in the past 5-6 years, some could argue later than that, earlier than that, depending on what you treat as application, there has been a shift towards low volume and application level attack. Those attacks have the specificity that they have a very small footprint on the network. They require a very small amount of traffic to bring down your application because they exploit an asymmetry in the protocol. And also, they are not going to be bogus at the network level. Your TCP packets are going to look very much fine. And the attack exploit is going to be in the payload of your request. Okay, there is a point with current limitation. There is a current limitation of network detection and prevention tools for those attacks. So, yeah, okay. Never mind, listen to me, don't look at that. So, if you look at popular tools such as Bro and Snort, for example, they very much use signatures or application or flow profiles to mitigate the attack. But signatures are very static. It means that if you can defend yourself against attacks that you know, not against new attacks. And application profiles are very hard to get by. So if you think about Bro, which has a strict scripting language, it allows you to, for example, say that in this specific type of request, the 20th bytes of the payload should not have this specific character or something like that. It's very tedious to come up, and you have to know a lot about it. And also, last point, those tools have a very coarse-grained granularity, meaning that you're going to drop traffic at the edge. You're going to filter through like the front-end load balancer some specific traffic which you don't want to get in your system. So my slides are totally screwed here, I can tell you. So our approach is we want to break the static nature of the signatures. And to do that, we're going to come to the conclusion that those attacks which are exhausting resources, they ultimately all want to do the same thing: burn out your CPU, maybe burn out your connection pool or your disk access. So we are going to profile the resource abuse impact on application components in a supervised fashion. And we're going to design policies which can apply at the scale of the components in your application, think about microservice, or maybe at a coarser scale, but which are adapted to all various degree of complexity in your mitigation. Overall, we tightly connect the data collection of your plane and the policy composition to actually automate your defense and enable more scale. So, oh, great. Oh, damn. Okay. So in this slide, you have a beautiful picture where at the bottom, you can see your I see. So imagine your application is running as an interconnection of components. Think about microservices. Your request is going to get in your application, and maybe it's going to be processed by some kind of front-end HTTP parser, and the request is going to be disaggregated maybe in some indexing engine or search engine database, any kind of component behind. What we are going to do is monitor the system consumption of the request on those different components and the actual application profile. And we are going to, thanks to a centralized controller, gather all those monitoring data, format them, put them into a database. Then an operator, the network operator, is going to be able to use those data to label them, to label known attacks, and compose mitigation policies. So there are two crucial parts here. Okay, well, I don't know. Let's keep the blank slide. So there is two crucial parts. The first one is that because we have access to some data, we need the operator to give us a hint about is there suspicion of an attack or not. And we allow various degrees of complexity in the labeling, meaning that you can say as an operator, if you have no clue, you can just say, oh, there was an attack. So attack, no attack. You're going to label a period of time saying that during this amount of time, there was an attack. Or maybe you are more informed and you're actually very good at knowing that this was a CPU-bound attack or memory-bound attack. So using this, you're going to create policy templates which are going to be deployed on the system and enforced systematically at runtime. So the policy composition is going to be as follows. A mitigation policy is basically composed of three components. You are going to take an action, and you're going to monitor a specific set of components, and also you're going to specify an enforcement method. Now the crucial part of the policy, which is how do you evaluate the policy? What is your actual decision point? How do you say the action should be triggered? Well, that is going to be filled by our composition engine in a supervised fashion. We're going to basically extract the features and the threshold that you need to use to evaluate your policy at runtime. So to do that, we're going to use a decision tree. Decision tree has various interesting properties. The first one is that it scales logarithmically with regard to the number of data samples that you have. And it's rather important for us because we expect the number of monitoring data to grow linearly with the number of components and the number of features that you have. And also, it allows us to incorporate these various degrees of knowledge that the operator has about the situation. So you could do binary classification. Is this an attack? Is this not an attack? Or you can do multi-class classification, trying to come up with policies which incorporate CPU-bound attack, maybe or memory-bound attacks. And it's also very easy to interpret, meaning that when you get out of the policy composition engine, you can look at your policy and see, oh, the system is going to classify request as attack if the CPU time they are consuming is greater than this threshold, and if maybe the number of concurrent connection is greater than this other threshold. It makes a lot more sense than other classification tools which are very difficult to interpret. So the way we're doing that is very simple in itself. We take the the labeled data from the operator. We're going to remove those low variance features. By low variance features, understand features that has not been exercised by the attack, so they are not going to provide you with information with regard to the classification. And we're going also to reweight the different class to not have class imbalance. You can expect to have a lot of good traffic, and maybe you will only be able to spot with certitude a small attack. Now, if you want to go into multi-class classification, it is possible also to do policies which can maybe mitigate two different types of attacks: CPU bound, memory bound, slow attack. This, however, will likely require some feature engineering, which find features specific to both types of attack. I can take that discussion offline, actually. So, oh, great. Okay, so in between this white thing here, I'm going to explain how we use this system to defend a small web server against CPU-bound attacks. And in this white box was supposed to be a picture detailing how our web server was working. So basically we have five types of components. Your request is going to get in. We have a read component which is going to decipher your request, transmit the plain text to an HTTP parser. Based on the content of the request, the HTTP parser is going to send that request to either an XML module, a regular expression evaluator, or a file IO module. Once you get an answer, there is a write component which is wrapping back your request, deciphering it, and sending it back to the client. Here, there are three components, actually four, which are all vulnerable to attack. So the read component can be vulnerable to TLS renegotiation, meaning that a client can forcefully initiate the renegotiation of the shared secret with the server. This has been shown to be up to 10 times more expensive for the server to compute than for the client. The XML component is vulnerable to the billion loaf attack, meaning that you're going to embed multiple layers of XML, which adds an exponential degree of complexity to evaluating the XML component. Identically, the regular expression component has a flow in the PCRE engine, which means that if you craft a specific regular expression and you ask for the engine to evaluate it, each time it's going to take a lot of time, basically, and you can configure that. So what we are going to evaluate is, if we train a policy using this engine, how is it going to compare against a very naive cloning policy, which is just going to, on a fixed threshold, very fixed static conditions, clone more components to handle the load. And we're going to compare that again, an isolation policy which is able to pick a component and redirect all the suspicious traffic to this component so that the attacking requests do not interleave with a good request. This has a property of not having the buffer queue up when the bad requests are consuming CPU. So for the training part, we throw to the system two kinds of attacks: the TLS renegotiation I mentioned, and redos, which is a regular expression attack. And so the operator is going to label the two attack periods. So what we did is 10 minutes of good traffic, 10 minutes of attack, 10 minutes of good traffic, 10 minutes of attack. And the operator labels those attack periods by being attacks. Now, we are going to train about over the flow features. So the flow features we gather, and I have extra slides to talk about what they are, but they basically gather statistics at the system level about the resource consumption of the flow, or the events, at the time they were unqueued, the number of time spent in the system by the request. And what we found, and it's a very simple setup, but what we found is that one feature was able to discriminate very much in the training scenario, attack and no attack, and that was the CPU time consumed by the request in the system. On a personal level, I will say, if you have more complex application, you might very well have one or two discriminant features. And the nice thing about this, the decision tree, is that the evaluation of the policy is basically a predicate. It's a sequence of conditions. So you're going to take the first condition of your decision tree and put it in your first, in your policy, and then the second condition. Basically, I'm going to cut short to that. Those pictures were precision numbers about the training, saying that this feature was able to correctly classify, at training time, again, most of the attacks. So of course, training is good, but what we're really interested in, how does that generalize? So we threw a third CPU-bound attack, the XML billion loaf attack, on the system, and we see how the policy is able to handle this unknown attack. So, oh, I have a picture. Isn't that wonderful? All right, so this picture is going to display the quality of service, the latency given to the client when the system is protected by the naive cloning policy and the isolation policy. On the x-axis, we have time, and we have on the y-axis, the first graph is going to be the latency, the second, the response rate, and the third one, the number of components, which for legacy reason that I can talk offline, we call MSUs. This third graph is going to be useful to evaluate the cloning policy. So, oh, wait. Okay, so I have a graph, but I don't have colors. So maybe, is there a pointer or something? No, well, we have two red bars which are delimiting the attack time. It was a nice red background to show that this is attack period, but the gray line, if it's gray, is going to show the latency under the cloning policy, and the blue line under the isolation policy. So what happens is that for 5 minutes, we have only legitimate traffic, or maybe 2 minutes and a half, only legitimate traffic. Then we have 5 minutes an attack, and then we leave the legitimate traffic alone on the system. The cloning policy is, what it's going to look at is the average queue length of all the components in our web server. When we go beyond the static threshold on the queue length of the components, we are going to clone more XML components. So our testbed has 3 machines, and basically we just spawn a new thread which is going to have this function handling the specific XML parsing. We are going to spawn up to 24 more components, which is going to spawn 3 computers, and all that to bring back, to stabilize the latency of the client under attack to about 100 milliseconds for a baseline of 10 milliseconds. The isolation policy, at the contrary, is going to very quickly see that this threshold has been violated, and is going to spawn one component on, one thread on which is going to put all the component of the web server and match all the flow originating from the IP for which the CPU time was violating the learn threshold, and redirect all those flow toward this constrained component. So because the attack traffic does not interleave with the good traffic anymore, we preserve very much the original quality of service for the client. We have a small spike at the beginning because we evaluate the policy only once a violation has been made, which is usually what happens for reactive techniques. And then after that, the latency is pretty much the same. So the takeaways here are, nice. The takeaways here are that mostly we move from a static signature pattern and how to compose an application profile to policies over which each component can be learned dynamically and integrated in a loop with the monitoring system on the application and the operator, which can provide validation and feedback. The second thing is that we're able to defend against unseen attacks. And we think that it's a very promising step because in general, if you can reduce the attack domain from all those plethora of different CPU-bound attacks to only the class of CPU abuse on your component, then we think it's beneficial. Also, this per component policy enables various degree of complexity in your defense. And the nice thing in our system is that you don't have to know a lot about the attacks. You just have to get an overall idea of what good performance should look like. But if you are a domain expert in this specific component, then you can embed your domain expertise into your policy and trigger very specific actions. And pave the way for more advanced methods to complete the policies. As a matter of next steps, we want to validate this technique against other types of attacks, understand other type of resource abuse. We have some progress on slow attacks like slow loris and some memory attacks too. We want also, there is an important point here, we want the feature selection in our system is relatively okay. What is questionable is the sensibility to adversarial learning. We have some initial tracks to make sure that the thresholds we learn are actually resilient to an active adversary, but this is very much ongoing research. And also, you can automate the update of those policies, but it's not quite sound. How do you study the evolution of the legitimate behavior? Meaning that if your users suddenly if your components change and your users have a different request pattern, maybe consuming more CPU, well, you will have to incorporate that into your policy making. All those things, we are working on all those different points. And that concludes my talk. So if you have, there was an interrogation mark here. Yeah.
Any questions here? So I was sort of trying to find out what I missed. So why wouldn't a flash crowd be distinguished here from an attack? Because it's CPU intensive.
So how do you differentiate legitimate traffic from attacker, right? So if you have a bug in your software, indeed, a legitimate attack could, or a legitimate traffic could also burn out CPU. However, if you have an integration pattern which allows you to look at, you have some expectation of what your CPU consumption should look like. That can evolve or not, but if you look at the statistic that we monitor, the attack patterns are very specific. You're going to observe very much an asymmetry in the request rate compared to the CPU consumption. So in general, you don't expect some specific class of user to to go through your integration testing and violate all the CPU performance conditions. Is that what I will say?
Anything? 1, 2, 3. Okay, thank you.
Thank you.
I guess I hand it over to Jen for deciding.
Great, so we have a few minutes left for sort of a general discussion. One thing I thought might be helpful in teeing off the discussion is Chung-Hoon Kim from Barefoot Networks, another member of the program committee. I thought maybe he could start by giving his perspectives on the topic and also reflections on what he's heard today, and then we can just have others jump in from there.
Thanks, Jen. Yeah, it was there are several interesting talks. While listening to the talks, I jotted down some of the ideas that I came across. The first thing that, especially Jeff's talk, reminded me is that if you're trying to automate the networking system without changing the network itself, it's probably not going to work that well. I mean, the current network architecture and systems and protocols are designed based on the assumption that there is going to be a human being who is going to be operating this system. So we probably don't want to repeat the same mistake here. So if you really want to build self-driving network, we'll have to revamp the underlying infrastructure, the networking substrate itself, basically the control plane and data plane and management plane all together. Especially the direction will be more around simplicity and homogeneous sort of regularity. And the reason is because, for example, BGP is known to suffer from divergence, right? Even if you input exactly the same thing based on subtle differences in starting conditions or timings, it may actually legitimately end up in two different situations or multiple different situations. Even if you have a really, really smart, intelligent learning system, and even if it generates the best configuration, if you cannot actually implement that best decision predictably enough, what's the point of having, decision-making system, right? Things like that nature, and maybe so. The complex BGP-based ranking is something that is probably quite unique in large-scale ISPs. But even in simpler data center networks, this sort of divergence scenarios can happen, for example, especially when you update devices with different configurations. somewhere in the middle of update, something goes wrong. When you roll back, different devices, even for the same devices with different configuration or even the same configuration, depending on the timing, you may actually bump into different unexpected behavior. So all these kind of unexpected behaviors and indirect control, indirect visibility will probably make self-driving network much harder to achieve. So that's one observation. The other one is, again, the analogy to self-driving car. So self-driving car is made possible not just because we have great smart AI, but it's also made possible because we have great and amazing sensing technology now. So what's that equivalent, great, amazing sensing technology for networking? We don't, obviously, today. We don't even know for every single packet which path it has taken. If you do ping and trace route, which path those packets taken, but you don't know. Just pick every single packet and then tell, okay, how did you come here? Why did you come here? How much time did you spend at each hop? There's no way we can answer those kinds of questions. So without those kind of knowledge, self-driving network is probably going to be very hard to achieve. And the reason this sort of great sensing technology is very important, in my opinion, is that this learning system or smart autonomy system is very different from simple automation system, in a sense that automation systems, when it faces something that is not in manual, it just stops, right? It's just workflow automation. Whereas these smart learning systems, when it faces an unexpected scenario, it'll try to find the closest possible situation that it has seen before, and then it'll try to react. And then even if that reaction was not that great, it'll learn from there. And then next time when you see something similar, the result will be probably better. So that's, if you want to have that kind of learning systems, then the feedback is really important. The amount of feedback and the granularity of feedback, and then the indication of the feedback that, okay, this decision that I made lead to all these different consequences, and then these consequences point to me that what I have done is actually driving the entire system into a positive direction rather than negative direction. Without that feedback system, learning systems cannot simply exist. So that's why I believe the visibility and telemetry is even more important. It seems like Margaret has a question back there.
Automating a car, you sort of know all the different things to expect, right? But when it comes to automating a network, I mean, I found through my experience, you're constantly adding stuff, changing stuff, and it introduces bugs that you didn't even think of. Every time you think you've covered all the potential or characterized all the different types of bugs, another round comes up that you didn't expect. And maybe you guys are further along and smarter than me, but I mean, I've been running networks for like, gosh, 10, 20 years. And I'm telling you, we were constantly learning new combinations of things. So that's why I'm suspect that, can we really go to full automation? I don't think we can. The best we can do is maybe more of the discipline, more of these concepts of principles, as you learn, and then it just helps you recover faster and faster. But through automation, I'm not as convinced.
So I won't disagree that there's a lot of risk there, but I do think actually that self-driving cars face in some ways the same problem. And one of the slides I skipped over was a quote from Vint Cerf talking in some previous talk about how in order to test our self-driving cars, Waymo being a unit of our company now, there's a lot of effort placed in things like having people slide out in the street lying on skateboards or pop out of trash cans and things like that. They're trying to create a whole bunch of unanticipated things. I think the problem is that that division probably has a lot more experts in testing than the average network design house. And you really probably need to invest a tremendous amount of money and skill in getting to anticipate the unanticipated in order to test ahead of where you are. I think the problem you ran into is because you're basically always in reactive mode, as opposed to really having the ability to invest in figuring out what might happen that you weren't anticipating. Here's, I'll let you respond. But
So, you know, you're as smart as your ignorance, right? And that's the problem. So, yeah, definitely we went down the whole, I don't know, for people who might not realize, I used to work at AT&T, so that's the discussion here. That, you know, you do a lot of, I mean, we got into definitely a lot of this predictive concept where you had a class of problems and then you try to predict and expand the signature and all this other bit. And of course, as you learn, you realize, you know, areas that you didn't cover. But like I said, I don't know if there's any other better techniques out there to make it more complete. And I agree that the automotive has issues, but in the end, the class is visually seeing everything that's going to jump in front of you. So in some sense, it's a common class, and now you've got to focus on how do you see all that stuff. Versus on the networking side, I mean, yeah, you have classes of, you know, queuing, memory, you know, that, I mean, but I don't know, we never could get it to be that simple that there was 5 classes and we just had to drill down. But I've been away from operations for like 5 years, so maybe people have now figured it out.
Yeah, I mean, I agree, and that's actually kind of related to the third point that I wanted to mention here is that I think we have to subdivide this into the individual subdomains here. If you just say that self-driving network, it becomes just too vague, and then we don't know how to start, where to start. So the types of technologies that, or self-learning and self-controlling technologies that you need for, say, traffic engineering or congestion control may be drastically different from access control or security controls and so on. And also more sort of operational things like configuration management, rollback, RMA, those kind of things will also need very different technologies. And even if you look at the domains where, you know, the AI systems turned out to be working effectively, for example, video sensing uses very different learning technology than, say, natural language translation. So this may actually turn out to be individual subdomain specific problems. And the last one, I keep going back to the analogy to self-driving network. One thing I think we don't realize that well and frequently is that the transportation industries are actually built on top of regulation and standardization. Standard may end up becoming yet another standard, but really we're relying on some really basic, simple, regulated environment to make these kind of things happen in self-driving cars. For example, you know, in one administrative domain, like in one country, everybody drives on the same side, right? Everybody around you, if you're a car, they all run roughly at the same speed as you. It's not like that the other car runs at this, you know, like airplane speed, whereas you're running at real car speed. All the car plates are exactly at the same location relatively to the car, and then, you know, all the traffic signals and signs are meant to be sort of in that position with different, you know, exactly expected sizes and so on. Do we have that kind of regularity in network? I really doubt that, right? So unless we can actually establish that kind of regularity, at least within each administrative domain, starting this kind of problem will be really, really hard. Yes?
So just as a comment to that regularity on the driving situation, it seems very much that we have some rough guidelines about how to behave together on the road, but on reality, it's very different from what it is on paper. So do you adapt a system to mingle with the reality, like being like very much sticking to the actual regulation on paper, or do you try to integrate with the outlaw behavior of 90% of the population too? And I think that's a very difficult game to play, because either you have to make everyone which is non-automated go to that direction, and which is very difficult for networks which are just, you know, interconnected. sub-network components. So I think that's maybe what one of the things you were referring to indirectly. And there is a fundamental question here.
Yeah, I agree. And yeah, just to add one more thing. Like data centers usually have regular build outs, right? Portions of your network are built every day, as the speaker from Alibaba mentioned, and then they retire a fraction of the network regularly. So then you have more hope of introducing something new, more in a sort of anticipated fashion. But still, though, we will have to expect an environment where there are automatically managed portion of your network and still non-automated portion. So that's a scary thing as well.
So I'll make some generic comments. I think what type of networks you have in mind needs to be defined well. So when I started off on my journey on these sort of things, to me, self-managing networks were about these organically formed wireless networks in communities where there was no IT staff and people were not smart. I mean, people were not domain experts to fix these sort of things. So then you had to build enough technology for it to be able to diagnose problems and isolate it and then perhaps mitigate it by moving around. So there was a lot of work actually in the wireless network community on the specific topic of self-managing networks with a lot of papers being submitted. Now, if you look at data centers, there's been a lot of work there too to figure out what causes failures, and paper after paper or work after work shows it's a human issue, which is a predominant reason for this. And so the trend that I see happening is that corporations and big companies that run these cloud networks, data center networks, are going to create disciplines around not having humans touch anything without some sort of a consent. So for example, in our case, we had this CrystalNet thing, and you have to go through CrystalNet before any configuration file can change, and this piece of software will verify everything is kosher before it does it. And that's going to get even more as we move along. So for example, you would have to have some certificates to be able to touch the hardware. The hardware is not going to allow you, and you're going to have more support inside the hardware. So from that perspective, if the question then is that the networks are running smoothly, I think we're going to move towards that end, and it may not be in the way that it's been described today, or Balaji also gave a talk on this where you have sensors, actuators, and then do it, but in a sort of a different way where the network is running smoothly. So I guess the point I'm making is one has to sort of think very hard about what is the scenario you're going after. Because a lot of these technology, like the last talk, which was about denial of service attacks, that kind of research has been going on forever and will continue going on forever and get better and better. So so I guess the question to you or everybody else is to answer that: is it really just the sexiness of managing thing, or is that a path that you really want to drive very hard towards, right? Does that make sense?
I'm just going to add one thing. I think one thing that has changed that's making this timeline relate to something that Chiang mentioned. We're starting to have the ability to have better telemetry in the switches and also greater direct control through programmable networks. I think we have been studying these problems for a long time, but the hope is we can wipe the slate clean a bit by actually having greater visibility and more direct control in settings that we used to never have it, like data centers and even carrier networks down the road.
But the actual notion of self-management, I mean, if you're thinking like a TCP protocol, which is kind of self-managing, right? Self-regulating and things of that nature. But the extreme of that is that there's no human in the loop.
Right.
So I think that at least the cloud vendors we will make sure this problem starts to go away in the sense of by creating more discipline around it.
Mm-hmm.
But the gradual notion of like a self-driving car and self-driving network, it's not clear to me where it's totally needed. It'd be good to have, but it's not clear to me that it's something that is not going to happen regardless of sort of thinking about these things.
Fair enough. Others?
I have also one comment on this self-driving network and self-driving cars analogy. So I think self-driving cars is a cool comparison to actually make people understandable what this is about on a high level and make it intuitive. But I think we should not make the mistake to actually really compare those two fields, because I mean, it's nice to look into what we did in computer vision, what we did to make self-driving networks work, maybe learn from our mistakes, learn what steps we had to do, but then also take a clear look into what we have in networking, really look at the data we have. And just because maybe we can't make sense of the data we have, this doesn't mean that it is not as structured or not well modeled. In vision, we are living in this world, we are perceiving this, so we are very well equipped to actually understand what's going on there, whereas the data we have in networking is, for us, totally unstructured, but still, we really have to look into what data we have there. Maybe we even need different modeling techniques compared to what there is at the moment in AI and ML, go beyond simply applying stuff that was successful in vision and actually develop principled methods in the domain we're in for the data we are working with. And this is something we can't simply say it's unstructured, it will not work. This is something we will have to look into, and we will have to see if we can make this work.
Yeah, so let me clarify. I guess I was going for the zero human. that's the part I was arguing that I don't see that. But I do agree telemetry is getting a lot better. And I agree the techniques on looking for patterns. So usually what happens is when you have a problem, you need the historical logs and you look for patterns, and a lot of times it's human. Now we have techniques, so at least you can automate it faster, and then from there you can get to root cause faster and so forth, and maybe you can even automate some of that. But to get to the zero is the part I don't think. So maybe it's 80% versus maybe today we're only at 20%. So I'm not trying to be so negative that we can't go forward. It's just that I was just trying to make the point that things are constantly changing, that I'm not sure you can get to the zero. That's really all I was saying.
Yeah, one thought I had was, if you think about telco networks which run at 5 nines and 4 nines, do they require self-management? You said you came from AT&T, I know you came from AT&T Wireless, right? You had 5 nines and the network was running pretty smoothly and everything was great. Right, so that's the point hasn't been raised the whole day. So one point that hasn't been raised that noting me that I think the drive towards self-management or automation is essentially to reduce the IT cost, right? To reduce the amount and number of people involved, the time it takes to fix things. Nobody said it, but I think that is the real driving factor here, right? How do you reduce that cost? Because, I mean, if the AT&T network is running at 5 nines, that's a pretty good network, right?
So to keep it at 5 nines, you had to do all this stuff, right? That was the point. It didn't magically just move by itself.
Yeah, lots of redundancy in those things.
Yeah, so how did we get to 5 nines? We had redundancy, and we were doing the whole data collection, the analysis. You hit a problem, trying to figure out the signature proactively, looking for it, then predicting it, and then, of course, preventing it. So, and then every time you had a new set of problems, you just kept going through that whole loop. So the discipline, and that's how you kept to 5 nines. I literally had a chart, right, that monitored, and when I think I was telling you, right, when it would above a certain number, we used the factory metric, defects per million. It would actually work magically, and you can literally see, and I was an AVP, so you could literally see when it's at one level, it got to me. When it went to the next level, it went to my boss and went to, right? And so I always told my team, the goal is to not go beyond me, right? Because then they help you. And so, but to do that, it was a lot of work. And so now I'm hoping, right, now we have better telemetry, better, analysis of the data to look for repeatable whatever, to then get to the root cause, and then from there automating, or maybe you can even, learn how to automate whatever the recovery is. And so then you need less people. I mean, that was my whole goal when I created a lot of this stuff within AT&T, was to basically reduce the number of people to support. But then you needed a set of, quality people, because you got to be very disciplined, very analytical, and obviously be able to program and all this other bit. But like I said, my point is, how far can we really get, even with all these tools? And I was just making a comment, compared to a car, which I still simplify, is easier in some sense because you have certain boundary conditions. So yes, okay, so let's say you go 50 miles an hour, and not that everyone does it, and you got to, but at least you know your range that someone might go 100. Or, you know, you go on a road and you have a range, someone will go off. I mean, you sort of know the boundaries in some sense, what can happen. And I'm just saying in the network, at least from what my experience is, for what you know the boundaries. The problem is it's amazing. Things happen, you go, oh my God, who thought of that problem, right? And that's all I meant.
But I think, you know, in what you mentioned, sort of in terms of sort of in the last 5 years versus today, so in terms of the data and analytic aspect, so this ability now, I mean, we are certainly not there, but this ability to do these things in real time with the sort of data we can do, I mean, that has improved, and the future there looks sort of promising. But I agree completely also with you in terms of, when, you know, so Jen and I. Right, but I mean, the real-time aspect was never there. Yes. Yeah. But I always sort of, talking with Jen, we always sort of find this sort of interesting, I think, naturally nowadays, sort of security, and Jen thinks performance. And then when I think it that way, then I go back to sort of your question, so where is the natural place to maybe start thinking in this space? And that is, you know, small enterprise security. That may be a way to, with the right data, to do something that gets us close, you know.
You have a target audience. So here's the deal. You have to have, so it's great to have a North Star, and the North Star says 0. But it's also, like, you can't, if in order to say you're going to be successful, you have to be more realistic about it. And so so again, I guess we're going to repeat some of these points. So the companies that run cloud networks are going to continue driving very hard to ensure that their network score don't go down, right? So they're going to put more discipline. They're going to get the hardware vendors to move on putting hardware support in it. They're going to do everything in their power to do that. And yes, the community will help in the process of actually coming up with great ideas that get incorporated. But then there is this smaller enterprises that cannot afford IT. They cannot, it's just a pain, and that's why the cloud sort of came, but they still have their networks. They want 0, right? So when we talk about all these problems, instead of focusing all the time on the big, large-scale systems, which already have billions of dollars invested and will continue, why not focus more on the little guys and create these networks that do have them? And their solutions will be different than the solutions that we are thinking here. So that's the kind of point that I sort of just wanted to say. So that way you have a right North Star, and you actually, when you achieve something, you can say, you can call it a success.
Maybe also a comment again on the analogy we have. We say self-driving cars and self-driving networks. I think maybe we are taking the wrong view even here. Like, I would not say we have a self-driving city, which is like constituted of many cars, which are self-driving. We also don't have a car, we say we have 4 self-driving wheels. So maybe we have to take also a different view, like saying of course, self-driving network is the overall vision, but again, maybe it consists of smaller parts which have to be somehow become, in a sense, self-driving. I mean, if we think about a switch will never go from A to B, like from location point of view. So we might have to change also our mindset to find maybe some small steps first, take smaller entities which we can really self-driving in order to get then to the big picture in the end. That's the full automated network. That's also what I think here.
So I want to make a brief point that actually one problem with the Corvair is that its wheels were actually badly self-driving. And if you look at the way that I'm not an automobile engineer, but there's actually a fair amount of mechanical mechanisms to make sure the wheels do more or less the right thing. So for example, there's this concept of caster, which I guess applies to the front wheels and forces the car, if you take your hands off the steering wheel, to go back into a straight line. So those wheels are in fact self-driving at some very primitive level of behavior. And that's actually what makes it possible for normal humans to drive cars. I think
an interesting analogy is the difference between flying a regular airplane and flying a helicopter. A regular airplane is also basically, if you take the hands off your controls, what I've been told is that they keep flying in straight and level. If you take your hands off of a helicopter that doesn't have a completely automatic control system, it's going to go wherever. And there are similar behaviors with sailboats. In some cases they're stable, in some cases they're not. You really, I think, would like to drive for that level where, when it's appropriate, you actually do have the equivalent of self-driving wheels, and in other cases you probably can't afford that, like helicopters.
One point that Victor made, which I think is really important. I mean, obviously the cloud is the setting a lot of us have been thinking about, and it's sort of, I think in the SIGCOMM community, one of the main networks we think about these days. But that may be better in hand, like you said. And that, I mean, I think the nice thing about that point is that all of us have campus networks that we live and play in every day. And so there's an opportunity. We all live in a small enterprise. And if we view our home network as an even smaller enterprise, we've all got one. And so there's an opportunity to do things there. I would also say, I mean, a harder thing for us to work on, but also important, is the cellular network, whether it's the actual wireless portion of it or the cellular core. That obviously requires more relationships with companies than working on one's campus, but that's certainly another area that we don't see much of at SIGCOMM, and there's a lot to do there to make that substantially better.
So my thinking on the cellular network is the following. I think like about, I don't know, 10 years ago, 890, when we started to have this major shift in the cloud. So from our perspective, this is when I hired Albert now, right? So this was, from my perspective, the story was quite the following. So we were being kind of held hostage by the Ciscos of the world and the Junipers of the world, and I'm sure people are here there, selling us hardware equipment which had many, many features in it and was very expensive. And so the customers were taking dependency on us, and we were taking dependency on them. And so if anything went wrong, we had to go to them, and they had to come out and fix everything. And so we were paying a lot of money and losing time, and that was just not going to work. So which is why most cloud companies took control and said, we're going to just work with the Aristas, or we're going to build our own smart mix and all. Now, if you look at the telco industry at this stage, it's sort of the same thing. Now, after the convergence of the stack, their stack used to be very different from the IP stack, but now they're becoming very similar. So 5G will be a similar stack. They are similarly held hostage by the Ericssons and the Huaweis and the Nokias and whoever else. Selling them these massive specialized pieces of hardware that is exceedingly expensive. And there's a lot of frustration in the telcos. They want to innovate, so they need to sort of have the ability. So that's where the opportunity then comes. But they are very afraid because they're used to running at 5 nines, and that's the scary part that these equipment vendors provide them, saying, "Hey, you're not going to get 5 nines." And so you're completely right. I'm actually just backing up what you're saying, which is that's where the opportunity is. And so when we look at the cloud and all, I sort of feel like it's great, but hey, guys, I mean, there's a lot of people working on this stuff, and it's open and working. But that, if you break that nut, that's a $500 billion transition that could happen. You could get them there with software. Some thought.
So I agree with you, Victor. Like even this big online service provider, their WAN portion has 4 nines, 5 nines, but their data center portion is probably still 2 nines, at most 3 nines. It's not that they don't have such high quality demand in data centers. It does, but the cost of making that happen just simply outweighs the benefits. That's why they're not getting there. But if this kind of technology, can add you another 9, 2 nines, then at a much lower cost point, yeah, that's probably worse. Another thing that I want to mention is that these 3 nines or whatever nines are based on only observable incidents, like hard failures. But there are gray failures, like microbursts and occasional packet drops, silent packet drops. Those things are not included, and yet applications suffer a lot. So if you can detect those kind of things and then react a lot more intelligently based on this, and then actually make application-aware, application-level performance improvement, that would be another interesting aspect that we can look at.
Actually, because you got FCC regulation, it's more than just heart failures. It actually includes a lot of those, because you have to. Because, I mean, you got the whole regulation. Anytime you have a major failure, all of a sudden the government's on you. That's the reason why you have to react the way you do. You know, I mean, I've been involved where medical doctors are screaming at me because something's not, and they're worried about whatever. Airline pilots, I mean, just on and on and on the things that I've gotten pulled into. And so you become very conscious of even degradation, right? If an x-ray is taking like an hour and they have someone on whatever, I don't know. The problem is that they need it in a minute. So it's, we actually started getting into the whole, yeah, no, we had the same thing. We have SLAs. Yeah, we had SLAs, yeah, same thing.
All right, we're getting close to finishing time, I guess. Any further comments that you would have? I mean, I think, you know, to some degree, we had these two sets of talks where the first set was sort of really sort of high level, and who knows what's, you know, crystallizing there with respect to something interesting as far as these aspects are concerned. We had this second set of talks that are very sort of case study specific, that give you little hints of what may be possible. And then this discussion, I think, points into this direction. You know, look to some degree for something concrete where you can, you know, get your head around, your hands around this idea of what do you mean by sort of self-driving. And I think I completely agree with you that don't think of take the human out of the loop, but, you know, minimize the, I mean, you have these domain experts that you want to use their expertise where it's valuable, and not bother them with things that are sort of doable, or that they can be automated, but they have to spend all their time to do this. And at the same time, I think with these opportunities that come with, you know, enormous capabilities on the measurement side, you know, it just looks very much possible to reach a goal that sort of indicates, oh, this may be the sort of the vision that sits there that's doable, or achievable, but, you know, it certainly will take a lot of time. So Jen, do you want?
Great. So I just want to, oh, yeah.
So a last consideration is that we all want to build software. We all want to do cool stuff and add more and more and more feature. I think the key point here is that the human in the loop is critical, but does not scale. You cannot be a domain expert in all the different components of your application. So if you want to reduce the cost and allow the scalability of having more components, more complex systems, more features for your users, you need to support your domain experts by all those data that we have and all this knowledge in extracting structure from the data and things that we don't see. So as a maybe wrong parallel, think about how do we observe space? We don't observe space with a wavelength of our visual cortex, right? We look at infrared and other spectrums which are not directly visible, and we play with them, we interpose them, and we extract structure from the universe.
So I think actually just one point I'll add to that is, you know, Vint Cerf used to say that a router is a computer with multiple interfaces with a graduate student wrapped around it. And then the number of routers grew too big for the number of grad students. You know, so the lack of scaling of people is a kind of fundamental problem.
Just as final comment, I believe that one natural way of thinking of self-driving, self-managed, or self-run networks is to consider the network as being self-run or self-driven as a state. But I think it is wrong. It should be thought as a process, because I don't believe that the human wouldn't be out of the loop anyway. But from the management perspective, the human is there to treat the exceptions, and then the exceptions could be learned. And then if the human is there in the beginning, but then that knowledge could be transferred to the network, so the network will be more intelligent on the next iteration. But because exceptions will be there anyway, we have to have the human there in order to, let's say, teach the network. And I don't believe that we have technologies today, so networks could properly learn out of the humans.
Great. Any final comments? Great, thanks so much, especially for sticking around a little extra time. And I particularly appreciate Jeff's keynote, the 6 speakers, and the really lively discussion we just had, especially at the end of what's been, I'm sure, for many of you, a long week. So thanks so much. And if you have any feedback or suggestions for us about the workshop, we're more than happy to hear your thoughts. And otherwise, enjoy the rest of your time in Budapest.